I think Professor Satyarana also has joined. Good morning, sir.
Morning, morning.
Yeah, so Professor Satish also is here. Professor
Yeah.
David from Washington State University also here.
Oh, great.
Yeah.
Hi, Satish. How are you?
I'm fine. Good morning, and how are you?
Oh, good, good. Just thought I'll just say hello before I get on to my other meetings. Thanks for accepting our fact colleagues' request and coming on. Yeah. And
Again, thank you so much for the invitation, and I think it's wonderful that this is happening. And more importantly, I can actually see a nice, fantastic core forming around advanced manufacturing and materials. And it's
yeah. Look forward to your continued support. You've been great support to our program. Yeah. And also, I see Dr. David Field online. Dr. David Field, thank you also for accepting our request.
Yes, thank you. Nice to see you. It's a pleasure.
Yeah, this is I'm Professor Satya, the director of the institute. Yeah, and I don't know if you heard my. Were you there yesterday? We've identified manufacturing and materials as one of the thrust areas of our institute in terms of taking forward our various academic and research activities, and we're looking at we are a new institute which is a little over 5 years old. So we are looking at starting our active collaborations and so on. We have already started collaborations with Satish's group at Texas A&M. We have a lot of exchange of students. Our students have gone there to do PhD, have done internships there, and we have had joint workshops earlier. So look forward to working with your group also. Yeah. So thank you very much.
Thank you.
Let me not disturb the schedule. Thank you.
Thank you so much. Thank you, sir.
nice to see you.
Yeah. So now I think we can start. Good morning and good evening, distinguished delegates, participants, and colleagues. This is Dr. Ajay Kumar, Assistant Professor, Department of Mechanical Engineering, IIT Tirupati. It is a glorious moment to extend my warm wishes on behalf of the organizing committee of 2 days international webinar on advances in materials processing and mechanical testing. I want to convey my heartfelt gratitude to all the distinguished experts from USA, UK, and Finland for accepting the invitation and presiding over this webinar on advances in materials processing and mechanical testing. So let me introduce today's speaker. We have Professor Satish Boppatnam and Dr. Bhaskar from Texas A&M University, USA. And we have Professor Pradeep Manges from University of Nevada, Reno, USA. And then we have Professor David Field from Washington State University, USA. And then we will have two talks from the industries. And then we will have Professor Nikhil Gupta from New York University. So the first talk will be delivered by Professor Satish Boppatnam and Dr. Bhaskar. So it's my pleasure to introduce Professor Satish Boppatnam. Professor Satish is the Rockwell International Professor with the Department of Industrial and System Engineering at Texas A&M University. He is also the director of Texas A&M Engineering Experimentation Station Institute for Manufacturing Systems. His research in smart manufacturing addresses the harnessing of high-resolution nonlinear dynamic information, especially from wireless MEMS sensors, to improve the monitoring and prognostics, mainly of ultra-precision and nano-manufacturing processes and machines, and wearable sensors for cardiorespiratory process prognostics. He is a fellow of the Institute for Industrial and System Engineers and the Society of Manufacturing Engineers. His work has been recognized with Oklahoma State University Regents Distinguished Research, Haley Wharton Outstanding College of Engineering Faculty, and Fulbright Tocqueville Distinguished Chair Awards. So I welcome Professor Satish and Dr. Bhaskar. Now I request all the participants to sincerely attend these lectures. They are very useful for you, for your research, as well as for your academic careers. Thank you. Professor Satish, over to you.
Thank you so much
Thank you.
for your kind introduction, Dr. Kumar. And again, it's wonderful to be speaking and being in the midst of IIT Tirupati, the faculty and students. And very good morning to all of you. This is very special to me because for multiple reasons. My first visit to IIT Tirupati was in the spring of 2016. And at that time, the institute just got established, and I had a chance to meet with Professor Satya. And I have had a chance to meet with him again and again. Probably he's had more interactions with me than probably many other faculty from the US, perhaps. And every time I come, I see this place grow. And I'm very happy to see that we now have a fantastic core of faculty, researchers, and students engaged in advanced aspects of manufacturing and materials studies. And today, what I would like to share with you is research that was conducted in cohort with my PhD student, Mr. Bhaskar Butcha. He is finishing his PhD. And along with his work, this talk will touch upon the works of my recent graduates, Zemo Wang, who is currently on the faculty in SUNY, Binghamton, and Asif Iqbal, who is now on the faculty in the Arizona State. And also all three of them, Bhaskar, Zemo, and Asif, they were mentoring students from IIT Tirupati when the students were there as interns. So some of the papers I will be presenting would be co-authored by students and some faculty from IIT Tirupati, and I would like to acknowledge as I mentioned them. And this talk essentially is based on some of our recent works. And my talk will begin by introducing smart manufacturing, just to establish a common terminology with which we can proceed. And then we'll go into basically a slew of works that has been done in the last 2 to 3 years. The first one will touch upon the architecting of this smart manufacturing machine tool with which we could conduct some of the things that I had mentioned as part of the topic. And through this process, I will introduce the idea of material on demand manufacturing, as well as what is AI-driven characterization and process monitoring. And also we will get into the details of some of these methodologies. At that point, Bhaskar will take over and then give those details to us. So the overall presentation will involve virtually 2 parts. My initial introduction hopefully will set the stage for understanding the nuances of some of the technical details that Bhaskar would present. So let me begin by introducing what I think of when I talk about smart manufacturing. Smart manufacturing, as many of us probably can relate to, is the next generation of manufacturing. And of course, it imbibes the advances in AI and data science, advances in materials, and also sensing, communication, advances in energy and computation, and the latest communication electronics. And of course, it is an advancement in the manufacturing technologies in particular, including additive, hybrid, and so on. So confluence of all these 7 different technological advancements constitutes what we can think of as smart manufacturing. And currently, Texas A&M has a very active research portfolio in smart manufacturing. What you're seeing are the 5 projects that we are currently undertaking, just our group is undertaking in this area. And today's talk would be based on the things that we are doing in the first 2 projects. The first one being in the development of this hybrid 3D printer. And second is leveraging the capabilities of this printer for autonomous materials discovery and material on demand manufacturing. So to set the stage once again, when we think about smart manufacturing, of course, we bring all these technologies together. The immediate question is, so what? Essentially, it leads to two very interesting possibilities. The first possibility is transformation of manufacturing into service. So essentially, we can, it's basically like a Uber for manufacturing, right? Um, so the idea is today, whenever you want to have any custom part made, so you basically reach out to a supplier, and the supplier has to make, and they usually take a few weeks before they make it and then ship it back. That's because the entire IP or the intelligence is completely concentrated. But with advancement in smart manufacturing, manufacturing as they speak is going to get democratized. So in other words, you can actually push the high IP content to your local manufacturer so that you can actually not only deliver the item, but also make the item at the point of need. Everybody is familiar with the models of Amazons and so on, right? What Amazon can do is it can deliver things on demand. It's still not able to make things on demand. They are working on it. And what will enable such make on demand capability is smart manufacturing. How will it, what kind of technological advancement can lead to that? We will see as we get into the details of this talk. But first one for us to remember is smart manufacturing can transform manufacturing into a service. Second transformation that can take place because of smart manufacturing is the idea of materials on demand manufacturing. The idea here is the whole idea of the customer getting the needs fulfilled by being able to manufacture on the fly. But this process, if you go deeper, essentially involves taking the customer needs and converting them into functional requirements, clear specifications, and translating the functional requirements into clear design specifications. If you think of design specification, the first thing that comes to our mind is basically the geometric shape that can be accomplished through the use of appropriate CAD drawing. That will be the outcome. And similarly, you can actually specify the morphology, the kinds of things that you want to have on the surface and so on. And third, microstructure and the material composition. So in essence, the entire process of design essentially involves specifying the shape, morphology, microstructure, and material composition. Currently, in most of the engineering practice, by and large, the microstructure and material composition are pre-decided. We only select them. And most of the engineering design involves generating the shape and to an extent morphology through the use of manufacturing processes. Again, let me repeat. Current design practice essentially involves generating the geometric shape and morphology and just selecting the material. The transformation that we are looking at is we are moving from just selecting the material to actually designing the material and tailoring the material for the application we are looking at. So you're creating material on demand, just like you're creating the shape on demand. Please remember that. So this is a new possibility that's emerging. Why is it important? If you look at many of these advanced applications, they are all becoming possible because of the material tailored to an application. What you're seeing here is basically a morphing wing of the next generation aircraft. And this whole wing of the aircraft is a single piece, except that some parts of this aircraft have a special shape memory alloy material tailored to create that kind of an actuation. And similarly, you can look at 3D printed homes. You can look at the next generation of complex concrete, whereby you can actually endow the right kind of property at the right location so that it behaves appropriately for this whole construction. And even at the consumer level, you can actually create integral components, integral custom components, like You go to your doctor or optician, you get your specifications, and as soon as that's done, it will be digitally printed. Again, a single piece, but different materials put together. So the whole idea that's getting transformed is you're actually designing the material to go with the specification. And it's highly personalized, and you can enhance the functionality like you have not seen before. And you can actually put, quote unquote, multiple materials, quilt them together to make your product. And that can lead to a lot of advantages, especially for people who are conscious about the environment, very frugal, minimal material wastage, and also optimized for energy. So there are lots of interesting possibilities will emerge through the use of this material on demand paradigm. And how can we enable it? Do we need a new kind of a machine whereby you can actually enable both this manufacturing as a service as well as material on demand? One way in which it can be done is through the use of what we are working on is a smart additive or hybrid machine tool. I will get into the overview of this through the video, and I will let Bhaskar take over after the video to describe the nuances of how this hybrid machine is constructed and how we can actually use this hybrid machine to enable the material on demand manufacturing, and how can we tackle some of the technical challenges related to materials characterization that will occur in this paradigm of materials on demand manufacturing. So please give it a listen, and let me momentarily stop sharing and start sharing the screen again, because I forgot to do a particular step I'm supposed to do. Bhaskar, would you be able to share the screen from your end for that video?
Yes, sir, I can do that.
Yeah, please do. Because it was not letting me work on the audio.
Okay, no problem.
And again, as we present, feel free to ask questions through the chat line. Since one of us will not be presenting, we would be glad to answer as the questions arise. Thank you.
Autonomous materials discovery is a challenge for current machinery. The research is an important step toward practical and fast material discovery. The Smart Hybrid Machine combines additive manufacturing and machining. It uses lasers, metal powders, and heat treatment to modify the structure and properties of the created materials while collecting data about the material. This process can be automatically controlled using a computer. The computer uses code to create parts that can be simulated and verified by the machine before printing begins. The synchronous use of a high-speed camera and other instruments allows for faster data collection, which will speed up the discoveries of material properties. Around 1 gigabyte of data is generated every minute by the machine. This data, along with the discoveries from the machine, are speeding up materials discovery for the future.
Yeah, that was Bhaskar from 2 years ago. Bhaskar, can you continue with describing this machine in full detail?
Yes, sir, sure. Thanks. Yeah, for those of you who are wondering why I don't look the same, that was before the pandemic. And Dr. Bukavitnam, thanks for giving the very high-level introduction for smart manufacturing and the two facets of it, like how we are discussing the manufacturing as a service and also for the material on-demand manufacturing. So in the further slides, which I'm going to discuss, so we are going to get into the intricacies of this hybrid machine tool, which is being central to these two concepts, which we're discussing. So let me start off by giving the capabilities of the hybrid machine tool, which we were discussing about. So the first thing is the finished capabilities, which I'm going to discuss. So as we know, additively manufactured products, when they just come out of the machine, they don't have a very good surface. So They are printed layer by layer, and the material is accrued together by like melting of metallic powders. And obviously, when it comes out, the printed surface doesn't have a very good finish. With this concept of this hybrid machine tool, where we have the additive and subtractive modes of the machine built into the same machine, what we can do is we can print the surface, and without removing the part, like those of you who are in manufacturing, we know like how much of a time just gets wasted when we are transferring these parts from machine to machine. If we are printing, then if we have to mill the surface and level the surface off, then we have to take it to the grinding machine and polish it. So all these steps using this novel attachment of like the subtractive part of the machine tool, we can do it all in the same machine. And we have actually demonstrated in this particular manufacturing letters paper that we can reduce the cycle times of the overall process by up to 40%. So what we can get from this is the samples are ready for characterization studies all in a single machine. So if we are aware of these characterization process, like if we have to go into nano indentation and find the hardness, nano hardness of some particular material which we have just printed with our particular composition. So to get that particular part ready for characterization, it takes like multiple machines and like multiple processes to get there. And with this particular setup of this hybrid machine tool, in less than 3 hours, we can go from fabricating a 3D printed component using directed energy deposition to a sub-micron finish, which is ready for characterization all in the same machine. So that's the finishing capabilities of this particular hybrid machine tool. And also, because of its unique construction, where we can finish the surface, and also we can summon the laser again, and we can see how we can use the heat input from the laser to actually soften the material. So we are all aware of heat treatment. Rather than heat treatment, as Dr. Mukhopadhyay mentioned, like this particular machine can be used to change the microstructure, as well as also the concept of laser assisted machining, where a very small laser is just used before cutting to soften the material so that we can prolong the tool life. So we can use this particular construction also allows us to use these thermodynamic pathways and use of the energy from this laser in situ heat treatment to manipulate the microstructures, as well as to lower the cutting forces to help prolong the tool life. So that is one more advantage of this hybrid machine tool. So I'm just building on this particular hybrid machine tool concept, and we'll build around a sensorized hybrid machine tool around this and see how it can be used for our characterization purposes. So the next concept is the sensor fusion. So in this particular machine tool, what we have done is we have sensorized this hybrid machine tool. We have a force sensor, we have an acoustic emission sensor, and an accelerometer, and all these can collect data simultaneously. And each of these sensors can go up to acquisition rates of up to 1 megahertz. That is like 1 mega samples per second. So, and also one very good thing about collecting all these data simultaneously is, as we see in the further parts of the slide, we have what is called spatiotemporal resolution, which will enable us to go back and look where the process has gone wrong. So in the further parts of the slide, when I'm discussing about the case studies, it will be evident as to how the spatiotemporal resolution and collecting data synchronously is actually helping us to go back and look at what actually happened in the process. So, and this particular example here, we are just showing the synchronous acquisition of this streaming data. So in the further slides, we'll also be looking at some milling data. So here you can see as soon as the machine tool has started moving, the laser head has started moving, we can observe a spike in the acoustic acceleration and forces. And because the printing process doesn't impart a lot of forces on the bed, we don't see a visible change in the forces, but definitely we are capturing some signatures which can be used further for analysis. And this video stream which you're seeing, that is also a sensor. This is a high-speed camera which can go until like 300,000 frames per second. this particular video is being captured at 1,000 frames per second. So we also use this particular high-speed camera along with some lens to just capture the infrared region of the spectrum, so that we can do some spatter tracking and actually see where these metal particles are flying off, and which actually has significant effect on the final quality of the part which we are printing. So now I've discussed with you about the capabilities of this hybrid machine tool and the advantages of sensorization and simultaneously collecting the data. So the first application which Dr. Bukapatnam mentioned, the manufacturing as a service. But the second application where we're talking about material on-demand manufacturing and tailoring the microstructures and tailoring the material properties as and when it's demanded. Like suppose so the concept is to synthesize material with all these tailored properties on demand. So what do we need for this? What do we need for tailoring these material properties on demand? So we have the smart hybrid platform, which I've mentioned, with all these data streams. And next, so consider this particular system, like the hands and legs of the body, like whatever movements which we make. And we have to map it to we should have a sensor fusion methodology and a PSPP, process structure and performance mapping. And through this, like consider this like the nervous system, which enables all these movements, the nervous system and the muscles which are enabling these movements. And on top of it, we need the brain, which is the on-demand material synthesis control brain, wherein if I suppose the brain gets an input as to like, I want these particular tailored material properties, we can go back, send the inputs to the machine. And again, using these sensor fusion and PSPP mapping can actually go back and give the exact parameters so that like we can tailor like whatever properties are required, we can input it to the machine and get the properties out. So we see that there is a forward mapping, which helps us understand this is the process understanding, and this is synthesizing the material, which is the reverse mapping, which is going back. So now the concept of autonomous materials discovery, we discuss this as a bottleneck and an opportunity. So right now we have data, we have many machine learning models which can be applied to the data. So, and as I've mentioned, like we have the capability of collecting data up to like 1 mega samples per second. And we also have models which can pre-process and post-process this data and give us inferences if we know the ground truth. And the next part is actually finding out the ground truth, which is the most difficult part in manufacturing experiments. So we have the experiments and we have the testing and instruments and etc., which can help us discern what the properties of the particular part which we have done the experiment on. And the critical part here is testing, analyzing, and characterization of these parts. So characterization is the major bottleneck, as discussed in this 2018 paper. So what happens is if we are looking at tailored microstructures, so if I go ahead and print a part, and if I need to know the material properties right then and there, like it gets difficult because the process itself, as I've mentioned, involves like multiple machines and shifting the path through multiple machines and getting the characterization done. So that is the bottleneck. But the opportunity where we see is like, can all these three, the testing, the experimentation, testing, and analysis and characterization, this particular cycle, can this happen simultaneously? So that's the question we would like to answer. So from the testing, analysis, characterization, and experiments, we can collect the data. But can this happen in a loop? Can we get the material properties at the point of where the experimentation is actually happening? And can we tailor it to our needs? So that is one opportunity which we see, and that is a very lucrative opportunity which the smart additive manufacturing and hybrid manufacturing platforms actually offer. So because the experimentation we see as fabrication, like printing the actual part, but the testing, analysis, and characterization, can we add some mods to this particular hybrid manufacturing machine tool and get this done within the machine itself. So that's the whole idea. So let's start. So to demonstrate this, let's start with a few case studies. Like this, this is the basic characterization route, the characterization using nano indentations and nanolithography. Why I started with this particular case study is this is the basic form. I wouldn't say basic form, the traditional form of characterizing a material. So I print a part, I kind of polish the surface, make it ready for characterization. I etch it, I find out the microstructures, then go take it to a nano indenter, make some nano indents at wherever I see or expect property differences, and see if that is what actually happened. So this is kind of giving me the ground truth as to what the actual hardness values are. But as I mentioned earlier, it takes multiple steps. So this particular sample is a Ti64 sample, and it has these different phases, alpha and beta. So alpha occupies around 90% of the phase of this Ti64 matrix, and beta phase around like 10%. And what we wanted to see was this is a nano indentation setup, and the premise is this: we use the nano indenter and make a nano scratch on the surface. And there are, if you see this, this is again instrumented like our smart hybrid machine tool which we saw. So there is an accelerometer near the indenter, and there is an acoustic emission sensor which is put right on top of the Ti64 sample. And this is the nanolithography head, which approaches the material and kind of makes a very tiny nano scratch on the surface. And we are still capturing the data at 1 megasamples per second. And these two are the different signals which you see. This is the standard microstructure. This is the signal when we are scratching the standard microstructure. And this is the signal when we are scratching a diffused microstructure. In the next slide, I'll show like how these two different microstructures look. So this is the standard microstructure where we have the different compositions of alpha and beta. And this is kind of an effect of the polishing, which we have like the effect of a diffused microstructure, more like you can see these beta phases placed more like flat sheets or planes. So we have made 5 scratches here on this standard microstructure and 5 scratches on these diffused microstructure. And we have collected the data from both these scratches, both these nano scratches. And we are seeing if we can characterize or we can classify these two, because these two stand apart in terms of the signal features which we are looking at, as we'll be looking in the further slides. So we are trying to train a machine learning model and see if these two actually stand apart. And by just doing this experiment, if we can discern the properties of the microstructure. So these are the signals from from the standard and diffused microstructure. And what we did is we just took a fast Fourier transform. We just took an FFT of this particular signal, and we have divided the whole FFT into like multiple bands. So we say like the bin size is around 20 hertz, and we find the total energy of this particular frequency spectra in the 20 hertz. So if the concept of binning is new, like I'll be discussing that in detail in the second case study, where I have done some where we discuss rapid characterization. So for now, just take that we have divided the frequency spectrum into 20 hertz bins, and we have used those as features. So now I know the ground truth because I've used a nano indenter already. So the ground truth is I know that this is a diffused microstructure and this is the standard microstructure. And we have a set of, we have a feature set, which is emerging from this particular signal. And we use the features to train a random forest classifier, a basic random forest classifier. And if we extract the important features, so random forest classifier has this really interesting way of defining what features have contributed best to classify these two microstructures apart, or these two classes apart the best. So when we looked at the most important features which are actually helping us to identify these two microstructures, the first one is the 0.3 to 1 kilohertz, and the next one is 30 to 50 kilohertz. And this particular plot shows the value of importance versus all these different samples where the scratching has happened. And we can clearly see that with the naked eye, we can just clearly see that we can clearly draw a line and say that, anything falling above this particular area belongs to standard microstructure, and anything here is the diffused microstructure. So here, this particular, the diffused 5 is actually somewhere really close to a scratch, which is already on the surface. So we also see that not just from the microstructure, we also get from feedback from the lithography process itself, or how the surface is. So this particular thing is the diffused microstructure, which is kind of closer towards the standard microstructure, but that is what we get from experiments. So this particular process, again, let's ask the question, like, can it be faster? By faster, what I mean is, again, as I said, this is a traditional way of characterization and a traditional way of finding out the properties of the particular material, like the nano hardness values. But can it be faster, and how can it be faster? So that's where our experiments and where we are using this particular hybrid machine tool comes in. So this is the hybrid machine tool, and the concept is simple. So we brought this particular part, which has been fabricated in the machine itself, to a submicron finish. And what we do is, in a nanolithography experiment, we have a static tool which has scratched the surface, and we could see that we could find discernible features which can say if it is microstructure 1 or microstructure 2. So what we are doing here is, we have a dynamic tool. This particular tool here is a micromilling tool. It has, the diameter of the tool is around 200 micrometers. We perform a similar scratch experiment, but right now the milling tool is rotating. And we collect the data from this particular milling experiment with all these different sensors. So what you can see here is an acoustic emission tool. And here there are some thin film sensors. And under this particular bed, there are accelerometers and force sensors. And we are collecting all this data simultaneously. So whenever we are capturing these particular signals, when these cutting operation is happening, so what we want to see is, can we do a very similar analysis, get the frequency components out of the signals which we collected, and see and do a very similar analysis, extract features, and use the features to say predict my hardness, and see if that makes sense. See if we can actually predict hardness from these signals. So that's the basic idea. So right now, like immediately, if we look at this particular process, we find that it is rapid characterization. I didn't even remove this particular sample from my machine. So it has been printed here, and I'm milling it right here. I'm collecting the signals right here, and I'm trying to see if I can get anything from these signals. So that's the basic idea. So the samples which were printed here are high entropy alloys, cobalt, chromium, iron, and nickel. And these were finished initially using a 3/8 inch milling tool. And then we have a phase grinding tool within the machine itself, and a cloth polisher, which we use to finish the samples. So the samples which you see here, all these samples were finished on this particular machine tool itself. And then we have done this micromilling scratches, where we collect all these 3 sources of data. And so these are the material compositions, different elemental compositions, and we have like 8 different alloys. And for the current analysis, we just look at these 2 particular material systems, where if we just look at it, we can see a major difference in cobalt compositions and nickel compositions. 196C2 has like very low cobalt and very high nickel, and 196C3 has very high cobalt and very low nickel. So we took these 2 samples as our test samples, and the idea is, can we identify which sample is which just from data? So this is the case study. So this particular sample is 196C2, and this is a stitched SEM image. So what these orange lines are is the feed rate of my particular milling tool. So whenever I'm cutting this particular sample, the tool advances by 100 micrometers, and the spindle speed is kept at 2000 RPM, and the feed rate is around 48 inch per minute. So we calculate this first, and then we arrive at this, like around 130 micrometers per flute is how it's cutting, and we cut a depth of around 5 micrometers, and during these cutting operations, we collect all these 5 sensor data: accelerometer at 10 kilohertz, acoustic at 100 kilohertz, and we have a thin film strain sensor at 10 kilohertz. We have a high-speed camera which is running constantly at 250 frames per second, and a force sensor which is collecting data at 100 hertz. And the case study is like we use data collected from the sample preparation and micromilling steps, and we want to train a model right now. So we want to know how the hardness values are changing across space. So we want to learn the spatial variation of material properties. That is what we are learning. And what we want to learn it from is the spatiotemporal sensor data. Again, by spatiotemporal sensor data, yeah, I'll be discussing in the next slide what spatiotemporal and how we can get that particular resolution from the experiments which we are doing. And why true is obtained from standard characterization procedures. Again, we need the ground truth at least for training this model. So for this particular experiment, we took the ground truth from micro hardness measurements. So again, as I said earlier, what is spatial and time resolution? So we look at this particular sample. Again, it was milled in these particular passes. So if we look at all these passes here, so each and every pass corresponds to a burst of signal here from acoustic emission. All these are acoustic emission signal. And if we look at this particular pass here, so just this one. So this particular pass is this particular signal. So this particular burst of signal is coming from this particular cut. So we completely identify where the cut has started and where the cut has ended. And we can go back and say, if I'm looking at this particular band, this is the signal where it's coming from. And this small square, which we are looking at, so this whole signal is from this end to this end. And this particular small section of data is exactly where this highlighted portion is. So what I'm trying to say here is we have spatial resolution. If I give a particular XY point, I can go back and exactly see where it corresponds to in the signal. I have spatial resolution where spatial resolution of 100 microns. So if you give me a point here and you say 100 microns from here, I want where the signal is, I can exactly show you which burst corresponds to that particular signal. And with respect to time, I also have the time series and I exactly know where the tool is on this particular path. So I have the spatial and time resolution with this synchronous data collection, which is happening. So that is important because when I look at my hardness measurement values, I again need to correlate this back to the hardness measurement values. And Dr. Kumar, if I'm getting, yes.
Yeah, I have a question in this slide. Can I ask?
Yes. Yeah, sure, go ahead.
Dr. Ravi Shankar. So whatever the highlighted area about red, there is no, I feel there is no cut there. Can you look into it? Because there is, the cut is there in the central portion because you have highlighted there. So the sensor signal normally whenever the milling cutter will be, see, you are emphasizing about only one milling cutting and which is at the central portion highlighted. So, but the highlighted portion of the red color, there is no cut. So, yeah.
You're saying this part, there is no cut?
Yeah, cut is there. There is no cut.
Yes,
because,
so.
Yeah, the cut is there at the center.
No. Exact. Yeah, I'm sorry. Again, these particular samples.
So the signal, as I guess, the signal acoustic emission signal refers to each and every cutting edge interaction with respect to that when you are making this particular scratch. So my guess would be that you should have drawn the line horizontal, not the vertical. So particular segment are, yeah. So that's, I guess that's just
yeah, I can give you the I can give you the clarification. So the thing here is we have also collected the data from sample preparation, and this particular acoustic emission signal which we are looking here is from the macro milling sample. So this is from the 3/8. Oh, I'm really sorry. Okay.
Yeah, fine. Just I would like to say that, yeah.
Yeah, these particular data sets are from the 3/8-inch 6-flute carbide cutters and not from the actual micromilling samples. So the spatiotemporal resolution which I'm showing you here is the milling cut, the initial milling cut, which is actually happening with the 3/8-inch milling cutter throughout the whole sample. This particular case study, we still haven't looked at these micromill samples.
Yeah.
But right now, this particular data set refers to the 3/8-inch, where I'm finishing off the sample right after I establish a datum with my cutter. I use a very minor 5 micrometer depth, and I just finish the sample using the milling cutter itself. And so all these particular lines here, they refer to the the feed of the macro milling cuts. So we are not referring to the micro mills yet. Did I answer your question?
Yeah. The second I would like to say, so whenever you do your FFT analyzer, so you are changing from time domain to frequency domain. Yeah.
Yes.
So you're talking about surface finish. So can you comment about that? The FFTs, the value of it will move towards left side or right side of as the surface roughness improves, your FFT signals. This is the burst signal of acoustic emission. What my question is that if this, assume that you are doing a machining with 5 microns depth of cut and 2 microns depth of cut, like so. If you decrease, automatically the surface roughness will go down, obviously. So now you take a burst signal for acoustic emission and which you convert into FFT analyzer. So in that circumstances, what will be your signal, whether it will move towards datum, or I mean to say left side or higher side or lower side?
Great questions, actually. Let me quickly answer. Bhaskar, I think I would like you to think through that too. First question is, how will it behave when you have very high finish on your surfaces? It would not go left or right, but the energy will actually come down. In fact, acoustic emission perhaps is the only one kind of a sensor that has the sensitivity to actually indicate some changes in the micro machining regime in those fine finish cut ranges, actually. If you look at the vibration data as well as force data, they probably will be just, will be submerged within the noise bands. But acoustic emission, luckily, will be able to capture. But as you correctly said, the energy levels will be so low that you need some advanced processing to extract useful information out of acoustic emission. And also, to your earlier question, if you look at some of these central bands on the picture that you're seeing, what you're seeing are actually bursts that were coming out of the surface. So, so it actually looks like that because you are seeing the bursts and not the surface.
Yeah.
Anyway, I hope I answered some of your questions on acoustic imaging.
Yes, sir. However, it is a fantastic, interesting work, though. So that's why we got a lot of doubts. Yeah.
Oh, absolutely. Thanks for your question.
Yeah, thank you, sir. Thank you. Yeah, please, Bhaskar.
Yeah.
Thanks.
Thank you, Dr. Shankar. Also, I would just like to clarify one single thing. So here we are looking, whenever we are doing the cuts, we are looking at samples which are less than 100 we are looking at in the orders of tens of microns of surface finish. And again, the output which we are looking at is again not surface finish low. I kind of didn't mention it in the starting of my slides. So what we are looking at is whenever we are looking at these signals, if we can associate it to the hardness of the material. So again, really interesting questions, Dr. Shankar, like with respect to like how the FFT response would change. I would definitely look back into it and see how the response would change. And also one thing I would like to add, as Dr. Mukhopadhyay said, the energy levels would definitely decrease for all the sensors, but in terms of the shift, it is not just the process, but also the process and machine interactions which we get from these particular. I'm sorry.
Continue.
Did someone have a question? Okay. Yeah, the next part we would be discussing the feature extraction routine from the sensor signals which we have obtained from these passes. So now we have this particular milling pass where we got this data from, and we convert it into the FFT transform, and we get these frequencies. What the next step which we would do to extract our features? So we need a set of X's. We need the feature vector developed to actually predict something. So here we slice this entire FFT into frequency bands of width of around 500 Hertz. So what we do is we slice the entire FFT spectrum, and we add up all the energies in this particular bands. And whatever the cumulative energy in this particular band is, corresponds to this particular step here. So this is the cumulative energy which I have over my around 100 bands of frequencies. And this is my feature vector. I use this particular data as my feature, as my input vector X, and I want to classify which sample it came from. So right now we have 208 milling passes, which came from just these two samples. The first sample 196C2 and 196C3. And the dimensions of the input space, again, because we have 100 frequency bands and we have 208 samples, and the output is just binary. We want to predict if it is C2 or C3, that's it. And we have trained this particular data set with 3 different models. The first one is a basic logistic regression, and we have used a linear basis support vector machine, and we have also used a random forest classifier. In all these classifiers, we almost got a very high classification accuracy, and there's a reason for that, which we'll be looking in the next slide. And also, one more thing is we look at the variable importance, very similar to what we have looked in the nanolithography experiments. So looking at these variable importance plots, and again, going back to the process and understanding why these particular frequencies have played a major role in when classifying these 2 particular parts, that is still yet to be studied, and we are working on it. And to the part where why we got such like high classification accuracies. So wherever we did all these macro milling experiments, we also took some micro hardness measurements. So the micro mill here, which we did, served as a good identifier as to where we need to do these micro hardness measurements. And so whenever we did this, so this is a particular milling pass. And along the milling pass, I know where the band of this particular pass is, and because I know my feed rate, and I also know in which direction the mill is progressing. So I have all these different hardness measurement values which I've done, and this is the ground
Hello,
truth.
Japan. Okay, yeah, not sir. మీరు టిల్డెడ్ వర్క్ అడితే ఇక్కడ 28 చెప్పారా మీరు ఇప్పుడు నేను జాయిన్ అయ్యాను
Dr. Ajay, can you mute all the people? Yeah, I think Dr. Bhaskar, you can continue, please. Sorry for the disturbance.
Okay,
Yeah,
no problem. So if we look at these again, if we look at these 2 samples, 196C2 and 196C3, so whenever we took these micro hardness measurements values, we saw that there is a considerable shift in hardness values for 196C3 with higher nickel content and much lower hardness for values where we have lower nickel content. And because of this discernible difference just from the hardness measurement values, we could kind of identify that, like, because a harder material when cut obviously emits higher vibrations, higher higher emissions in terms of acoustics. So whenever we have such proper proper difference in terms of hardness values for 196C2 and 196C3, we could identify that whenever we extract the features, the energy values would be very different, and we could get a really good classification accuracy. So the next step would be, now we can classify what sample it is just from looking at the sensor signals. But the next step is, can I actually predict my hardness values? So now I have the signals from all these which correspond to these particular hardness value measurements. And that's what we did next. So we broke the signal down into segments. We know what segment corresponds to what hardness value. And now we again did a very similar analysis. We built the random forest model and checked what we looked at the features, and now the feature set corresponds to a particular, this is a regression. So previously we saw a random forest classifier. Now we are looking at a regression model where I want to predict my hardness values. So the test accuracy of this particular model where I predict my hardness values was around 96.43. Again, this stems from the fact that the hardness values for these two particular materials are way off. And we can clearly see that from the signals which we obtain. And that is for material property correlation. So now so at the end of this case study, what we see is, using this smart sensorized hybrid machine tool, what we can do is, whatever we have achieved in nanolithography, we haven't achieved it completely with this particular milling experiment or the rapid characterization experiment yet. We still have a lot of things to establish for us to say for a fact that we can actually characterize the materials in a rapid fashion. But this is a starting step where we are seeing that from the sensor signals, we could see that we could estimate the hardness values, and we can say that there is some discernible changes. So we still have a long way to go in terms of rapid characterization. So my next case study would be in terms of process monitoring using streaming image data. So until now, we have captured images, but we didn't actually look at the image data from these particular experiments. But what we are trying to explain here is the defect concentration in this. And so these are images from the Ti64 sample itself. And what we want to identify here is the Bolling defects, which we are seeing here, which are gas-induced porosity. So which, in these particular samples, we see that, suppose if we are looking this from a pure image standpoint, it is kind of difficult to exactly identify these anomalies. And we also want to track these anomalies in situ, like if you have some form of an imaging. So we want to kind of identify what's the porosity of these samples just from the images. So here we have these two conditions where the laser power has a very stark difference, and you want to identify these particular defects. These particular defects for identification, the problem gets particularly difficult because of the uncertainties in the location where these defects are present, and morphology. And also, whenever we are looking at these images, it is evident that there is a lot of noise and exposure differences at different points of this image. So, and again, if we are trying to build a model where we have these particular images and we want to correlate it to the porosity, so what we need is a lot of experiments. And unfortunately, we can't really afford that, because like each and every experiment here is involves a lot of cost. And if we are going for supervised methods, the supervised methods are like actually infeasible because of the huge experimental costs which are involved. And we kind of need to find an efficient means to segment out all these anomalies. So this is work done by one of my outgoing seniors, which he has used a graph cuts based method where for any configuration, they determine the graph structure that minimizes the error in the measure of fit and the measure of smoothness. So by this, yeah, this is a segmentation algorithm. Like by using these, he came up with a comparison criteria for different unsupervised methods and supervised methods. So this particular score is a DICE score, so these are images from brain scans, and these are the areas which are to be identified in a patient with a particular ailment. So this is the expert segmentation which is there, and this is the estimated segmentation which comes from unsupervised learning models. And if we look at this particular DICE score, which gives the accuracy of the fit, so we see that this particular model which he has built, this is unsupervised, and we don't need any training samples for this particular method to work. So this unsupervised method performs like much better than most of these supervised models. And the current state of the art unsupervised methods have a DICE score of around 0.3. And right now we are reporting somewhere around like 0.75. So this very example, when applied to the examples which we have shown before. So these are the different defect segmentation results. We can see with all the other models from A to E that it has identified different areas of this as defect. This problem gets really difficult because of the differences in exposures at different parts of the image. It is just not black and white, and we can't use a basic thresholding technique to identify where the defects have occurred. And this is the particular method which we have developed, the unsupervised max flow, which shows an estimated this score of 70.56. So what we are showing here is a label-free, fast detection and tracking of defects without performing any additional data. And we don't actually need data sets to perform this particular defect segmentation. So let me summarize. We have discussed like 3 case studies, and Dr. Bookpatnam gave a very high-level introduction of the 2 concepts of smart manufacturing, which we are actually targeting. We are using a smart, sensorized, hybrid manufacturing machine tool, and in conjunction with different AI techniques. So this whole setup is an enabler for different things. First thing is the concept of manufacturing as a service, the concept of materials on-demand manufacturing, where I not only get what part to manufacture, but also the part comes with particular specifications as to the properties which are required in the particular part. So we discussed how the materials on-demand manufacturing can be enabled using this particular machine tool. And we have discussed cases of rapid characterization of alloy systems in conjunction with AI and this particular machine tool, and autonomous material synthesis and discovery. So we are not at the discovery part yet, but we have looked at the synthesis part as to if we know the elemental compositions, and we can go to the hardness. Like if I want a particular hardness, can I come back and say like what are the different elemental compositions which are required? And finally, we have discussed a case study of the in situ process monitoring, where we have the final images from the parts which are ready for which are done characterizing, and if we can do some process monitoring from the results of what we get finally. So the central part is the hybrid manufacturing machine tool which we have here, and we are kind of using that to see if we can move forward and inch forward towards the autonomous material synthesis and discovery research. And that's my talk. Thank you. And if you have any questions, I'll be happy to take them. Thank you.
Yeah, thank you so much. Thank you so much, Professor Satish and Dr. Bhaskar. Now talk is open for any question. I request from the audience, if they have any specific question, they can directly ask to the speakers.
Yes.
Any question from the audience? Yeah, I think if there is no more question, let us thank Professor Satish and Dr. Bhaskar for the wonderful talk. It was really a wonderful, you have covered the smart hybrid manufacturing rapid characterization, and you have presented the case studies which are very useful for the our students and who are doing research in this area. Thank you so much. Thank you so much, Professor Satish and Dr. Bhaskar.
Thank you so much.
Thanks for the opportunity, Dr. Kumar. Thank you.
Again, thank you so much, and it was so nice to meet some of my old friends. Again, I know the next talk is coming up very soon. Look forward to the talk. And,
thank you so much. And we will have our interaction later on. We will have Thank you so much.
You. Bye.
So now we have next talk by Professor Pradeep Manges from University of Nevada, Reno. Professor Pradeep, are you there?
Yes.
Yeah.
Can you hear me?
Yeah. Nice to see you. Good evening. So let me introduce Professor Pradeep Manges. I have a long-term association with him. So Professor Pradeep Manges is the assistant professor in the mechanical engineering department at the University of Nevada, Reno, USA. Before joining UNR, he worked as an adjunct assistant professor at the University of Wisconsin-Milwaukee, USA, and research assistant professor at University of Pittsburgh. His research areas are tribology and surface engineering, additive manufacturing, metal forming, metal cutting, metal testing, and characterization. His productive research career has produced over 85 peer-reviewed journal publications, more than 3,000 citations, and 28 H-index. He has published 27 book chapters and 3 books on tribology and other materials. He currently serves as a reviewer on over 50 prestigious journals and as an editorial board member for 5 international journals. He has also prepared technical newsletters and tribology web notes for American Society of Mechanical Engineers Tribology. So I welcome Professor Pradeep Manges. So Professor Pradeep Manges, over to you. Thank you so much.
Thank you, Dr. Ajay. Can you hear me?
Yeah, I can hear you.
Yes, as Ajay mentioned, I basically work on in the areas of tribology and manufacturing. So let us move where I am located at this moment. I belong to University of Nevada, Reno. This is the place where I can live. It is just a boundary between California and Nevada. As all of you know, that where is Las Vegas is located. So it is pretty close to, it is not to Las Vegas, but it's very close to Sacramento, just 2 hours drive from here. So Reno is my city here. It is known as the biggest little city in the world. Okay, and it is very close to the Lake Tahoe area. You can see this area. This Lake Tahoe is covered by mountains. So this is a ski place. It is many people from all over the world. They come here for skiing, and it is also a casino place. This is a tourist place. People come here to play and win some money. Okay. So now coming to my university, University of Nevada, Reno. This is the campus for University of Nevada, Reno. This is basically the Students Activity Center. This is the library, and this is the gym. And this is our soccer ground. And this is our mechanical engineering building standalone. And just 2 years before it was renovated, or we spent like $15 million. These are my students. Arpit is already graduated. He got job in ASML in Connecticut, and Ashish He is graduating this year. Okay, and at this moment I have 6 PhD students and 5 undergraduate researchers. Coming to, if you want to see any of my research areas, please visit my website. These are some of the areas. Already Dr. Ajay indicated that I work on tribology and tribocorrosion, surface engineering, additive manufacturing, multi-phase lubrication, self-lubricating composites, and using both experiments and finite element modeling. Today I will be discussing more on surface texturing and multi-phase lubricants. So these are some of the facilities we have in my lab. We have universal tribometer that is used to measure the friction, wear, and the lubrication properties. It is connected with the optical profilometer. We have a potentiostat which can connect to the tribometer. We can study both the tribology and corrosion together. We have several 3D printers. We have cryomilling ball mills to ground powders. We have friction stir welding machine, contact angle goniometers to study the surface properties, coating units to deposit coatings. We have also chemical vapor deposition unit, high temperature furnaces, DSC TGA for characterization, and laser units for surface processing, welding, and sintering process. So today, our presentation outline will be like this. I will talk a little bit about tribology. I don't know how many people know about tribology. I teach this course once in a year at the University of Nevada, Reno. We have like more than 50 students enrolled for this course. And today's my topic, I focus more on tribology of surface engineering and tribology of lubricants, including liquid lubricants, solid lubricants, multi-phase lubricants, then the combination of how the surface texturing and multi-phase lubrication synergism will help to reduce the friction and wear. So as you know that tribology is the science that deals with the friction, wear, and lubrication. Basically, two surfaces come into contact. There is a load and there is a sliding motion. So basically, it's a very simple contact conditions. If you analyze, it is easy to understand. So tribology will integrate multiple scientific and engineering disciplines to increase the probability of a whole system success. So you can see this in science, you can see this in engineering, dentistry, and medicine. As you know that we walk today because of friction, right? We drive because of friction. Okay, so all these things are very important in our daily to-day life. And tribology is not like reducing friction. Okay, so tribology means the designing friction. Okay, friction. For example, sometimes you need a low friction and a low wear. Okay, for example, in case of bearings, you need very low friction and very low wear. In case of brakes, you need high friction, right, and very low wear. Otherwise, your brake will wear away very quickly. And when you write chalk on a board, we need low friction and high wear, and in some machining process you need high friction and high wear. So as you know that when friction is there, there is energy loss. So when wear is there, then material loss can come into picture. Okay, you lose materials. And lubrication, most of the metal forming processes or machining processes, they use lubricant as a coolant that will damage to the environment. Most of the lubricants today we use, which is petroleum based lubricant, that will go to the environment and damage to the environment. So these things are very important when you talk about efficiency, energy efficiency, material conservation, and sustainability of this process. So back in 2003 to 2008, I was doing my PhD at the Indian Institute of Science under supervision of Professor Satish Kailas. So he introduced me the tribology field, and today I'm standing with this field. So basically my PhD was on surface texturing. So you can see that how the surface texturing will be there. Interestingly, you know, you can have different surface texture, right? This is kind of unidirectional surface texture, and this surface texture is kind of random. You can see that both surface texture can have the same RA value. We are talking about here roughness, Okay, roughness means there are many things. Most of the industry people, they are talking about only RA, but actually there are many other things are involved, because there are two surfaces can have the same RA, but their frictional characteristics could be different. And you know that surfaces are not smooth. It has some kind of roughness, and this roughness we call it as peaks and valleys, just like asperities. So, and surfaces, they contain different layers, like a physisorbed layer, chemisorbed layer, chemically reacted layer. They play a major role during tribological contact conditions and during sliding motion, and that will influence our friction and wear properties. As I told you, surface roughness means there are many things come into picture. Basically, if you see the literature, many people are focused only on RA value, but there are many things, because RA is talking about only the amplitude variations, only height variations, but it doesn't talk about spatial or spatial variations. So many hybrid parameters also developed. When I was in IISc Bangalore, we developed several roughness parameters, and we correlated how these roughness parameters will influence friction. For example, the slope of the asperity is one of the parameters that play a crucial role than the RA value. So there are many methods to measure the surface roughness, 2D surface roughness using stylus contact type profilometer. When you go to nano level, we use AFM. Generally for micro scale, we use optical profilometer. So you can see that again, these three surfaces, this surface is produced using sandpaper or emery paper, we say, like 600 grit, and this is same paper, but it is a random. But you can see that the surface roughness is same. And when you do like a silicon carbide wet polishing process, you can achieve the same surface roughness. So these surface roughness looks same, like RA is 0.24. But if you conduct experiments to study the friction and wear, the friction and wear properties are totally different. You can see that UPD surface texture means here the sliding is conducted perpendicular to the unidirectional grinding marks. 8 ground is the these surfaces. UPL means it is parallel to the sliding direction, and this is the random surfaces. You can see that how the friction changes with the texture. This is very important when we're talking about surface roughness. Just surface, considering surface roughness is not important. You always know what is the type of surfaces you use. So based on this, we have discussed a little bit on different components of friction, the mechanism involved behind these changes in friction. As you know that friction has two components from the classical theory of friction, that which has like addition component and plowing component. And when you add lubricant at the interface, basically the addition component comes down, and basically under lubricated condition, what you see basically the plowing component of friction. So in this picture, you can see that the plowing component varies with the surface texture, but the addition component is almost remains constant. This is the case of aluminum 4 magnesium alloy. But when you change to material like lead, which is much softer than aluminum magnesium alloy, the effect of surface roughness and texture will be more influencing compared to the harder material like aluminum magnesium alloy. And we have developed several non-dimensional roughness parameters which can correlate well with friction. For example, if you see here for a different surface texture, you can have the same RA value, but the friction will be different for different surface textures. But if you plot in terms of surface texture, you can see that the same range of surface roughness, how the friction changes with surface textures. And accordingly, we have studied the transfer layer formation, how the wear process influence due to surface texture. And you can see that when sliding perpendicular to the unidirectional grinding marks, you get more wear friction as well as wear. But when the surfaces turning to random surfaces, you get less wear or transfer layer formation. Under lubricated condition, the amount of transfer layer on the flat surfaces will be much lower. So this is what we studied when I was doing my PhD. This is because when the surfaces are unidirectional, the material has to flow over the asperities. When they are random, it has to flow around the asperities. We have done some kind of simulations to study the how the stresses will generate when the pin materials moving over the asperities and moving around the asperities. We see that the stresses will be much higher for unidirectional perpendicular surfaces and which less for the random surfaces. We have also done some kind of compression test to study the effect of surface texture on friction. You can see that the flow will be more constrained when the friction is higher at the interface, and it is less constrained when the flow is the material flow is less constrained when the friction is lower. So we have also done some kind of to validate this hypothesis. We also conducted some kind of experiments, condition tests, and you can see that for unidirectional texture, we generated some kind of unidirectional ring kind of texture on the so that the material flow can be constrained. And this is more on polished surfaces. You can see the difference in microstructure and how it influenced the frictional behavior. There are many roughness parameters available in the literature. You can see that, and we found that the del A, which is the slope of the asperities, play a crucial role than the surface roughness. So previous plot I showed that the surface roughness remains more or less constant in the range of surface roughness what we studied, but here the surface roughness del A value, which is provide a correlation of like 0.94, and that is the best roughness parameter for our case. But you know, when the material process will change, for example, you do your own new technique to produce surface textures, this roughness parameter may not be valid. Okay, so depending on the conditions, the surface, you have to choose the surface roughness. So, and again, when we studied the material, two materials like aluminum against steel or steel against aluminum, it is very important which you have to choose as a pin material, which you have to choose as a flat material. For example, in this case, this is the case of aluminum magnesium alloy pin against steel flat. You can see how the surfaces, same conditions, only the pin is magnesium, aluminum magnesium here, steel flat, but here it is a steel ball against aluminum magnesium flat, just a reverse case. So you can see that variation in friction. So it is very important what type of material pair you choose during your studies. We have also done some kind of angular texture. We moved parallel to the sliding grinding marks. We moved perpendicular. We moved a different grinding angle. You can see that when you change the grinding angle, how the friction changes, and basically this is dominated by the ploughing component of friction. So we have also did some kind of subsurface microstructural analysis to study what happens. So in this, this is the pin, aluminum magnesium alloy pin. After sliding test, we did some kind of cross section, and we have traced these lines, the deformation lines. And schematically, you can see that when the sliding is perpendicular to the unidirectional grinding marks, where the friction is high, you can see the flow lines are much bent parallel to the surfaces. Okay, and from this kind of traced lines using some kind of models, you can basically predict the equivalent strain, and from this you can predict how much deformation is taking place below the surfaces and why the wire particles are more or larger amount when sliding perpendicular to this direction compared to the random surfaces. Random surface, the flow lines will be less, and here it is much more, and the depth of deformation will be much higher. So that is the history when I was doing my PhD. So now coming to University of Nevada, what I'm doing research. Here basically I use laser equipment to process the surfaces. Okay, one of the research my student was working on laser shock peening on friction. Okay, here we have taken the steel material, we study the surface roughness, we keep the initial surface roughness same so that it will not affect during laser process. So we give the laser shock peening process. As you know that when you do laser shock peening, there's an interaction between laser matter interaction, and the surface strengthening will increase. Okay, so it will produce some kind of compressive residual stresses and work hardened layer, because the strain rate will be of 10 power 5. So that is the reason the surface hardness also increases. So we used here Nd:YAG laser, which is wavelength of 1064 nanometer, pulse duration of 5 nanoseconds, laser beam diameter of 1.5 millimeter, and we kept initial surface roughness of 0.1, so that the initial surface roughness should not affect the friction values. So we have done some scratch test and some standard tribological conditions we used. You can see that it is 24 degrees Celsius, room temperature test, 50 Newton loads, 10 millimeter sliding distance, and 2 millimeter per second sliding speed. Interestingly, you can see that as the laser intensity increases, the friction decreases, and after a certain laser intensity, the friction again increases. And the transfer layer or wear process also, it follows the same trend. After a critical laser intensity, the friction and transfer layer increases. We would able to find out the reason, because as you increase the laser intensity, the surface strength increases, the hardness also increases. You can see in this plot the micro hardness values, the surface hardness continuously increases. But you can see that the friction decrease and then increase. What could be the reason? So we have done some profilometer studies to see what happens at the interface. We found that when you at low laser intensity, the surface are original surfaces, it can like squash the asperities, and it will become very close to the mean line. And after the critical surface roughness value, the sharp asperity will regenerate. So that is the reason the friction increases after a critical laser intensity. This is published in 2018. Then we wanted to study the effect of laser shock peening on microstructure. Here we choose the magnesium alloy, which is, as you know, that magnesium is lightweight, and several applications we use today because of lightweight nature, and there are many advantages. So we use laser intensity, a particular laser intensity, and we see that we observed a gradient twin microstructure. Okay, so this is the top surfaces, and when you go below the depth, you can see that here more or less several twins are there, and when you go to the around like 350 micrometer, there is no twins. So we have calculated the twin volume fraction. We found that the twin volume fraction is highest at the surfaces, and it decreases with the depth. Then we studied the tribological test. This is at the after removing the chopping the material at around 350 micrometer. So you can see that there is no twins, so the friction will be much higher. When the twins are present, the friction decreases. And we plotted this graph, the variation of friction versus twin volume fraction. You can see that as the twin volume fraction increases, the friction decreases. So microstructural aspects are very important when considering the friction. Similarly, the wear process, you can see that when the twin volume fraction is 0, you can see the maximum depth. That means more wear. So for highest twin volume fraction, you get less depth, low wear. So this is an interesting result, and we also studied the wear rate with the different applied load. You can see that for twin volume fraction of 0, you can always get higher wear with respect to load, but when there is a twins are present, the friction as well as wear decreases. Also, we conducted some micro hardness test. You can see that when the twin volume fraction increases, the hardness also increases. So this is an interesting result, as you know that hardness is always related to friction and wear properties. Another interesting results I have not put here the microstructure is that this is the case before laser treatment, and when you do some kind of laser treatment, you get some kind of twins, right? So when you do some kind of testing, interestingly, the sliding also produces twins. So there are two kinds of twins you can observe. One is these twins are just because of sliding. There is no twins initially. So when you do some sliding test, you get the twins. This is laser treated surfaces, and again when you do some kind of sliding, you get the twins. This is an interesting result how the tribological will play important role during sliding conditions. And another interesting result we obtained is we have taken the rolled magnesium sheet, and we have done sliding test in different directions. We want to study the anisotropy friction of this rolled magnesium material. You can see that this is a rolling direction, this is transverse direction, and this is the normal direction. All these directions, you can see that the friction is different for all these three directions. Rolling direction is different, transverse direction is different, normal direction is different. This is another interesting result we obtained, so that when you're choosing a material, and the direction is also play important role, because friction is anisotropic here. So similarly, the wear properties also we found similar to friction, the wear also follows the same trend. So from this you can conclude that magnesium alloy exhibit prominent orientation dependent friction and wear properties. That means anisotropic nature. So another interesting study we are working on surface texturing. Okay, surface texturing using laser. So again, here also we did some kind of patterns, and we wanted to study the different laser intensity. The previous study was done for a single laser intensity, but here we just wanted to see how the laser intensity influence this friction, where the material processing parameters and mechanical properties. So you can see that again here, normal direction and rolling direction. So rolling direction didn't have much effect with the laser intensity, but normal direction had a substantial influence on friction and wear properties, and the hardness also. So this is the hardness plot, and this is the friction plot. So moving from surface texturing to now lubricants. So currently my research focus is on bio-based lubricant. More specifically, we synthesize ionic liquid. So ionic liquid found very interesting lubricant nowadays, because you can tailor it, because it has a laminar crystal structure similar to solid lubricants. You can derive like bio-based green lubricants. It has a low vapor pressure and non-flammability, highly polar, and high thermal stability. For this reason, I started working on imizonium and posponium based ionic liquid lubricants. And ionic liquid today we have several applications, not only as a lubricant, heat transfer fluid in battery. So various various things we apply this ionic liquids. So we have done a lot of studies on ionic liquid. We synthesized ionic liquid in the lab, and interestingly, we found that the molecular structure of the ionic liquid influence friction and wear properties. So longer the chain length, lower the friction values. This is for the case of imizolium, and this is for the case of posponium ionic liquid. And from this, you can see that the longer the chain length, lower the friction values. We have compared this with the other liquids, some like petroleum-based lubricants, natural oils. You can see that saccharinite-based, posponium-based ionic liquids showed lowest friction and wear properties. And there are other environmentally friendly lubricants exist that are slightly higher friction and wear properties compared to natural oils or some kind of synthetic lubricants. So these are very important aspects of ionic liquid. Ionic liquid gives much lower friction and lower wear compared to natural oils or petroleum-based lubricants. Moreover, we can put this ionic liquid into natural oils or other lubricants, and you can control the friction. Suppose if you want to low friction, you can choose only ionic liquid, but ionic liquid is expensive at this moment because we are producing in very small quantities. If you try to produce in very large quantities, then definitely the price will come down. And you can see that here, when you add this ionic liquid to the natural oils, the friction is slightly increases. If you take only 0% ionic liquid or only natural oil here, the friction is high. So if you add ionic liquid as additives, you can control the friction, or you can tailor the friction values. This is the case of friction results, wear results of both imizonium and posponium-based ionic liquid. So coming to the solid lubricants, as you know that nowadays many research is going on adding solid lubricant as additive to the oils, because it will perform much higher than only the base oil. So basically the HPN and boric acid, they are considered as more environmentally friendly additives because they have a layered crystal structure, so easy to shear. It produces lower friction. So I know that most of you play carom or played. We use boric acid powder there, so it is easy to shear, so friction will be less. So this is the structure of the boric acid. This is the for hexagonal boron nitride. You can see that they are layered structures, so easy to shear, so lower friction can be obtained. And these powders can be environmentally friendly, green, low interlayer friction, and even we can use it to high temperature where liquid lubricants cannot be used, because liquid lubricant we can go up to 300, 400 degrees Celsius, but solid lubricants we can go much higher. Currently, my focus more on like developing adaptive lubricants rather than the static kind of lubricants. So initially, we have done some tests. You can see that adding just solid lubricants at the interface will not help, because these particles will get out from the interface. It will not stay at the interface. Okay, so when you add the particles, the friction decreases, but after some times the friction increases because these particles will not stay at the interface. So to any system, we need a continuous delivery of lubricants. So then what we have to do is we have to use some kind of natural oil as a carrier fluid. So if you use natural oil or any other lubricant as a carrier fluid, the performance will be enhanced, because this will stay at the interface due to surface tension, and this will help to reduce friction and wear. So we have done several tests on adding this micron to nano-sized particles in the lubricants. You can see that when we add these nano additives to the canola oil, the friction decreases compared to, this is for the case of only canola oil. This is for the case of canola oil with the 7% boric acid. You can see that you cannot add larger percentage of these additives in the lubricants. Here also the case of another study, you can see that this gives the canola oil with boric acid. Then again, we started working on how the micron-sized particles and the nano-sized particles play important role. The nano-sized particles played much more sensitive to the friction and wear performance. You can see that the 20 nanometer boric acid shows the lowest friction compared to micron-sized particles. Similarly, the wear results follow the same trend. The wear will be much lower for the nano-sized lubricants and higher for the micron-sized particles. Is this true for every case? That is another question, right? When we talk about nanotechnology, we say that, okay, nano is better, it produces better strength and it gives lower friction. Is it true? So the surface texture and surface roughness play a crucial role here. Which size, what size particle we have to choose? So here you can see that this is the case of 70 nanometer particles, boron nitride now. So previously we studied for boric acid, then we changed to boron nitride. So nanometer size particles play important role, but when you go to micron level, you get more wear. When you mix nanometer particles and micron size particles, then you can reduce the friction and wear properties. But micron size generally gives, single particle size always gives higher friction and higher wear. But you should remember that this is for a particular surface roughness. So why this friction is high at this for micron size level? Because the surface roughness what we produced here is in the range of this 0.5 micron. So if the particle size is of the same order of surface roughness, then you get more stress concentration and more wear compared to the nano size. Nano size particle easily fill at the asperity level and produce a kind of protective layer, tribo layer or tribo film, and it will reduce the friction. So we wanted to study how these particles play a role when the surface roughness changes. So you can see that these are very smooth surfaces here. Here it's very rough surfaces. So when the surfaces are very smooth, then smaller size particles play an important role and reduce the friction. But when this nano sized particle, when you use for rough surfaces, it won't work. For example, you can see that for smooth surfaces, the nanometer size particles, 70 nanometer showed the lowest friction. But when the surface roughness is increased, the other way, the larger particles showed better performance compared to the smaller particles. So when choosing the nano additives or micron size additives in the lubricants, the surface roughness is very important. Similarly, the wear results here, you can see that in the low roughness, the nano size particles produce low wear because the wear track is very thin. But for the case of high roughness, the nanoparticles produce more wear. You can see that the width will be much higher compared to larger particles of 5 microns. So these are very important things: nano size particle, micron size particle, what surface roughness. Another interesting study we are working on, like adding graphene and graphite particles. So you can see that how the weight percentage of these particles play a crucial role. For every case, when you choose any type of additives, there is the optimum particle size or particle concentration in the fluid is very important. Beyond that, the friction will increase, wear will increase, because these particles can coalescence, and it will affect the friction and wear performance. You can see that around 0.7, both case graphene played a crucial role. It reduced friction improvement will be 26%, and wear improvement will be like 83% compared to graphite particles. So it is very important to what type of materials you choose. So most of the research previously done using natural oils, and we use canola oil. So why we have to use only canola oil? Why not other natural oils we can use? So we have done some kind of different natural oil test, and we found that avocado oil showed the lowest friction compared to canola oil or other peanut oil or corn oil. Similarly, the wear avocado the avocado oil shows the lowest friction values. So we went to further investigate what is the reason. So we found that in fatty acids there are different kinds of structures. So oleic acid plays a very important role here. So in general, the higher the oleic acid, better the friction or wear performance. I mean the lower. So the avocado oil had the highest oleic acid. That's the reason it showed the lowest friction value. So we compared with the we have done some tests with the avocado oil adding boronitrate particles. Again, here the nano size particle showed the better performance. Then we compared with both avocado oil and canola oil. You can see that when you add particles, avocado oil showed the better performance than the canola oil. This is because avocado oil had the more oleic acid content. Then another interesting research we have done on adding particles with the different textures. So what we found is very interesting result here, that for any kind of surface texture, like this is kind of sliding direction is this direction, and here the sliding direction is perpendicular. There are various degrees. We took unidirectional surfaces and slid with the different angles. So in every angle, you can reduce the friction to 0.05, but the amount of additive concentration will be different. So for example, 45%, you need 1% particles. For example, 0 degree, you can still achieve 0.05 friction, but the concentration will be 3%. So the selection of texture and the particles both play an important role. Not only just adding particles to the lubricant, you also know the roughness. You also should know the texture, what type of morphology. So when it is perpendicular sliding direction, little bit these particles engage at the interface. When it is parallel, the case, these particles will not engage. That is the reason you need more concentration. When it is 45-degree angle, then the engagement with the interaction with the two surfaces will be more. That is why the solid lubricant will be much more influential. That is the reason you get the lowest friction properties. So in summary, I can say that tribological properties can be controlled by understanding the roughness, surface texture, particle size, molecular structure, and material properties. Practice of biodegradable lubrication is essential to move away from petroleum-based lubricants and reduce the carbon footprint. Tribology plays a crucial role to enhance energy efficiency, conservation, and materials to create a sustainable environment. So my research is focusing on solving the ecological, health, economic, and performance challenges of tribological problems in advanced manufacturing. I would like to thank my PhD advisor, Professor Satish Kailas and Kishore. Satish Kailas basically introduced me in tribology areas. I think Ajay is my junior, so he also did PhD at the same professor. And Michael Lovell, where I did my postdoc with Pittsburgh then University of Wisconsin-Milwaukee. When he moved to Wisconsin-Milwaukee, I moved along with him. And now he's the president of Marquette University. Another professor we commonly worked, Professor Rohatgi. I and Ajay both worked on self-lubrication and composites. Then I thank my collaborators. There are several collaborators I have, and most of the work done by students. Of course, I thank them for doing this hard work. And of course, funding agencies like NASA, NSF, DOE, they funded several projects. Some of the projects I'm working on, like one is recently funded NASA project where I develop a CERMET composite, which is like a self-adaptive. Instead of adding solid lubricants into the composite, I basically because of environmental conditions, they are self-adaptive to the environment and provide the lubrication. Another project from NASA is to reduce the surface roughness of additively manufactured components. As you know that most of the heat exchanger components, they have internal channels. When you 3D print this component, the surface roughness is very high. So since my area is in surface roughness, I received this funding. Basically, we are trying to develop a new methodologies to reduce the surface roughness of internal channels so that it will increase the heat transfer rate. Another project from NSF, we worked on developing studying the corrosion and tribo-corrosion of bio-based ionic liquids we synthesized, and we started this research last year. Apart from that, we have work on DOE, where we develop nanocrystalline materials, aluminum materials. Our goal is to increase the strength as high as steel. So we're still working on this project, and the NUP, where we are actually using laser processing to reduce the stress corrosion cracking of the weld mates. From this, I thank for giving me this opportunity to present my research. And if you have any questions, I'm happy to answer.
Yeah, thank you so much. Thank you so much, Professor Pradeep. It was really wonderful talk. For your information, we have also started the tribology and surface engineering course at IIT Tirupati recently.
Okay, great.
Yeah, so we are also building the strong tribology lab here, and definitely we'll look forward to for your support and guidance.
Sure.
Yeah. So we have also our sponsors. We have also Dr. Devdutt Patro is there from DCOM.
Yes. Oh, yeah. He was my batchmate at IISc.
Dr. Devdutt. Hello, Dr. Devdutt Patro.
One interesting thing is that, I done test on all the 3 different equipment like DUCOM, from Bruker, and from CETR and Artec.
Yeah, right. So I think they are also working with us, and so that's it. So it is really nice to see you here, and you have given a very from fundamentals to the advanced level in the area of tribology. So now I request all the participants, if they have any question, they can ask directly to Professor Pradeep Menzies. Any question?
Hello, sir.
Yeah, go ahead.
Greetings of the day, sir, Professor Pradeep. Hello.
Yeah, go ahead.
Please ask a question, please.
Why 70% graphene is exhibiting low coefficient of friction, and after that again friction trend is increasing?
Yeah, basically when you increase the concentration, there is a possibility that these particles will coalesce. Okay, these particles are effective when they are smaller size, right? So when it is coalesces, the particle size basically due to agglomeration it increases, so it will be less effective.
Yeah, I hope you got the answer.
Yes, sir.
Okay. Any other question?
Yeah, Ajay.
May I?
Deepayan, yes, please.
Yes. Sir, as we know that 3D printed specimen has very bad surface roughness, especially specimen with an orientation angle. So can we remove these surface roughness with using a laser application? Means without using any kind of solution or saline, with laser can we remove this surface roughness?
There is a special type of lasers are available. We can using laser, you can reduce the surface roughness.
So
Of course, but yeah, go ahead.
How, sir?
There is a laser welding machines are available. When you can increase the scan over the surfaces, the asperity height will decrease.
Sir, what amount of power it is required? Can we done this in a laser marking machine with less power, with Nd:YAG laser and less power?
Not Nd:YAG laser. There is one more type of continuous laser is there that you have to use.
Means, sir, continuous laser is required.
Yes.
Deepayan, I think I am Dr. Ravi Shankar from IIT Tirupati. Yeah, there are laser polishing machines. Specified laser polishing machines are available. So there is these are, as Dr. Pradeep says, that these are continuous wave like CO2 and other things. You have a specified lasers where your power requirements are normally below 100 watts. Okay, so there are specified lasers. So it works by, I think, by remelting process. Only thing is that you have to control your parameters. That's all.
Yes.
Okay, so then, sir, I have to design.
Deepayan, that machine we are procuring it. No, don't worry. When it comes, it is on the way to receive by IIT Tirupati.
Okay,
we are working on laser polishing. Yeah.
Thank you very much, sir. Thank you.
Yeah. So yeah. Any other question?
Sir.
Any question?
Sir, I am having a small doubt on slide number 13, sir.
Yeah, please ask.
Yes.
Sir, in the surface structuring images, the right side one is the randomly oriented texture is created by polishing, right, sir? Cloth polishing.
Yes, cloth polishing with silicon carbide powders.
Sir, by this cloth polishing with the alumina powder or a diamond paste powders, the real area of contact generally increases, right, sir?
Yes. Friction is not like, when you make smooth surfaces, the friction decreases.
Yes, sir.
What happens?
Here, real area of contact increases. That's why the coefficient of friction should increase, right, sir? But
yes.
But in the graph, it is decreasing.
Yeah, but this is not smooth surfaces. If you use diamond paste polish, you will end up with 0.01, less than 100 nanometer roughness, less than 100 nanometer roughness.
Yes, sir.
But sir, this is use silicon carbide powder, so the roughness is high here. So the real contact will not increase.
Okay. Actually, compared to this 8 grounded with the emery paper, generally the real area of contact with the diamond paste powder or this any cloth polishing powder should increase, right, sir? That's why I'm asking this question.
No, that is the reason. This is the results.
Yes,
so
sir.
Because I and my professor had a lot of discussion on this, because generally we think that when you go from emery paper to polishing paper, the roughness should decrease.
Yes, sir. Yes, sir.
That is not the true.
Okay. Actually, here the asperity height reduces, right, sir? So the contact of asperities will increase, right, sir?
Surface roughness is so far no one is described properly.
Okay.
Okay, surface roughness. We say that roughness RA is this will describe completely, but it is not so. There are several non-dimensional parameters also developed, but so far no one has described complete surface roughness.
Yes, sir.
Or surface texture.
Yes, sir. This
you can develop your own surface roughness parameters, but that may correlate best with your system, but not universal.
Yes, sir. Actually, different surface geometries can have a same area, right, sir?
I think
yes, definitely.
Yes,
so this is the example, right?
Yes, sir. Yes.
So the friction will be different. So RA cannot be considered to, predict the friction.
Yes, sir. Yes. We should use hybrid parameters like delta A.
Yes, but still it is not so accurate.
Okay. Okay, sir. Thank you, sir.
Okay. Can I comment? Yeah. So Tirumala, so From this, if you see RA value is 0.242424. Okay. So if you could have measured another one parameter that is called bearing area and other thing, then there would have been small difference that you might have found. For example, okay, so if you do RA value, for example, if even though you change from, for example, if you are doing a cloth poly, any process you are doing, one case you are doing silicon carbide, another case if you are doing diamond, for example, and even though you get a surface roughness value of approximately same, but the surface morphology or surface topography, there will be a change. That is what Professor Menges has already mentioned. Okay, so if at all you want to know the difference here, okay, what you, in case of your work, if you want to go, you can go for bearing area curve. In case of bearing area curve, there may be a small change because as you pointed out, that the surface asperities in the last case is very less compared to the other 1 and 2. So in that case, for example, if you are making a bearing out of this particular surface, for example, so the life of the last one will be slightly better than first and second because your bearing area curve will be slightly better in the case of third. Because the load it is distributing will be more uniform because your height of the peak and distribution of the peaks is slightly better.
Yes, to add
I just want to, So,
in our case, we found that the slope is very important than the height. So you know that, when the slope is higher, you need more force to climb the asperities.
Yes. Yeah,
that results in more friction than just height of the asperities.
Yes, a stick and slip phenomenon.
Stick and slip is an interesting phenomenon, So when I was doing PhD, I found that stick slip phenomena basically occurs only for hexagonal metals like magnesium, zinc. Okay, but most of the literature, if you see, they say that generally dry conditions, the stick slip phenomena taking place, lubricated conditions, the amplitude will decrease. And also the stick slip phenomena depends on the load. At low loads, you may not get stick slip phenomena, but at higher load. But interestingly, when I was doing PhD, during my PhD, the aluminum is a very interesting material, which showed stick slip only in lubricated condition, not under dry conditions. But the cause will be different because what happens is when the lubricant present, there is a certain load and there is some kind of texture. Because of this lubricant present at the interface, it will be squeezed out. Okay, when it is squeezing, the viscosity of the lubricant increases. So that leads to stick slip motion. This is nothing like only dry condition you get stick slip, but lubricated condition also you get stick slip. But you should know how to explain that.
Yeah, right.
Thank you.
Ajay, I have one.
Yeah, please go ahead.
Yeah, Professor Pradeep ji, it was a fantastic lecture. So definitely, So I am Dr. Ravi Shankar, Associate Professor in IIT Tirupati. After working in IIT Gauhati, I moved now. Okay. So just I want to ask you, just out of this slide, just you were mentioning about reducing surface roughness in additive manufacturing in internal structures.
Yes.
So you are using any post-processing or?
Yes, we are using post-processing.
Yeah.
We are basically using ultrasonication and chemicals.
Okay, like slurry polishing type.
Yes.
Okay. Just by the curiosity, just I ask. Yeah.
Yes.
Thank you.
Thank you. Thank you.
Okay. Thank you so much. I think if there is no more question, thank you so much. Let us thank Professor Pradeep Menges once again, and we would like to continue our discussion and collaboration, and we would like to look forward from you. Thank you so much.
Sure, thank you. Yeah.
Thank you so much. Yeah.
We look forward to work with you. So Ajay, myself, and
all
the manufacturing fraternity and other people. Yeah.
Yes.
Thank you.
I'm happy to collaborate. Yeah.
Sure.
Thank you so much. Thank you so much for your time. Yeah. Now we have next talk by Professor David Field from Washington State University. Professor Dev. Professor Dev, are you there?
Yes, sir. I made it. Can you hear me?
Yeah. Thank you so much. Thank you so much. Nice to see you. So let me introduce Professor Dev. I have a long-term association with him since my PhD days. He has been my mentor and when I was doing my postdoc in Washington State University, we had a lot of discussion. So let me introduce him. Professor David Field, he is the professor at School of Materials and Mechanical Engineering at Washington State University, USA. His research interests are metal deformation and recrystallization, physical metallurgy of ferrous and non-ferrous materials, materials characterization, microscopy and electron microscopy, material anisotropy, and he is the expert of texture. He is well known in the area of texture, grain boundary structure, thin film and IC interconnect structure property relationship, and advanced experimental techniques. He has several recognition and honors, such as Brahm Prakash Visiting Chair at IISc Bangalore, India. He is the honorary member of Golden Key International. He is the fellow of American Society of Materials International, and he has got the best paper in physical sciences, microscopy and microanalysis, and so on. Now I request Professor David Field to give the lecture. Professor David Field, over to you. Thank you so much.
All right, thank you, Dr. Ajay. I appreciate that. So I was listening to Dr. Pradeep's lecture in my internet in my home. I use a satellite internet, and it went out. And so I had to drive to my town. I'm about 20 kilometers away from my town. So I made it here about 10 minutes ago, just in time to do the lecture. So start off, thank you very much for inviting me and allowing me to be part of this great meeting that you're hosting. My talk is going to be on processing and structure evolution of metals with gradient microstructures. So trying to create these structures and understand them. The picture up here on the left is my university, and the picture on the lower part, if you just kind of turn the camera around from where you took the picture of the university, it's very much wheat fields, it's rural area, and so I live out in the country out here, and so I was driving through these kind of fields to get here. Now, I definitely should acknowledge the students and others who I've worked with. These first ones are all students, all the way up to Colin Merriman, and then Yanis Masterakos was a postdoc working with me. And then collaborators, Tony Rowlett, of course, from Carnegie Mellon, Natalie Alambonasso and Francis Wagner, they're from Metz. At the Lemtois Lab, and Stefan Zephyr at Max Planck Institute, and Stuart Wright, who's at EDEX. So I just want to tell you a little bit about my university and about the school that I'm in. So the university, we have about 30,000 students. In engineering, we have about 6,000 undergraduate students and 1,000 graduate students. And in mechanical and materials engineering, which is the department I'm in, we have degrees, of course, in bachelor's, master's, and PhD degrees in both mechanical or materials engineering. About 19 faculty on the ME side and about 15 faculty on the MSE side. You can see the number of students there. We have about 65 PhD students right now in material science. And it's an interdisciplinary program, so it includes a few faculty members from physics and chemistry, as well as some other engineering disciplines. Now, this is kind of my personal philosophy slide that I like to share. So if we have a given material and we know the details of the microstructure, then knowing those details, if we know them good enough, then we should know the properties of the material. And I focus on mechanical properties primarily, but just knowing the microstructure well enough, then we should know the properties of the material. And modeling helps us to optimize processing parameters so we can obtain those properties we need. And to be able to do the modeling properly, you have to explicitly include something in the microstructure. And so I always try and work with characterizing structure, pulling out measures that will tell me something about the properties that I'm going to measure. And then being able to experimentally validate those models is important. I'm going to talk about that a little bit. So this is a simple view of how I see the world. So I work with polycrystalline materials primarily and metals more than anything else. I do work with some electronic materials, some superconductors or some semiconductor materials, but primarily I'm focused on metal structure. And each of the crystallites in a polycrystal has a unit cell that's oriented in a specific way. It's a certain phase. So we could have cubic and hexagonal phases in here, tetragonal, whatever, different phases. And then there's a series of interfaces, and all of these different features in the microstructure control what goes on in the material. And you can measure these by different ways, of course. And I typically will focus on electron diffraction using EBSD techniques. So first, I'm going to talk about some friction stirring. And the first couple of examples I have are friction processing, different types of what I would call frictional methods. So kind of along some of the talks that maybe one of the first talks in yesterday's meeting, Carlos, that talked about some of these kind of things. But this is one where I believe I've talked with Jay about this technique before, but this is a friction scribe tool that we've come up with. And this is to be able to take a softer, lighter, lower melting point material and connect it to something that's a higher melting point material. So in this case, magnesium or aluminum and joined with steel. And what the tool is it has a standard friction stir welding or friction stir processing type of a tool, but it has a little scribe right at the bottom. So let's show this picture here. So this is a close-up. So this little scribe tool is poking down into the higher melting point material. The reason you don't put the whole tool in there is you're going to create so much heat that you will melt the top plate that's on there. So doing a lap joint like this, you can put a little carbide tool, a little scribe, we call it, that's there. And it will go down, it will clean the surface, it will scratch it, and it will enable a nice metallurgical joint between a lighter material and a heavier material, or a lower melting point and higher melting point material. So that scribe is an important feature. And of course, there's a lot of benefits to it as far as reducing tool wear and being able to work with difficult to join material systems. Now this technique developed at Pacific Northwest National Lab, and some of my collaborators and students who are working there, some people I'm working with. In general, if you look at friction stirring and you look at how the texture evolves, how the crystallographic texture evolves, this is just, if you'll notice this micron bar down here, this is about 3 millimeters, this micron bar. What happens in this condition, the vertical direction is the tool travel direction. So the weld is along a vertical joint, and it has the shoulder is on the top here and pushing down into the slide that you can see. And then we've done a orientation map using EBSD and looking at the orientations of poles that are aligned horizontally here, so transverse to the weld direction. And you can see you get these directions that you have different colors based on where they are across the weld. And what's important about that is you have different properties based on that, because you have a different type of anisotropy. So this is something we did very early on when we were studying. It's almost 2 decades old, this paper, but very early on studying the textures and the microstructures in friction stirring, we noticed very quickly that we could modify the texture very locally in a material using a friction tool. Now, if you look at one of these joints that we did when you're joining this one, in this case, this was an AZ31 magnesium to a mild steel, so it's a low carbon steel plate. So down on the bottom is the plate, the steel, and up here is where the magnesium is, and the big weld nugget or stir zone is all up in the magnesium, and then it just joins very nicely. You get a nice metallurgical bond with steel. Of course, you do have problems with things like corrosion, depending on what type of environment you're in, of course, but if you have a need to join this and the design is proper to avoid some corrosion issues, then you can do a very nice metallurgical joint with these two materials. Now, one of the problems of using this scribe tool is that it basically scratches up the surface of the base metal of this higher melting point material, and you get particles that come up here into the weld. And of course, they usually move over to the retreating edge of the plate. So this is the advancing side, and they move around here to the retreating side of the weld. So this is now a cross section of the weld. So the bottom plate here, and then the weld tool is vertical, pushing down in here, and the weld direction now is into this slide. And I haven't talked about these textures a lot, but obviously these textures are changing from place to place where we are. One of the things you can do with magnesium when you start to get this, a lot of other particles in there, is you very much randomize the texture. So instead of having a strong basal metal texture that you would typically get in a rolled magnesium plate, you very much randomize the structure when it's in these regions where you have particle interaction. And that could be beneficial for higher ductility during or in these places that are maybe prone to cracking because of these additional particles. And of course, as with most welds and most friction stir processed materials, or any kind of friction processed materials, you get pretty sharp gradients in the transition region. So through the weld nugget, this is just looking at grain size here. Through the weld nugget, you get fine grains, and then you get larger grains up here in the base metal. And then you have this transition region where you get a sharp gradient in the materials. And typically, if you're going to have something go wrong in the material, you're going to have some kind of failure, some kind of corrosion issues, residual stress issues. These are usually going to be in these steep transition zones. And this one is showing a gradient in grain size, but the same thing can be shown with textures. So these colors, of course, with the orientation map are showing in the magnesium, are showing from the stir zone out into a kind of a transition region and then into the base metal region. And the textures are quite distinct in the different regions. Now, if we look at a couple of images up close with this is just showing these steel particles that come in and are rolled or stirred right into the metal. So this is an aluminum weld now. I've showed you the magnesium and the same thing done with aluminum. And a lot of times what we'll do is what happens with that stir when you do a lap weld like this is you get these hooks that form. So as the material is pushing out towards the sides from the tool, you get these hooks that form up. So you get somewhat of a mechanical interlock with the base metal plate. But in addition to that, you get a good metallurgical joint if it's done properly between the aluminum and the iron. Now, of course, depending on the exact region you're in, you're going to get intermetallics. This is just under the hook in this region, and you can see that there wasn't a good connection made here. And this was actually an intermetallic. It was a aluminum iron intermetallic that formed. You can see with the gray structure, and it didn't have a nice coherent interface. So this is down under the hook where this happened. So there's all kinds of problems that can come in with these kind of materials. A lot of advantages to doing them, but also a lot of issues. Right, and then if we go just through the thickness, so this is the top here is where your weld tool would be, and then through the thickness, and then this is where the second plate is. The steel is down in this region. This is just showing the aluminum and the gradient in orientation that you get as you go from the top to the bottom. And we've already talked about gradients across the width of the welds. And so with orientation gradients, you're getting all kinds of different changes and gradients in your microstructures. And these are things you need to be careful of if you're worried about issues of formability after the weld particularly. All right, and I like to show this one just because this is kind of a nice optical micrograph here. This is showing just two different aluminums. And these are butt joints. These aren't lap joints. So the joint's going down through here. And this specific one that's being showed has a crack in it. But if you do the properties, if you do the weld parameters properly, you don't get these voids and cracks in here. But you do get a nice intermixing. So you can see the gold layer is the 6000 series aluminum, and the greenish or gray is the 60 or the 5000 series aluminum. So you can see you get a really nice mixing. You do have strong gradients as you're going both. So I have over here the 5000 series is over on the right and the 6000 over on the left, and this is just where they join in. But you do get quite a lot of intermixing through the width of that weld as well. And then of course there's regions of smaller grains. So this is the 5000 that's coming through here, the gold. So that's the 6000 coming through here, the gold part, that results in a much finer grain size in that 6000 type alloy than it does in the 5000 series alloy. So you just have to recognize that you have all these gradients and sometimes sharp gradients in your structure that can be problems with your later performance of the material. All right, so that's just kind of talking about gradients in general and kind of how we can play with them. Right now we're playing a lot with additive manufacturing, like a lot of folks are. We have 3 different types of additive systems. We've had a lens system, which is a powder feed that comes in, and then we do a powder bed as well. The powder feed is nice because you can get all kinds of different alloys that are, you can mix the powder as it's coming in and make all kinds of different gradients and composition. And I'm not going to talk about that in this talk. I decided not to talk about it and focus more on the solid state processing. But that's a whole new paradigm in being able to design material microstructures for specific properties. All right, so this one I'm going to show you. This is another one that I've interacted with my colleagues at the National Lab with. And this is something we call shear assisted pipe extrusion. So SHAPE is what the acronym is for this now, SHAPE. And what happens is you basically take your metal, which is this feature in here. In this case, it's magnesium that we're playing with. We have a shoulder that's rotating and it's scrolled, got a scrolled shoulder, just like a friction stir welding tool. And then there's a collet in here. And as you push down this ram, so this is your metal, you're pushing down the ram, this is just a backing plate. And as this pushes down, the metal extrudes back up through here and creates this pipe structure. So here's some smaller pipes. This is what we started with at about 7.5 millimeters in diameter, 7-8 millimeters diameter here for these small little pipes. But now we've gone up to where we're about 50 millimeters in diameter. And I have a video. I hope this will work so you can see this video. So this is the billet that's scrolled. This is the piece that's being worked, and then this is the backing plate here. So these all get rammed together. So they're in a machine like a lathe, and then this will spin, and this piece will be forced into the spinning tool with the collet, and inside is a mandrel that is pushing the material into the pipe shape, and then the pipe is being pushed. So there you can see the mandrel nicely. And then that's just being pushed right up and out the back of the spinning tool. So there's that coming out, and then there's the run out plate. And so this is a process with that kind of friction and that kind of mixing. This is something where you can make an extremely long piece of material without, let me see, go to the next one here. You can make an extremely long piece of material without any kind of joints or welds or anything. It's just a very nice metallurgical bond, just like in a friction stir processing or something like this. Now, in this case, this is the material that is being pushed up. So the ram is pushing down on this surface, and then the material with that scrolled shoulder is being pushed in this direction and then being pushed up here. So this is one side of the pipe, and then on the other side is the other piece. So this is just one wall of the pipe that's being pushed up. So this is the material before it is being made into a pipe, and here kind of a transition zone as it's going up. And there's some nice features that you can look at with the textures and see how the pipe is shearing up in there. And this is just kind of different directions. Yeah, this is the one I was wanting to get to. So this is where you can see from the base metal of the magnesium, and you can see how that material starts to deform, and then you get a shear direction, and you can tell this from your crystallographic texture exactly which direction these are moving. And so as you get towards the pipe, the metal actually starts to flow down because a lot of it's pushing in, and you can't get as much pushed up as is coming in. So it comes in, goes down, and then pushes up against this inner collet, which forms the inner wall. And as this is coming up here, of course, this material, this tool up here is spinning against the collet. So that material is being sheared in a radial direction and being pushed in an axial direction. And so you can really kind of develop exactly where you want that shear direction to go. And through the thickness, the wall thickness of the metal, you can have a gradient that goes from your base metal aligned perfectly with the wall of the tube, all the way to where the base metal is, the C-axis is aligned with the axis of the tube. So you can rotate that 90 degrees as it goes through the wall of that. And what that does is it randomizes the texture enough that it allows for good formability. So these pipes that are formed out of AZ31 all of a sudden have very high ductility. And here's some of the walls that you're looking at, inner and middle and outer wall, and you can see grain sizes which are relatively similar. This is the larger pipes that are made here. And then this is just showing kind of a orientation map going from the outside wall going through into the inside wall. And if you look at these textures now in these crystallographic textures, and maybe look at something like this inner wall of the tube, where you get a very strong C-axis, very strong fiber texture that's pointing, basically has your hexagonal close packed plane aligned with the wall. And then as you come in here, and this is starting to turn down as you move into the material itself. Whoops. And you can see it's coming down where it's gets close to where it's 45 degrees away from that one. And you can actually, depending on how you feed that, you can control where those textures are. And that just completely removes the tension compression asymmetry that's typically involved with magnesium ductility, and really does a really nice job of solving that ductility problem without adding rare earth material into the alloy, like is done with a lot of magnesium alloys that need good formability. So that's a really promising technique, I think, for processing. And then this is just showing in numerical form of how that base plane orientation, how that preferred orientation changes from the distance of the outside to the inside of the of that tube wall, of the wall of the pipe. All right, so now I'm going to switch up and go to some material that was deformed heavily, and it ended up with a gradient structure, and then we annealed this material. So this was copper, and what's being shown here now is a video of just the surface. It's on a heating stage inside the SEM. You can see these grains growing. Here's this yellow grain growing out into this deformed region, this blue and red grain growing in. So, you know, it started out completely deformed, and then you end up with completely recrystallized material. So let me show a couple of snapshots of that. So the first nuclei of grain growth we saw were right here. And these were two different nuclei, apparently, on the surface that were actually the same grain. So obviously that nucleus formed subsurface. Now this is something to always expect when you are trying to look at something on the surface of a material. You've changed that energy, right? So you've lowered the energy by creating a free surface. And so the nucleation is almost always going to happen away from here. So it happened underneath, and then the grains grew up here. So there's the grain that you can see that grew up from that first nucleus. And one of the things that we could see through here is if you look at the dislocation density, which I'll talk about in a minute, but if you look at that density, it's highest where the nucleation took place. And so anytime you have gradients where you have very high gradient and then a lesser gradient, there's going to be something that goes on there, right? That's an unstable situation. And so we heat it up, and that's where the nuclei begin to form. That's where the grain growth happens to begin with. And one of the interesting things here, this is a little twin, this yellow grain that's forming in here. This is copper material, so there's a lot of twins. But that twin started growing. And then this grain, which the twin was part of, you know, it had these other twin variants in there as well. But this grain stagnated and stopped growing. And you see this little tiny yellow grain there that took off and started growing. This is actually a twin of this same grain that you see here. So that's the twin. That's another twin, exactly the same twin variant. But this grain had stagnated and stopped growing. The yellow one took off and all of a sudden looks like its own grain here. But it just nucleated and grew just completely out of a twinning type of mechanism. And then the interface energy with respect to the matrix was more preferable, and that took off and continued to grow. And this is something that's been theorized for a long time, that these kind of things would happen ever since the work of Peter Hasson 20 years ago or 25 years ago, whatever it's been. And here's some kind of experimental evidence showing some of the things that he had postulated. And then we go in, and typically we use a grain orientation spread measure from our EBSD to determine recrystallization. It does a pretty good job of tracking those recrystallization kinetics. And so I'm just showing you the measure. This is basically the grain orientation spread. It's just kind of the difference from each pixel, the average difference from each pixel to the average orientation of that grain. And there's another measure that people use a lot called the grain average misorientation. And this is the average misorientation just between neighboring measurements in a grain and just that overall average. And so the grain orientation spread can actually be quite large from, you know, one side of the grain to the next, whereas this is looking more locally inside the grain. So anytime you do these grain average, you get just one value per grain. And so you can identify grains or talk about structures based on that. And we just use this grain orientation spread to say here the light is the low values of grain orientation spread, the dark is the high values of grain orientation spread. So these are all deformed regions. And you can tell at the end of recrystallization, there's a couple of deformed regions that were left here that never actually recrystallized after 140 minutes of annealing in situ. And then the other thing I talked about, these twin, where this big yellow grain took off and grew from this one here, this grain, this yellow grain here. And you can see it's got twins as well. There's that green grain that's a twin from that yellow. And all of this in maroon color here and all of this in tan color, these are all grains that are related to each other by a twin variant. So these grains somehow are all related. So one took off and grew, it twinned and took off another one, something twinned here and took off. So these are all probably came from the same nucleus originally, or very similar nuclei that resulted in that kind of a structure. That's another interesting feature there. All right, going to dislocations. So gradients and dislocations are also important. And this is just some bright field images of dislocation structures. This is tantalum. So this was a specially prepared tantalum material, and you can see this is a triple junction. So this is 3 grain boundaries here, and pretty free from dislocations to begin with. We really annealed this well to remove all the dislocations. And then this one we just kind of loaded and unloaded, so there's a little bit of compressive deformation, but not very much. And then this one we deformed 2%, and this one we deformed 15%. And you can just see the evolution of that dislocation structure. And of course, this develops a very well-defined structure, whereas this is kind of tangles with regions free from dislocations and regions with heavy dislocation density. And we can go in and identify those based on our EBSD measurements. These are single crystals, and if you just look at single crystals, this one was deformed in plane strain deformation, or channel die is what we used, where you constrain the walls and then you just deform it. So it can't deform in the lateral direction. It just presses down, compresses, and then extends along the axis. And then this one was done a single crystal that we hit with a Hopkinson bar. And there's actually, a pretty significant gradient through this. This one, you had a gradient that kind of went back and forth. And this one, the high strain rate, had a real looping type of a gradient. But we want to quantify these structures. So we do this with a dislocation density tensor, and this is now standard in most of your EBSD packages. But all you're doing is measuring the curvature in the lattice. So this alpha is a curvature tensor, and it's defined by the change in orientation in a given direction or about a given axis in an X direction with a given step. And so how much, if I'm moving in X, how much does that orientation tend to change there? And so you can go in and measure these directly using EBSD data, right? It's just the orientation data on a grid. And then you can calculate from a knowledge of what dislocation should be there. So the B is a Burgers vector and the Z is a line direction of a specific type of a vector, the kth direct vector. This is just the dyadic product of that Burgers vector with the line direction. Multiply that by the dislocation density of that type of dislocation, sum them all up, and you get the same dislocation density tensor. Now this is geometrically necessary dislocations or excess dislocation content. So this does not show anything if it has dislocation dipoles where you get a half plane coming in from the top and one coming in from the bottom, for example. It just shows the dislocations that result in curvature of the lattice. And the calculation is a lower bound estimate of that. And so if you have a certain curvature, the calculation will tell you you need this dislocation density to result in that type of curvature. Whereas in reality, you could have a lot more dislocations than that. It's just that they are canceling each other out, some of the curvature that they would cause. So this is a lower bound of the geometrically necessary portion of the dislocation density. And you can do this with the high resolution EBSD techniques. And I just kind of bring this up because a lot of people will look at it, and we've looked at it here as well and done a number of measurements with it. This is an HT9 steel. One was irradiated and one wasn't irradiated, and we wanted to see if that was something we could measure. You can go in and look at some of the dislocation densities, and these got ridiculously high in some cases, maybe because of the way we did the measurement. So 10 to the 17th isn't a realistic type of a measure for a GND. It should be less than 10 to the 15th or so, or at least 10 to the 16th, I expect. But then we did the same type of measurements with conventional EBSD, and we compared these. And of course, we could get maybe lower measurements, a little bit more realistic type of measurements, but somewhat the same trends as far as where those dislocations were and where the patterns were that occurred. So these just values that we got using high resolution versus conventional EBSD. And frankly, if you're going to measure GND products, then you have to be careful with either technique. And if you're very careful, you can get reasonable estimates using either one. And the reason I bring this up is because remember at the beginning in my philosophy discussion, I said that I wanted to have some kind of measures in the microstructure that I can go in and validate with my models. So I want these inside the models as well as things that I can go measure. So crystal orientation is one of those, grain size is one of those, and geometrically necessary dislocations is also one of those. All right, so here's just a look at doing a 3D EBSD scan using a dual beam, right? So you fib off, it's a destructive method where you fib off and destroy the material, but then you have the structure. And we're looking at the difference between two-dimensional estimates from each plane versus the overall estimate, knowing what happens in the third direction. And of course, knowing the curvature in the third direction, you get a little bit higher dislocation density that we measured. This is from the 2D sections that were all rather consistent, which wasn't really surprising that they were consistent. Maybe it was a little more surprising that the 3D wasn't consistent, but obviously lower. So if you're just using 2D sections, which is typically what people will do when they try and measure the GND content, then you're getting, again, a lower estimate because you don't know the curvature through that opaque material. And you're getting a lower estimate of something that's already a lower bound. So you're really looking at a small amount of what is actually in your material as far as dislocation. All right, so this is just to show that there's, this is from exactly the same sample. These are bright field images in a commercial purity aluminum. And this is just it was deformed 2%. This is a 110 orientation compared with 111 orientation. You can see these dislocation structures have already formed, pretty sharp walls, and these are loose tangles over here. So there is some orientation dependence. And we've gone in and tried to measure that using a split channel dye sample where we looked at, the original material and then 5 and 10 and 20% deformation. And you can see this grain. And here it is deformed and deformed more and deformed more. So we're looking at the exact same grains, the same regions. And one of the interesting things in that, let me see, nope, I didn't show the other one. One of the interesting things, of course, is that for low Taylor factor type grains like this 001 grain, you get a little less dislocation density that is occurring. You get a little bit higher for the high dislocation density or for the higher Taylor factor grains, which is maybe something you would expect because Taylor factor is a measure of internal slip according to the way the Taylor factor is measured and calculated. So this maybe isn't too much of a surprise. The dashed lines are just looking at kind of average cell sizes and how they change with deformation. This is going 0 to 30% deformation, and this is 100 grains and how the dislocation density is evolving. All right, so I'm going to make you aware once again of surface problems. So this was a single crystal we were looking at, and we did a we basically had it oriented for single slip. We were hoping to see single slip on this slip plane, so we oriented it in a 2920 direction, which puts that slip plane right at 45 degrees from the tensile axis. And so when we did that, we cut that specimen in half. And on one side, we looked at EBSD, and on the other side, we looked at synchrotron measurements or high energy X-ray measurements with that. Now the slip plane is approximately in this direction. And it certainly looks from this like it should be the other direction. You see some activity. This is I should define what this map is. This is an orientation map, and it's going from 0 degrees deviation from the original nominal orientation up to 5 degrees difference. And then this is just a digital image correlation showing how the crystal deformed and some of the boundary effects, but I'm not going to focus on that. I'm going to focus in this region that actually shows some slip. This is the mapping from the X-ray structure. You can see how this looks a little bit sharper. If we do a one-to-one comparison, this is the EBSD measurement. This is the X-ray measurement. The EBSD measurement actually has a lot better spatial resolution, although it looks much worse here. And when we go in and do our modeling, this is surface defects or surface effects that allow a little bit of relaxation in that structure. We still have the same kind of curvature. These scales are effectively the same, so we still get red to green kind of curvature away from the nominal orientation. But it's just a lot sharper when we look inside the material instead of looking on the surface itself. We did this with mechanical polishing, we did it with electro polishing. We tended to get the same results either way. So that was something that makes us a little bit cautious in using GND too much from those types of measurements without being really careful. And then this is just saying, here's another one showing, see, this is a 1 micron here. This is 1,000 nanometers, this scale bar here. This was a twin boundary before it was deformed. And you can see the structure in here. This is just an image quality map from EBSD. And this structures look very tight. So this is a dislocation structure that has been well developed. This is 30% deformation, this one we're looking at. It's well developed, so when we polished it, we see a very nice dislocation structure. We don't get that relaxation that we saw on the lower deformed material. So, all right, so that was just kind of an aside to say, be careful of surface defects. So now I'm going to finish up here, just kind of showing in model. There's all kinds of different models you can use to look at deformation. This is just a crystal plasticity finite element model. And I'm going to show some equations, but I'm not going to really describe the equations too much. This is a typical way that you would describe the kinematics, just doing a multiplicative decomposition of what's called the deformation gradient tensor. This is the strain rate on a given dislocation or slip system. So it's the slip on a given slip system, the rate of that. And then this is just showing how the model works. But if you look at this, you can use an Orawan type equation and say that slip rate is the dislocation density times the velocity of dislocations on that plane times the Berger's vectors that are there. And then this is just saying this little C here is screw or edge type dislocations. You just keep track of them separately. The velocity is something we don't know, so we have to come up with a value for that in a constitutive modeling type of a way. But pulling this model out, we can basically come up with what should be the dislocation density on each type of slip system. And then when we evolve those, so this is the evolution of dislocation density of a generation term, an annihilation term, and a flux term. But we also have this dislocation density tensor that we have explicit in our equations, and we can evolve that through the model. So that gives us something that we can compare directly from our measurements with the model. So here's just showing one that we did on IF steel. So this is the work we did with our friends in Metz. So this is just basically pure iron, right? It's an interstitial free steel. This is not an orientation map. This is a dislocation density, a GND density map. And so the blue is all showing very low dislocation density. In these little regions where you have lines of color, these are actually low angle grain boundaries. So we told the software that if it's 5 degrees or higher, then that's a grain boundary, so ignore that. So if you have a grain boundary that's a 4-degree boundary, it will interpret that to be dislocation density. And so it'll show a high dislocation, a local dislocation density there. That's just something to be aware of. But then we deform this, and then you see this structure, and this is again from an EBSD measuring the plane section. And you see regions where you get rather high local dislocation densities, the geometrically type of dislocation density. So we can take a piece of that from our EBSD map and model it. And this is some work from my student, Jay Chen, and you can see he used some software that used a micron sign that was actually Chinese. So I'm not sure what that says, but I guess it means micron. But we took and we don't know three-dimensional information, so we just assumed that we allowed rotations through the plate, but we just modeled a thin slice like this. And then when we looked at it, we didn't get very good results on our dislocation density measurement. So we went back, we included some grain boundary specific criteria that say, if you have a slip plane that's going to hit another slip plane, then you're likely going to have some slip transmission through that boundary, and that's going to be more of a dominant slip. And so we used some energetics and some equations to describe that. And when we did that, we came up with a reasonably good result, I think. If you look at a grain like this grain was completely clean to begin with. So no dislocations in it, of course, and no low angle boundaries or anything. And then after it was deformed, you get a line along here of high angle local misorientations or high geometrically necessary dislocations. You get one that runs from this triple junction down through the grain. And then you get a little bit up here and a little bit here with this other grain. And so you can kind of see some of those features here as well. Now you can see a line here as well of high dislocation density, and we didn't pick that one up in the modeling. So there's always room to do better, but this one we did okay on with including that boundary criteria. But that was using something specific to look at these gradients in the material, these local gradients within a grain. Throwing something, an additional measure into the modeling that we could validate experimentally, and that helped us improve the models. So that's what I wanted to say about that. And I think that's what's being said here generally. So mixed results, but we want a model that we can validate directly. All right, so this is kind of my summary. We looked at a lot of gradient structures. We created a lot of different types of gradients with friction, with this indirect shear extrusion. We looked at heavily deformed materials and saw how the gradients were important as far as recrystallization and behavior later. And then we were able to put this in a form that we could do somewhat of a modeling with it and use our measures that we had developed in the models.
Video.
All right, so that's what we are working on, and that's the end of my presentation. And I hope I'm okay with time. I actually haven't been watching time. Sorry about that, Ajay.
Thank you so much. Thank you so much, Professor David. Thank you so much. It was really an insightful talk. You have given the very detailed information about the advanced microstructure gradations. So now the talk is open for the question answer. If I request from the participants, if they have any queries, they can directly ask Professor Dave. Any questions from the audience? Any questions from the audience? So, Professor Dev, I was just curious to know, in one of your slides on shear-assisted indirect extrusion of magnesium, you have used the spiral solder features, right?
Right.
So, just wanted to know what is the effect of that spiral on that processing, on the material deformation.
Yeah, so this spiral, what that's trying to do is to push the material in towards where the pipe's being formed, because we're trying not to have a dead zone right there like you would typically get in an extrusion die where you have the dead zone. So we're trying to move that material, we're pushing it down, but we're also stirring it around in the radius and pushing it in. So it's moving in 3 directions. So we're trying to avoid dead zones by doing that.
Okay.
And what it did is it gave the material kind of a tortuous path. So it had to go in and then down and then back up. And I think that made it so we could really control what the structure right inside that pipe wall was.
Okay, got it. Thank you so much. Any other question from the audience? Yeah. So I think there is no question from the audience. Let us thank Professor David Field for his insightful talk on microstructure evolution during deformation of polycrystals with gradient microstructures. Professor David Field, we would like to work with you. We would like to collaborate in future, and I am working on it. And if you plan to visit India, we would like to invite you at IIT Tirupati, and we will have more interaction. Thank you so much.
Yeah, thank you very much, Ajay. I hope to be able to come visit you in the near future. As soon as pandemic's over and we start making our travel plans again.
Yeah.
Right now I have no idea what plans are, but I definitely need to come see you sometime. So thank you for that invitation.
Yeah. Dr. Amlan is there.
Hi, Professor Field.
I see Amlan. Yes, nice to see you, Amlan.
Nice to see you. I have just small questions. Does this scribe technology, what you have described, modify the texture and the fracture behavior of the high strength material which is placed at the bottom during lap joint configurations?
Yeah, so the scribe is a little bit of a problem because it's going to make a pretty sharp transition region where you maybe are going to have fracture, sharp corners, these kind of things that maybe are going to cause some issues. But being able to scribe the material just a little bit so that you can make that good metallurgical joint, a nice clean surface to make the good metallurgical joint without melting your lower melting point material. That basically enables a joint that you could not make otherwise. And so there's definite disadvantages, right? You get little particles of steel up in your magnesium or in your aluminum, and you get these sharp features, but it makes it possible to do something that maybe wouldn't be possible otherwise.
Okay.
But there are problems.
Okay, sir. Thank you, sir.
Yeah, thank you, Dr. Amlan, for joining. Thank you so much. Yeah.
Thank you,
so,
sir.
Yeah, let us thank Professor Dave for his time, and he has spent sufficient time with us, and he has addressed all the doubts. Thank you so much. Thank you so much, Professor David. Thank you so much.
Okay, thank you, sir. Bye-bye.
Yeah. So now let us move to next talk. We have a talk from Instron India. Mr. Avilash, are you there?
Good afternoon, Dr. Ajay. Avilash here.
Yeah, Avilash. So we have another talk from Instron India before lunch. Then after lunch, we will have two more talks. So let us invite Mr. Ravi Shankar from Instron India, Bangalore, and he will be talking on fatigue and structural testing. They have some Instron India initiative. So now I request Mr. Abhilash Ravi Shankar to deliver the lecture. Abhilash, over to you.
Thank you very much.
Yeah.
Yeah, so I've shared my screen. If you could just confirm that you have a visual, I'll continue.
Yeah, you can continue.
Thank you very much. So myself, Abhilash. So I've been working as a product manager with Instron India. So I've been with the company for a little over 8 years now, and I'm working on the fatigue testing systems and the structural systems, what we have for offer from the Instron India product portfolio. So today's topic of discussion is the fatigue and structural testing systems, what we have from Instron India. I'll focus on some of the applications, what we are focusing with the products, and also the products which we have for offer from the Instron India facility, basically the Bangalore manufacturing facility, which could cater to most of the applications, what we are focusing under fatigue and structural testing. So the agenda for the presentation is a brief introduction about Instron, locations, operations, and then again the applications. So basically I'll be focusing on fatigue and structural testing here, what solutions we have from the product portfolio, and the differentiators, because this is what defines why one would have to choose an Instron system over other. We'll also have, if time permits, a Q&A session towards the end. I'll also leave my email address. If you have any questions, you can always write to us. We'll definitely come back and address your queries. Now, Instron has 5 major manufacturing facilities. So one is in the US, Havicom, which is UK, Germany, Italy, and India. So I'm speaking from the Bangalore facility. In Bangalore, we manufacture dynamic systems, a couple of static systems, and all structural testing products are being manufactured from the Bangalore unit. We also ship systems globally from Bangalore. About between 25 to 30% of whatever we manufacture, we ship globally. And a brief about the operations. So basically, we are about 100 plus employees at the Bangalore facility. We have about 5 PhDs, 17 postgraduates. About 25% of the employee base is mostly engineers, and then technicians similar to the engineers. We have R&D within the facility. So basically, right from software to the systems that are developed and produced from the facility here. We provide application support, of course, sales and service from the same office. And we also have a product manager sitting in the same facility. So what we could do is we can address your queries with regards to applications and also new solutions, because this facility also caters to custom solutions, not just the standard product portfolio. We are also a certified company, ISO 9001 for QMS, 14001, 18001, and then again 17025 for calibration. Now, I wanted to introduce some of the products from the portfolio, many of which I'll be discussing in the coming slides. So we start with the low force category. We call them as the low force systems. They start from about 100 newtons upwards up to 2 kilonewton. Why 100 newtons? Because we have another product portfolio which addresses the biomedical market, where forces can go as low as 10 millinewtons, and for that we have these low force systems. These systems are also used in the testing of metals, typically testing fine wires and similar materials. Now, going further, we have the high frequency electrical systems. So these can go upwards up to frequencies upwards of 100 hertz. And we have the hydraulic systems, which caters to most of the fatigue testing market. So we start from 25 kilonewtons and extend up to 2000 kilonewtons, addressing the structural testing market. I'll eventually get into the different product bases and how these are categorized. So to start with, coming to the important topic of discussion for today, which is fatigue testing. I wanted to introduce a slide as to why this whole fatigue testing took off. Like you see here, see, this is one of the paintings. Well, this is a depiction of one of the accidents that happened. And it's a famous accident. It's the Versailles rail accident. And this was in France. So this was a painting from 1840. So basically what happened is, back then, these were steam locomotives. And one of the locomotives, the leading locomotive, derailed. And basically what happened was the entire coke, which was red hot, was all over the place. And eventually the cabins ran into the locomotive and it caught fire. And funny thing, I mean, it is scary now, but back then what they used to do was, it was a rule that all passengers had to be locked within the carriages. And the fatality rate here was over 200 as documented. And this is what is thought of to have led to understanding about why fatigue testing is required and what was the reason behind the failure. Because they eventually found that one of the axles on the locomotive failed. And the reason was because of fatigue, because it was used continuously without understanding. And this plot, which is basically what we have all seen during our studies, is where we see the ultimate strength and the yield strength. But back then, during the turn of the Industrial Revolution, most of the products were designed based on the ultimate strength of the material. And that is when they realized there is also what is called as yield strength. And even in the region of, even in the elastic region, material would fail if it is subjected to fatigue loading over a period of time. And that is why we now invest time and money into testing materials, also products. We invest money into also buying equipment. Now, since we are talking about fatigue testing, I wanted to show some of the major ASTM standards covered under fatigue testing. We have the E466, which is mostly the stress controlled HCF test. Extensometers are not required here. Of course, the 606 is the low cycle fatigue test. Tests are done under strain control, which is this particular standard is very common amongst all fatigue tests. And now you see here the 2714, which is the creep fatigue testing. And of course, 2368, which is thermomechanical fatigue testing. I want to say we are one of the very few companies which can offer a product, a complete solution for TMF testing. I'll get to the slide where I talk more about TMF. Now, since we are targeting fatigue tests, I thought we also have to look at what the standard dictates. So basically what the standard says is a test system has to be verified in accordance with E4 and E467. Then again, it also says the bending strain should not exceed 5% of the axial strain. And also a class B2 extensometer has to be used. This standard also dictates some of the test termination parameters, something like crack initiation, drop in force, and all of these are covered, and it gets taken care by the software on the test system that we supply. Now, since alignment is critical for any test, and also when we're talking about strain control test, it becomes very critical. What we have is we offer an alignment kit. As part of the kit, we have the alignment fixture, a strain gauge sample, and also a software. So the strain gauge sample has 12 strain gauges, and real time when the kit is being aligned. So basically, you see the screws here, which is used for aligning. One is for concentricity adjustment, and the other for angular adjustment. Now, as and when it's being aligned, the software gives real-time display, and this is verified as per E1212. Now, what we have as part of the product portfolio to again address the alignment is a hydraulic LCF grip. Now, what this does is it is a self-locking and a self-aligning grip. Basically, what this does is it avoids the use of a spherical washer, because spherical washer having a complex geometry, it is known to induce misalignment in the load train. So we have basically eliminated the use of a spiral washer, And what this does is hydraulically, it locks the grip onto the actuator and also onto the load cell, basically applying preload so that there won't be any misalignment during testing. And also, if you see here, hydraulically, we're also loading the sample. That is, we are applying force on the sample. It's held in place and it is perfectly aligned along the load train. And we have seen very good results, upwards of 1.5% strain. You can see here. I just pulled out one of the data from the LCF test. In line with this, we also have mechanical fixture. So this is the manual LCF grip, and this is rated up to 25 kilonewtons. So this grip is part of our standard package with a 25 kilonewton nano system. I'll show that system eventually towards the end of the presentation. But basically what happens is, here there is a split pin with a nut arrangement, and this is what this provides the self-aligning feature, and similar to the hydraulic grip that you saw previously. Now this degree by which it can rotate will emulate a spherical seat. So you don't see a spherical seat here, but the arrangement is such that it emulates a spherical seat. We also have opportunity to test flat samples here, and we have very good results up to 2% strain. And this again is a test from one of the samples that was tested on 25 kilonewton system. Going further, this is one of the niche areas what we have covered for some of the customers. So basically what we're doing is LCF testing in corrosion medium, where we are targeting marine applications, could be ships, submarines, basically all modes of transportation or material subjected to corrosive media. So what you see here is a bath which has an arrangement for circulation of corrosion media. And also, if you see here, extensometer is mounted in the gauge section, and it is also completely isolated. The bigger challenge here is to avoid leakages, because one is that the corrosion media is circulating continuously. Second thing is you also need to get strain data from the gauge section of the sample. So we have a standard arrangement, and this is a package what we supply as part of the corrosion test application under LCF requirements. And for corrosion LCF, we also have another testing which basically targets weldments, because steel is welded and they're also subjected to fatigue loading. So the challenge here is, when testing weldments, samples are in the hourglass specimen shape. So you see here it's in the form of an hourglass. The arrangement is such that strain is measured diametrically. So this is a custom designed diametrical extensometer. We use this extensometer to measure strain, but the problem is this will not be able to detect crack initiation and failure. So for that, we have an axial extensometer working in tandem with a diametrical extensometer, which detects crack and basically terminates the test. So this is another standard rig. So both these configurations can be used for corrosion testing. And sorry, just have to go back. Okay, so now we are seeing the creep fatigue testing. So earlier ASTM 606 covered tests. Basically, these tests are done at elevated temperatures. You see an image of the sample with the extensometer from within the furnace. We have configurations with testing which could be done upwards up to 1,200 degrees centigrade. And basically what we do is we introduce a hold time during the loading and unloading regions. And you see here, this is during unloading. We can have it along both the ends during loading and unloading as well. So the new standard ASTM 2714 provides option for hold at different stress levels, unlike what ASTM 606 did earlier, which was basically driven by strain control. And with these tests, what one could derive is the transient, the stress relaxation regions, and also the change in fatigue life, because if the material is subjected to different loading conditions, and if there is a hold time, which the material sees. So basically, there are standard configurations available for such testing. And this is the TMF application. So thermomechanical fatigue we can do in phase and out of phase testing. So basically, in this video you see, this is a sped up video because the rate at which the temperature is increased is somewhere in the 20 degrees centigrade per second range. So heating and cooling is done. Of course, heating is done using the induction heater. Cooling from the compressed air arrangement. You see here the jets of air being directed to the sample. So the biggest challenge here is tuning the whole system for such an arrangement. And there are multiple modes, and the software will transfer the constants to the firmware because all the computation here is done on the controller. And the thermal strain compensation, the constants from the polynomial is what I'm referring to. So I'll just let the video to run so that you see the different modes. So with this whole package, we also provide whatever is required for a customer to do a TMF test. So we provide the thermocouples. So basically we have 3 thermocouples which are spot welded onto the surface of the sample. You see here 1, 2, and 3. This is spot welded on the surface of the specimen. And there's an extensometer here which is measuring the strain. But basically, the whole package is built around the ASTM 2368, and it adheres to what the standard dictates. Now, that was the fatigue part, basically covering LCF and the TMF test applications. We also manufacture rig beds and systems which would cater to the structural testing applications. To start with the civil engineering application, we build portal frames. These are custom built, and we also have certain standard configurations with actuators mounted on them. So you see that there is an actuator which is mounted vertically here. And basically portal frames can also have different mounts on the actuator, so that if maybe the specimen or a product calls for application of load along a different direction or at a particular angle, we can always supply such configurations. Now, I thought I'll include one of the recent supplies, what we did to one of the customers, overseas customers here. So this was for testing sleepers, and this is a 500 kilonewton configuration. The actuator is mounted on top, it's a top mount actuator configuration. And this chamber that you see can basically cycle temperature between -40 and +60. So the sleeper is subjected to different temperature ranges, and it is also a fatigue system. So up to 15 hertz of fatigue load could be applied, and this is rated at 500 kilonewtons. We also have to be one of the few companies who are supplying shake tables. So one of the configurations that you see here is a biaxial shake table. We have uniaxial as well as biaxial shake tables with payloads upwards up to 10 ton. We can supply shake tables with strokes upwards up to 1.5 meters. What you are seeing to the right here is an electric single axis shake table. The payload here is about 100 kgs and about 300 millimeters of stroke. So basically the target application is seismic applications. We have the option to feed seismic data from any of the pre-recorded events. So you can eventually simulate such a situation here. We also have 3-axis 60 of freedom shake tables. So these can offer displacements upwards up to half a meter, and frequency is up to 30 hertz. We have similar shake tables in few of the prestigious institutions in India, and also some overseas supplies that we have done. Tables can custom for the application that any of you have. Now we talk about multi-actuator systems. What we have is we have rig bits here. So to start with, it's a 3-axis boost test rig. So what one could do is you can apply conical loading, torsional, as well as radial loading simultaneously on the bush. So basically the rubber sample there is being subjected to different multi-axis loading. And this is of course a fatigue test rig. So you can again feed data from one of the recordings which was done on any of the automobiles, during one of the trial runs. And what you see below is, let me just play this video. This is a simulation where multi-load, multi-actuator configuration where the wing of an aircraft is subjected to multi-dimensional, and all actuators are being controlled by a single controller, and the data can be fed from a order here again. Of course, for automotive testing, for structural testing on automotive components, we have rig bits. And for such applications, what systems I have from the product portfolio. So like I said before, targeting the low force test system, starting from 100 Newtons up to 10 kilonewton. We have the electric system, which is the LFS series top system. These cleans on polymers, but the force is limited to 10 kilonewtons and frequencies up to 10 hertz here. Of course, this system can be tilted in the horizontal direction if lateral loading has to be applied on maybe a sample or a component that is subjected to testing. Because the way this system was developed was targeting academia and R&D sectors. Why? Because 25 kilonewton, and this whole package comes with all accessories required targeting tension, compression, fracture mechanics, and fatigue applications. So in addition to this, we call this as a plug-and-play system because what is required is a single-phase supply, and that's it. This system is on wheels. It is mobile. You can move it from your classroom. Am I audible? Yeah. So this is the bottom part of the system. Hydraulics again are within the system, controls hydraulics and the cooling. All are integrated. It's a single footprint machine. And like I said, it is what we call as a plug and play system. And this is very popular amongst academia and R&D institutions. Now, if we increase the capacity, we call the systems as the median series. So the one you see to the left. So the force capacity ranges from 50 to 600 kilonewtons, and all the fatigue test applications that I showed you before was mostly done on frames of this sort. So basically, the 100 kilonewton frame is almost always used for such applications. You see here a system with the furnace. We also have a servo electric configuration with a maximum capacity of 200 kilonewtons. Frequencies can go upwards up to 80 hertz and even more. So this is a hydraulic rig. To the right, you see a high capacity system. So this basically is a 4-column system and targeting structural applications. They start from 600 kilonewtons up to 5,000 kilonewtons. Strokes are limited to 150 millimeters. I can also confirm you that we have customized some rigs where the stroke is much higher than what you're seeing here. But then again, these are targeted towards structural applications. We have a bottom T-slot bed, so you could test maybe an I section or as shown before, a sleeper. Or we also have some of the customers who are using systems for testing actual components, so structural requirements, automotive components, and even polymers. As shown before, the structural actuators are part of the structural test systems. But what I wanted to show here is, see, these actuators can have different mounting arrangements. So what you see here is a pedestal mount, which we use for applying load vertically, so in the upward direction, and swivel mounts. So these are in place to avoid damage to the actuators because of side loading. And we also have face mount actuators. So basically, we can combine different actuators with the rig beds, and we can formulate a test platform for any of your structural testing requirements. We also have servo electric options, but they fall under the static testing category for be a hydraulic actuator. Now, we understand that about recently our old test, so the life, that is the test frame is much higher than the electronics, because technology changes, but an actuator has to apply force, and it sits on a frame. Basically, that's what it does. We have up for our is retrofit. We can renew your old test systems with the new electronics and software. So basically, it's very similar upgrading your machine. You can always look into programs of the start. The system stops when the standard that this is the condition when the system has to run continuous, insensitive to contamination. So basically, these systems run around the clock. We also have a very big test lab here in Bangalore. I'll get to that in the coming slide. But what I wanted to stress upon is the kind of systems, the kind of components that we use in basically reservoirs are known to operate in harshest conditions, and what key to and remote monitoring services. I have the lab resource management. I think it got disconnected. Audible? Yeah. Okay, I'll just share the screen. Sorry, for some reason it got disconnected.
Yeah. I think you have some unstable net connection.
Yeah. I have 3 or 4 more slides,
No problem.
More than.
Please go ahead.
So I hope my screen is.
Yeah, it's visible. Yes.
Visible. Great, thanks. So I was referring to Connect BI, which is a remote monitoring package, and unlike you having to get to a system to get a visual of what is happening, since you're mostly into fatigue or creep testing, where these are long duration tests, you can remotely monitor the tests, and also we have a feature where we can provide remote health monitoring for we call as a preventive maintenance. So our team can always work with you and extract data from the system, which basically gives a heads up as to when a system has to be maybe so basically these preventive maintenance systems. So this comes under the Connect BI package. Like I said before, we have custom solutions. So we provide solutions based on requirements. So these are packages outside of the standard product portfolio. And like I said before, we build systems here in Bangalore. And since we are the OEM, we know how to fix it, and also shows the efficiency in terms of servicing from Instron India. I wanted to introduce some of the customers, existing customers. So basically, this shows the market presence. Most of the IITs and NITs, including Institute of Science, which is very close to Bangalore. Russia is again a very big customer base for us. Our target customers are from academia, aero, defense sectors. And we also have some of the customers from the OEMs, basically from the automotive and the aero domain. When I talk about service support, we provide services for calibration, preventive maintenance, like I said before. We also repair systems, and also the retrofit package comes under the service again, because a system, if it has to be renewed, integrating the controller, maybe even servicing the hydraulics comes under the same domain. This is I believe the last slide. So when I spoke about Connect BI, I was referring to integrating all systems either through your local area network over the internet. So everybody who is connected to these systems, they get a visual of what is happening on the machine, including could be the professors, the students. If you are from a contract testing lab, the lab managers and the business head will be able to extract data from these systems. So this is a topic by itself. We are launching this towards the end of this month, and we'll have a functional package. Some of our customers are already using this. The last thing what I wanted to introduce was the test lab. We have in-house test labs, which is NAPL and NADCAP accredited. We have over 25 systems. So in India, if you have any testing needs, please feel free to contact us. And lastly, thank you very much for your time. I know this is a lunch hour, and you all have been patient enough to stay on board and listen to the talk. Dr. Ajay, thank you very much for the opportunity. And if there is any question, feel free to let me know. I mean, I've also listed the email address here. So one can also write to either myself or the other address that's listed here.
Yeah. Thank you so much, Abhilash, for the nice presentation. Now I request from the participants, if they have any question about the mechanical testing development equipments, feel free to ask questions from Abhilash. Any question from the audience or participants? Yeah, I think it's a lunch time. You will be hungry because you are listening from morning. So Abhilash, it is good to have you here, and thank you so much for these developments in the area of mechanical testing and UTM's machine, which you have presented here. And we look forward to continue our interaction in future, and look forward to see you. Thank you, Abhilash.
Yeah. Thank you very much for the opportunity.
Thank you so much. Yeah.
Have a good day. Thank you. Yeah. Bye-bye.
So now with this, we have ended our pre-lunch session. In the pre-lunch session, we had 4 presentations. First presentation was by Professor Satish Bukpatnam. Then we had Professor Pradeep Menges, Professor David Field, and Mr. Abhilash Ravishankar. So with these 4 presentations, we have ended our pre-lunch session. Now we will break for the lunch, and we will rejoin at 2:45 p.m. We will start our, we have 3 more presentations. So we will rejoin at 2:45, and the presentation will start from 3 p.m. onwards. And so let me tell you, we have a presentation from DUCOM, Dr. Devdutt Patro from DUCOM. He will be discussing about Travelology 4.0. And we have Professor Nikhil Gupta from Newark University, and he will be joining at 6 p.m. For his place is morning 7:30 a.m. So you need to join at 6 p.m. for his talk. And after his talk, we will conclude our webinar. So let us meet at 2:45 p.m. Thank you once again. So, yeah, good afternoon, Dr. Dibdatji. Are you there?
Hello, Dr. Ajay. Hello.
Yeah, good to see you.
Yeah. We are from the office, so I have to still keep wearing a mask. I hope my voice is audible.
Your voice is audible, no problem. Okay, so we will wait for a couple of moments now, so that more participants will be coming.
Sure.
Yeah. Is speaking. Okay. So, Dr. Dibbatji, shall we start?
Yes, Dr. Ajay Kumar, I'm ready.
Yeah, okay. So, yeah, so dear participants and my colleagues, welcome back. So now we have Dr. Devdutt Patro from Ducom Instruments PVT Limited, Bangalore. So it's my pleasure to introduce Dr. Devdutt Patro. He is a product specialist, tribology at Ducom Instruments. He collaborates with the academia and industry to establish knowledge partnership in friction and wear evaluation of materials. Being a subject matter expert in materials characterization and tribology, he also hosts workshops and specialized courses on contemporary challenging topics such as electric vehicles, tribology, high temperature and biomaterials, wear and friction. He holds a PhD in materials engineering from Indian Institute of Science, Bangalore. Prior to Ducom, he was with General Electric Global Research and Development Center in the Manufacturing and Materials Technology Organization. And during this period, he conceptualized and matured several technologies across diverse applications. I welcome Dr. Devdutt Patroji for joining us today. Now I request you to deliver the lecture. Dr. Devduttji, over to you.
Thank you, Dr. Ajay Kumar, for the kind introduction. So we are both from IISc, so we have a common background.
Yeah.
In some sense, right, about that atmosphere. So it's a pleasure always to reconnect back, with IISc and with you, Dr. Ajay Kumar. So I'm sharing my screen. Is it visible?
Yeah.
Sure. So I have 1 hour, but what I will try to do is I will try to complete it before that, so we have enough time for questions and discussions.
Yeah.
So I think all of us have listened to what Professor Pradeep Menezes talked about early in the morning on the importance of tribology and how so many new exciting developments are there in materials, ionic liquids, and a lot of interesting material science and how the microstructure and materials property could influence tribology. So what I would be doing in the next 1 hour is giving you a different perspective of how, moving away from connecting the academic research and innovations, from the lab to the field, and then how the experimental research is an important enabler in the entire process, and especially when you start to look at a tribometer. This is a short video. It will introduce the company a bit, but it will also give you a background on let's say, how tribology has evolved and where it stands now. So I'll quickly play this video. Right. So I think the video captures in essence what would be the theme of this presentation. So obviously, you know, as material scientists, we are always motivated or inspired to look at materials, lubricants, and technologies which can address pretty much the four major problems associated with globally. So let's say, you know, climate change, you know, the carbon dioxide, global warming, healthy living, especially healthcare, renewable energy, and then finally resource utilization. So tribology, you know, it's being said often on this platform that materials enable all of these technologies, and you know, and how tribology connects was also highlighted by Dr. Menezes. So keeping that theme, what I would cover in the outline is I will give you case studies, and these are case studies where it's slightly different because it also gives you an industry perspective into how a materials discovery in the lab can actually make a difference in the field. So I would try to highlight that with case studies. And now when we look at the case studies, we will also come across a concept of something called as data-driven decision making. So for people to implement something in the field requires people to develop confidence. And confidence comes from data and faith, and an underlying pillar of faith and data is repeatability and reproducibility. So it's that the data being generated or the novel findings are not limited to the lab alone, but they can be repeated and reproduced elsewhere. That enables confidence and faith in the discovery. And that brings a lot of data management into the process of data analysis. And lastly, I will introduce how we can use 4.0 technologies, which has been covered on this platform in different forms, and really bring it into tribology or materials innovation. You know, in different forms. I think Professor Surya Kalindi talked about how, you know, 4.0 technologies and AI are driving materials innovation, helping them to discover new materials. So I would try to use or let's say highlight 4.0 technologies as pillars of data management in the lab and how they can make our work more effective. So coming to the first, before we start the topic, one thing about tribology is, you know, as part of a mechanical engineering or as an interdisciplinary topic, is it is highly experimental. Predictive models are there. People do a lot of simulation, but those simulations are fairly advanced for material science and mechanical engineering. But in tribology, they are very complex just because of the, you know, the mechanical, thermal, you know, chemical reactions and a lot of unknown things happening at the surface. So they are very, very complex and not yet evolved, which means for solving problems, we still have to look at tribology as an experimental subject. So there are a lot of experiments, a lot of tests, the right kind of tests which are involved in understanding materials and their tribological performance. So let's pick up the one, you know, one of these case studies, which is at 1000 degrees. And why I bring up 1000 degrees is because it is connected to a lot of industries, whether it is manufacturing in the steel plant or it's a power plant or even in defense or transportation where it powers a gas turbine. So all of these require materials which see, you know, temperatures exceeding 800. So you cannot use, normally you would use steels, but you cannot use steel. So you have to use cobalt or nickel based alloys with coatings. So, and then how do you start really understanding the performance of these materials at 1000 degrees? So, and that's when you would start looking at experimental platforms to evaluate materials, right? So some of the new materials which are developed in the lab, some of the new manufacturing methods, whether it is additive manufacturing or deposition. So for that, we have got two platforms. So one of them is on the left side, of the screen you see is the erosion tester, which can go up to 1000 degrees for evaluating coatings. And then the modular rotary turbometer, which can go up to 1000 degrees for friction and wear. Now, let's look at one case study where we are looking at multi-layer materials, or in this case, coatings, and how a lab experiment can help develop scientific insights and how it can be quickly deployed in the field and undergo field trials. So before that, let me highlight the challenge a bit. So the gas turbine operates at temperatures. So the core temperature would be close to 2400 or even 2600 Fahrenheit. And that is close to 1/5 the surface temperature of the sun, hence the analogy, right? So the surface temperature of it operates very close or at comparable magnitudes to the surface temperature of the sun. And then in that period, right, you get something like a 25,000 hour maintenance interval. So you typically don't do a shop visit on a gas turbine till 3 years. It's supposed, so the aeroplane is supposed to run for 3 years daily with 5 or 6 takeoff and landing at this temperature. And during that period, it can travel a distance, close to 875 km/h speed, almost the distance of close to 20 lunar missions. So this is unimaginable when you think of two-wheelers or four-wheelers, where you typically go in a quarter to change, top up or inspection. So gas turbines typically don't require anything except a surface, external inspection, but nothing major for 3 years, and with the course running at 1000 degrees and above. So this is this. I'll play this video. This is how we would test the material. Of course, I'm not showing the actual test because when we push the sand at very high velocities, we cannot keep the chamber open. So just for visualizing the fact that we are running a sample at 1000 degrees and then there is a stream of erodent, this video was shot. But let me show you what would happen when you do this experiment. So these are 3 coupons which you would typically test in your lab, and these are what I'm showing you is about 25 mm by 25 mm coupons, square coupons. And the base material was Inconel 718, which is a fairly commonly used high temperature material. And it's also age hardenable. Now, the top experiments were done where, this material was subjected to different temperatures, and then you got some sand particles impinging on that material, right, or the coupon. The bottom set of images are the same substrate, in this case Inconel 718, but what was done is, there was yttria stabilized zirconia, which is a very common thermal spray coating used for these applications, and that was coated on the substrate. The point here being how a coating can prevent, I would say, rupture of the substrate as you start testing at higher and higher temperatures. So if you look at the images from left to right, you would not see, that the substrate is still intact till 600, but once you hit 1200, you can see the substrate actually getting punctured through, while on the bottom with the coating, some of the coating has gone, but the substrate is still not affected. So it just gives you an indication of how important coatings are in some of these applications, but more so how they are actually making a difference. So identifying the right coatings and testing in the lab according to the tests shown before, how can it make a difference? So this comes from one of the studies by Dr. Harish Barshilia from National Aerospace Labs, and he has been running a project for quite some time. And it's very important in the context of India, because if you look at Indian defense, which is a very strategic industry, we only produce 50% of the weapons. So if India is probably one of the biggest importers of equipment globally. It's probably the second largest arms importer in the world. And when you import a lot of equipment, lot of infrastructure, you would have to maintain them, over their life cycle. And maintenance costs can be very, very huge, almost 10 times the cost of importing or the initial cost of the equipment. And there are reports which say that, you could save a lot of maintenance cost, by deploying materials which could prevent failures of the kind we saw earlier, as well as maintain aerodynamic efficiency. So for aerofoils or things which go on the compressor, surface finish and aerodynamic efficiency are correlated, and eventually it relates to fuel consumption or how the power is generated in the engine. Right? So what was done here by Dr. Harish Barshilia and his team members was they developed a lot of novel multi-layer coatings. And the novelty in this case was they developed not multi-layer but nano multi-layer. So there was a lot of novel materials with different compositions, TIN, TiAl, and chromium nitride, titanium, which were deposited on standard coupons. And on this in this picture, what you can see is the difference between a coated and an uncoated sample, right? So you can see that the uncoated and the coated sample show different results, and those were encouraging enough to transition the coating process out of the lab into the field. And on the image you see on the right side is in fact the actual component. So that was coated again based on the lab trials, and the field trials, it has to undergo significant field trials and rig trials, but the field trials are very promising. So all these images are from Dr. Barshilia's work, so it is acknowledged to him. But having having these material discoveries being tested in the lab and identifying the right candidates using the right test methods can help get confidence to transition them out of the lab into the field, to field trials. So materials inventions become innovations. So that's the power of what repeatable and reproducible data in the lab can enable. So coming to the second topic, and so which is to do with again materials, but in this case they are nanoparticles. So they're not coatings, but they are nanoparticles. And for this particular example, what was done was the nanoparticles were added to lubricants. So Dr. Menezes talked about using ionic liquids on their own or as additives to get a lot of lower coefficient of friction, lower wear in several applications. And here what talking on the same theme, we are talking about nanoparticles and how they can be used as additives. See, one of the advantages is environmental friendly. Typical lubricants, as most of you might be aware of, use a lot of chlorine, sulfur, or phosphorus, especially people, who do a lot of metalworking machining and they use lubricants. Metalworking fluids, for them, they know that there's a lot of sulfur and phosphorus and chlorine being used in order to enable the cutting process to be more efficient. And that is not environmental friendly. Eventually you have to dispose of that lubricant or the metalworking fluid, and there's a lot of sulfur and chlorine which goes out. In Europe, there are standards which regulate the chlorine concentration to be lower. Should not, in fact, there are chlorine-free lubricants being developed just to make sure that the metalworking or the machining operations are environmental friendly. And one such technology, which is from the material standpoint, which can enable that to happen, is using nanoparticles which are not, let's say it's a chlorine-free, right? So now, if you look at this series of images, right? So in this case, what was done is we had a conventional metalworking fluid which is chlorine, and then there is a metalworking fluid which is chlorine-free, but it had something called as tungsten disulfide, nanoparticles, but the tungsten disulfide nanoparticles had an inorganic fullerene structure. So they were a core shell kind of a structure which was there. And some of the initial trials, which happened on the actual test bed, right? So the top is actually milling, and the bottom is grinding. It shows that the conventional metalworking fluids and the inorganic fullerene nanoparticles do show similar. In fact, the surface finish is better for the inorganic fullerene nanoparticles. So the field trials were actually promising. The question was, what was the mechanism by which these things work, right? And at what concentration? So optimizing the concentration, understanding the mechanisms become important, because this has been demonstrated that it has potential in the field. So these images and this video, which I will play, is from our collaborator, Nanotech Industrial Solutions USA. And they actually make these nanoparticles with a very proprietary technique, and they are using it for different applications. So these videos are from their library, and we are using it here. But I will show you what I mean by the mechanism of how these nanoparticles behave. So on the left, you would see this is a transmission electron micrograph of these inorganic fullerene nanoparticles. And there is, if you see, there's an onion kind of layer-wise structure, right? So there is, each layer is a tungsten disulfide, plane, and there are several of these stacked. Now, how do these really behave? When you put them between a surface or they are in contact. So let me play the video on the right here. This is an in situ, transmission electron micrograph. And there is a video shot of how these particles behave. So on the left, you would see this is a surface. On the right is actually the tip of a sharp tip. And there is a particle which is between these two surfaces. So let's bring them together and see what the particle does, right? So now you're actually squishing the nanoparticle. Think of it as very high load. And you can see that it has very good compressibility. And at some point it cannot, and it slips. And it slips because of these low shear layers, right? It moves out of the contact. But importantly, what you see is there are a few layers which are still stuck to the surfaces. Now you are retracting it back, right? So when you're retracting it back, you can see there is like a shell which is still stuck to the two surfaces, right? And it's still stuck even when you pull it off. And here you have complete lift off, right? So, but you see what the nanoparticle has done. How does it behave? So when it's at very high load, it does show a good amount of compressibility. And at some point, of course, that fails. But when it fails by shear, you get residual layers or a certain number of layers which are still quite adherent to the surfaces. And they form what may have been mentioned early on in the discussion as tribofilm. So you actually form these tribofilms. In this case, you do it by a physical mechanism, rather than a chemical interaction. So now we have got the field tests, and we got this in the transmission electron microscope. But in transmission electron microscope, you do one particle. So is it really representative of something which is bulk? So that's where we got an experimental instrument called as a 4-ball tester. This is one of the industry standards for testing lubricants, and it can test and give you very repeated. It can repeatably give you those results for any lubricant. And all is required is about 25 to 30 ml. So you don't have to make liters of lubricants, and which you would require for a field operation. Very small quantity of lubricant, you can test them to understand if it has the potential. So when we ran a test, and in this case, what we ran is a stepped load test. So the load was increased to increase the contact pressure, similar to what we were doing in the transmission electron microscope by putting them together, bringing the surfaces together. We're actually trying to create more aggressive contact pressure and loading conditions. So we tried to simulate that in the 4-ball tester here. So to read out these graphs, the red plot, which you see like a step, is the load, and it is ramped, every after certain seconds or minutes, it's ramped to go all the way up to, something like, 2000 to 2 kilonewton, right? So, and then, there are two other plots. One is the green and then the orange. So the green is the conventional metalworking fluid being used today, which has chlorine in it. And the orange is the chlorine free, but now it has got these nanoparticles which have the fullerene kind of a structure. And failure is indicated by this sharp rise in coefficient of friction. So whenever there is failure, the coefficient of friction shoots up because you don't have the low shear strength across the interface. So you've got steel on steel contact, and in this case, they actually weld together. And then from the load displacement and the load time curve, you can back calculate the adhesion energy. And we did that. And when we did that, we found that the adhesion energy of the fullerene, right, which is the orange, is like almost 4 times that of the conventional metalworking fluid. So what it helped or support whatever data was there at the nanoscale and in the field was there was now a tool in the lab which could reproduce, let's say, the benefits we see in the field, but it also explained the mechanism, or we were able to correlate it to the nanoscale mechanisms of how an adherent tribofilm could in fact delay the, give you lower coefficient of friction, point number 1, but it could also withstand much higher loads. And this becomes very important when you do metalworking operations where, more aggressive metalworking operations, turning, machining, high speed, where there's a lot of heat generated. You don't want the tool to, and the workpiece to cease, right? So these kinds of developments actually would enable some of these new applications, new manufacturing processes be more effective and environmental friendly. And of course, thanks to George Deloyan, so he's the CEO of Nanotech Industrial Solutions, and there's a lot of work we have collaborated with him, and more recently with Professor Jayashree Bijwe from IIT Delhi. So she's the Reliance Chair Professor. She's also working a lot on how we can use other kinds of nanoparticles like PTFE, which is can be also used as an additive in oil to get rid of some of the other harmful or environmental unfriendly materials which are being used. So for any of these students and participants who are interested, what is being covered here is available as a video on the DUCOM Tribology channel. So, and it's free, so people can just log in and watch the videos if they want to know more. So coming back to the second theme, right, which is we start off by understanding our materials in the lab, right? So we start off by tinkering in the lab, coming up with ideas, developing these discoveries in the lab, and then taking them into innovations requires faith in the data. So, and faith comes from confidence of having a robust process where you can repeat day in and day out what you generate from an experiment. And that's basically what this says, that data repeatability is the cornerstone of your lab. So if somebody does an experiment in the lab and a few years later, another predecessor may come and do another experiment, right? And if it does not repeat, and if there is some anomaly, then you know that you don't have confidence or faith in what was done. So repeatability is very important in a lab. And now when you go beyond the lab and you talk about science, right, publications in science or innovations or things you want to move out of your lab into an industrial application, then reproducibility becomes important. What experiment is done in the lab? If the same experiment is done in another lab under the same set of conditions, would you be able to reproduce the results, right? That is the pillar of science. If you are not able to do it, then there is, then there is you have to look at why we are not able to do it. So now that brings up an important topic of something called as a reproducibility crisis. Now, what do I mean by reproducibility crisis is experiments being done in one lab are not being able to be replicated in another lab. And not only that, they are probably not being able to be replicated in the original lab after a certain period of time. And that's when you see a lot of scientific publications, we saw in the last several years, a lot of papers have been retracted from prestigious journals like Science and Nature because of authenticity of data, right? Now, this is a bold step, and hats off to Professor Hans Frances Arnold. So she is a Nobel laureate in 2018, and she tweeted early on in 2020 that she had retracted a paper. She took her own step to retract a publication from a prestigious journal because she was not able to reproduce her own work. And she had that integrity to approach the committee and get it retracted, saying that, you know what, possibly by oversight that some of the results were not in line, and let me retract it back because I don't want this to go out as a scientific study. Since then there have been several surveys, and these are some of the snapshots of surveys conducted by Nature, and they reached out to almost 1,500 or 1,600 researchers globally. I'll come to the statistics part later, but the simple question asked: is there a reproducibility crisis? And definition of reproducibility here is the work done in your lab, can it be replicated by somebody else from your lab, or can it be replicated in another lab? Let's say that's a simple question which was posed. And the red sections of this pie chart show the number of people who agreed, yes, there is a crisis. You can almost see that close to 90, a overwhelming majority agreed that there is a crisis. And it has been repeated, of course, in 2016 and also 2020. Now, if the questions were to be broken down by discipline, right? And I'm looking, so on the left, you would see questions which were asked, not only on engineering, but also biology, chemistry, medicine, earth sciences, a lot of across different engineering disciplines, right? And there are two questions asked. One is, have you failed to reproduce an experiment which is your own? And in the physics and engineering discipline, almost 70% agreed yes. 50% agreed. And if it is someone else's work, then it becomes higher. Then the next question which was posed to them is, why do you think there is a problem? What factors really affect why we cannot reproduce either our work or someone else's own work? And I will only highlight the points which are there in encircled. The other factors which are there, that is selective reporting and integrity and pressure to publish, that is not the objective of this presentation. But if you look at the ones which come out very strongly, right, where the center is based on data, right? So the first is low statistical power or poor analysis. So there was not enough experiments done in the original lab to substantiate the results or the findings. Not replicated enough in the original lab. Third point, which is encircled in the right side, is either the method or the code is unavailable. Method means properly documenting the way either the materials were prepared or the experiment was conducted, right? It's not available. And lastly, the raw data is not available. So raw data is usually the Excel file, right? I mean, usually most of us would take the raw data and, kind of post-process it and show it as bar graphs in a publication. That means the raw data is not available. So if the raw data is not available, all you have is a single point. So let's say you run a friction test and you report the data as 1 point. You know that friction is not a single value in the entire test. You could go up with a initial friction, you could run into steady state friction, it could migrate different ways. But if you represent it with 1 point, so a lot of scientific information we are missing out. So, and the raw data is never published, right? I mean, it's usually processed. So it becomes difficult to benchmark what another experiment would look like. And of course, what what further adds to this concoction is we all use some kind of scientific instruments for any measurements we make, right? So any experimentalist would rely on a scientific instrument. And it's extremely important to have these two considerations in mind. That is, all scientific instruments typically are governed by certain traceability standards. So starting from the industry, which gives the scientific instrument, to the calibration lab, all the way to the international standard. So it should be traceable and there should be calibration. So what are those international standards? It could be ASTM, which we typically use for material testing, right? They give you a set of guidelines of how you could run a, let's say, simple tensile test or a hardness test, right? So we follow certain guidelines, and the same guidelines help us establish a set of procedures and methods, and also help us to calibrate with certain reference materials, right? And some and these are some of the examples of the guidelines, right? But how does EUCOM, or how do we look at let's say a scientific instrument, in this case a 4-ball tester? See, the 4-ball tester was used for understanding materials like nanoparticle lubricants, but how do you establish a calibration and a global benchmarking for a 4-ball tester? So then we have to look at the global standards organization, in this case ASTM, and the ASTM typically runs something called as a proficiency test program. And the objective of the program is simple. There is an oil, the properties of which are unknown. The same oil is given to close to 30 to 35 labs globally. So, you know, our lab and 35 other labs globally participate, and nobody knows about that particular oil. What additives are used, what the result ought to be, nothing is known. We just follow a well laid out protocol, and then, you know, all of that data is kind of then summarized by the committee, and they establish precision limits, and they establish the performance of the lab. So how do you know where your lab is in terms of being able to repeat or reproduce the data compared to 30 other labs globally? And the parameter which I'm highlighting here is called as a z-score. So z-score is nothing but it's the standard deviation divided by the mean. It can go from, you know, it has both positive and negative depending upon where you are with respect to the mean of the population. And then why we are talking about it is, one of the things which was raised out in the survey was there is not enough statistical analysis to suggest how repeatable or you know, how reproducible is the data. So the z-score is one of those metrics which tells you where you are with respect to a global benchmarking. The closer you are to 0, the better you are. And if you see on this chart, and we have been participating in the last 4 or 5 cycles, you know, over 2 years, and anything which is within ±2 is actually satisfactory. And the closer you move to 0, the better you are getting. So everything is acceptable, but then even when everything is acceptable, you are excelling in what you are doing. So that is what this conveys, that, you know, as and when we run more and more tests and improve the way we run the tests, we get better with each cycle. So this is one of the ways we would be running these experiments to establish statistical analysis and repeatability and reproducibility of data. Right? Of course, so this is one of the examples, but let's look at another example. So early on, the first case study talked about materials at high temperatures. And when we look at what kind of standards are available for high temperature testing, if you are interested to know, you will find that there are not really a lot of standards which talk about testing at 1000 degrees, just because it's a very niche area. You know, there are challenges associated with an instrument and setting up a test at 1000 degrees. And what we have done is, with the limited standards, we have tried to get what are called as reference materials. So what is a reference material? A reference material, so we know what is a reference material for hardness testing, right? So if you do a simple hardness testing, you would put a steel block of a known hardness, you run the, Rockwell or Brinell hardness, you get that value, then you put your material and see what that value is. So there is a reference material for which the value is known. And such materials are not there for 1000 degrees. So what we have done is of course, this shows you the high temperature tribometer and the test running at about 900 plus degrees, close to 1000 degrees. And we have run close to, several hundreds of tests at high temperature, both at room and high temperature on different materials. So why different materials is to capture how metallic materials behave and how ceramic materials behave. So again, what is shown here is the friction and wear, and the materials which are used are, let's say, sapphire, is one of the counterface, and the other material against which it rubs could be, silicon nitride, which is again a high temperature ceramic, or Inconel 725, which is a high temperature superalloy. So we have established these reference materials, done a lot of tests to set up what I would say the precision limits of friction and wear at 1000 degrees. So what that means is, if these materials were to be run in another lab, we believe that the results of friction and wear at 1000 degrees would be within the bounds what is shown by this graph. And why is that important? Because then you got a good benchmarking. Your results are repeatable and reproducible, not only in your lab, but in other labs, who conduct similar tests. So that's the power of having these, I would say, these precision limits. And there is some more data here which shows the scatter with the bar graph. So these limits are very important for 1000 degrees tribology, right? So now we started with the material discoveries, and then the power of being able to repeat and reproduce, and that requires a lot of data, right? Handling data, managing data, looking at data, statistical correlation of data. Then how do you look at, do we see that as a daily job that you have to sit down and look at it? Yes, you could do that, but then that is not an effective utilization of what we call as creative thinking. And our planet does need more creative scientists, because we want to come up with new ideas, new ways of solving the problems than doing data management. So let me play this video to give you the inspiration behind what we call as a digital platform. So the problem is, we need data in order to have faith in our inventions. We need data to be analyzed. We need to establish the repeatability, reproducibility of the data and the precision limits. But then if we go down the path, a lot of time is being spent in order to do it. So can Industry 4.0 technologies like automation, data analysis, digital twins, can all of them help? Can all of these technologies somehow help in the day-to-day activities which we do as part of research, scientific research, right? And that's where, what the smart tribology becomes very important. So smart, in this case, you can consider it as your smartphone. We have taken it for granted just because it's so seamless to use, right? We use it in our day-to-day lives effectively, to schedule meetings, to connect, to collaborate with people, to have group calls, to exchange notes. And it even comes with inbuilt sensors, which tells, your phone needs to be charged because the battery is, you're either you're out of memory, right? You have just too many files. You have to clean your junk files, clean your cache, or your battery is running low, right? These are simple things which we have taken for granted, but what is the equivalent of that for a tribometer? So can a tribometer be smart enough to come up with sensors which helps you monitor the health? tell you when it needs to be maintained, tell you when it needs to be serviced. So you tell you when it needs to be calibrated. So you don't have to worry about it. It's just something which is enabled. Then the next question comes is, any instrument you test, you generate a lot of data, right? And the data has to be processed, right? You have to export the data. What if you could do all of that data analysis without really having to worry about basic knowledge of statistics is important, but you don't have to worry about a lot of how the statistical procedure is implemented, right? Because you want to get to the data part, the exciting part about your data, then worry about the process. So that's where the kind of Industry 4.0 technologies which are being used either in manufacturing or healthcare or in all the other industries, but really having that at the core of something which is there in your lab, it has been missing. So what we think is this could be a disruption in how you could bring 4.0 technologies into scientific processes which you run in the lab. So I'll play this video again of how we think it could enable or transform the way people learn, people process information, and people handle data. So this was a small snippet. I just kind of wanted to highlight the problem, then give you the solution. It's not intended to be a pitch of our products, but highlighting what the problem is and the fact that you could always reach out to us if you want to know more in depth about this platform. So it combines a lot of different technologies, which comes with connected sensors, and then you can get the raw data. You can use data visualization techniques and a lot of AI algorithms to help analyze your data better. And then a lot of information is available, so I will not cover that. So this brings me to the end of the presentation, and I believe we have got some time, 5 to 10 minutes for question and answer. Thank you. So, yeah, Dr. Ajay, I think I have completed before time in the interest so that we can have any discussions and questions.
Yes, definitely. Yeah, thank you so much, Dr. Petro. Yeah, now I request all the participants, if they have any question regarding Dr. Petro's talk, we can discuss. Any question? Any question from participant? Yeah, I think Dr. Petro, participants don't have any question. I think they will be tired a little bit. From morning, they are listening all the lectures. They will be a little tired, I think. Right?
Sure,
but
I understand. Yeah. But anybody, they have the email address and they have the company. So
yes.
Anything which comes to them later on, they are feel
definitely.
Us or anybody at DUCOM for any doubts.
Yeah, it was really, you have given all the information about the basic and philosophical views about the tribology and the latest development and smart tribology basically. And as I mentioned that we have also started the course on tribology and surface engineering.
Right.
And we are also communicating that now we are going to develop a strong tribology lab at IIT Tirupati. So we will continue our discussion and look forward to see you again.
Sure, Dr. Ajay Kumar, and thank you for the invitation.
Yeah, thank you so much. Thank you so much. Yeah. Yeah. So dear participant, now we have another talk by Chintan Bhatt. Chintan Bhatt, Mr. Chintan Bhatt, are you there? Yeah, Chintanji, are you there? Chintanji, are you there? Yeah. Can you please unmute your mic or? No. Can you go to setting and see whether it is in problem? Yeah. No. Yeah. Now it's audible. Yeah. So yeah. So we have Mr. Chintan Bhatt from Anton Park, and he has expertise in the area of again in the area of tribology and related areas. So I welcome Mr. Chintan Bhatt for joining us today, and we look forward to listen to you. So I request Chintan Bhatt to give your presentation, and over to you.
Thank you. Thank you, Ajay, for this invitation and speaking to the audience, the conference or the webinar which the IIT Tirupati has organized for the audiences who are interested in understanding the recent trends in material processing as well as the characterization side. Let me give my background. I am a PhD from IISc Bangalore with instrumentation engineering background, and I have almost 10 years of experience in R&D for mainly the surface mechanical property characterization instrumentation. So it's nice that we should interact. This kind of interactive sessions, right, is always good for the audiences, new students. So without wasting our time, let me start my presentation. Just a minute.
I think, Dr. Chintan, you can share your screen, right?
Yes. I'll have to share my screen. Just a minute.
Yeah, right.
Can you see the my
yeah,
slide?
We can see. Yeah.
All right. Good.
Thank you.
So,
thank you.
Right. Okay. So basically, I will be talking about the recent developments in nanomechanical property characterization, and mainly I'll be focusing on the surface property characterization, and I will also be much focused on a specific technique. So let us start our presentation. What I'll be talking about in today's presentation is why to study surface properties. I'm not sure whether this topic or the content may be repeatable, but I would rather go through this because it is important when we move on to the technique which we are talking about. So I will talk about why to study surface properties, particularly at nanoscale. What are the conventional technologies and the present scenario. Then I will be moving on to a technique called instrumented indentation technique, which is also referred as nano indentation technique, basic building blocks of nano indenter instrumentation aspect of it. Then I will be talking about more on the technique, which is again a very specific, I will say quasi-static nano indentation, because there are other way of doing the nano indentation experiment, which is a dynamic. Okay, so there are classification of nano indentation technique. One is quasi-static, another is dynamic. But if I'll go with the dynamic, it will take another 1 hour time. So I've excluded that technique in this presentation, but I will be talking more about the quasi-static nano indentation technique. The most important thing that people knows about nano indentation technique, but then it is very important that how to utilize the this instrument. Okay, people can operate the instrument. Okay, but the utilization of the instrument is very, very important. Okay, so I will be talking about that aspect, means major practical considerations when you are actually utilizing this technique and instruments, how to set up the experiments, and how will you validate your data out of the experiments. Then I'll be talking about brief case studies, mainly the soft samples, particularly biological samples, and then summarize the whole presentation. So let's talk about the surface properties. The surface properties are mainly the why we study surface properties, because surfaces are the part of the body or an object or a material which is exposed to the external environment. Okay, and how this surfaces will interact with this external environment will determine the shelf life of the product or a material. So it is very, very important to understand by a developer, researcher, or a manufacturer to understand that how these surfaces will interact with the external environment. Okay, so the behavior. Okay, how will you come to know that what kind of interaction will be there? Okay, so for me, I will classify the interaction will be in two different categories: constructive interface as well as the destructive interface. So I will just classify into two categories. So the constructive interface, when I say, is the interface where the purpose of the surfaces or the behavior of the surfaces meets the requirement of the environment. Okay, so I would say this kind of interface will be a constructive interface. The destructive interface is the interface where the surface, right, will not behave normally in the existing environment. Okay, so then what will happen is the material will fail. Okay, so the failure happens and the product or a material will not survive for a longer period of time in that particular environment because the interface is a destructive interface. How somebody can predict, okay, because you are the researchers or manufacturers, right, they are actually manufacturing something with some ideas in their mind or a thought process that I want to implement this particular thing into this specific environment, and it should work in a better manner, right? Because everybody in today's world, right, everybody wants to do something which is unique, new, and improves the what do you say, life of the society. Okay, so everybody wants to contribute somehow to better the life of the society. So wants to build new things every day. Okay, so now in that reference, it is very important for the manufacturer or researcher to identify before, right, before the product or material goes into the application, what they have to predict is that the interface will be a constructive interface, right? And what decides whether the interface will be constructive is the behavior of the surfaces. Okay, the behavior of the surfaces will determine whether the interface will be constructive or a destructive. Now, who determines the behavior of the surfaces? Its characteristics. Okay, so properties of the surfaces will basically determines the behavior of the material, and the behavior of the material will determine whether the interface will be constructive or a destructive. So it is very, very important for anybody to really study the properties of the surfaces before this product or a material goes into a real-time applications. That is why the surface property characterization is must. Now, when we say properties of the surfaces, when we say property of the surfaces, we should also need to classify the properties. Okay, which properties we need to study, which property we need to characterize. Okay, it depends on the environment where the product or material is going to be implemented. Okay? If the environment is electrical environment, right, then the surface property which are important will be the electrical properties. If the material or a product is going into a temperature environment, thermal environment, right, then the thermal property is important. If it goes to the automotive sector, aerospace, right, then the mechanical properties of the surfaces are important. So people has to identify the environment, means application. Okay, based on the applications, they can identify which are the important properties. Okay, and then based on that, people has to have a tool, okay, characterization tool to characterize the property of the surfaces. So it is very, very important to study the surface properties and then in terms of what applications you have. Why? The second question is that why we need to study at nanoscale then? Okay, we are talking about the surface properties. Now we are actually making it very focused. Okay, very much bringing it to a very closer, like to the length scale, right? We say why we study at the nanoscale. The surface property we need to study at nanoscale because we have found that the mechanical property of a small volumes is different as compared to the properties of a bulk material. Okay, and if you see the graph on the right hand side, right, which actually is a combined graph which has been taken from the like sort of literature together. Okay, and every literature has been the data has been put it together. Okay, as a strength and the size of the particle. So if you see that when the size decreases, right, the strength of the material increases. So people has given a statement that smaller is stronger. Now we know that if when the volume has become small and small, right, the strength of the material increases. So when we are talking about the mechanical properties, strength is one of the important behavior of the material. So people will get like fascinated that, okay, so if we are making this material smaller, right, we are getting a better strength. Let's do that. Okay. So now when people talk about that, when what are the benefits of the nanometer length scale structures? Okay. So when we say nanoscale engineering makes the material lighter, stronger, cheaper, and more recyclable. Okay. So these are a couple of things that are the outcomes or the conclusions of various researchers has come out with. Okay, and so now when these things are out into the market, right, everybody, all the manufacturers, right, or the researchers will want to try to get to this particular aspect. Okay, these are very fascinating statements, right? And like I just want to go and do this. Okay, let me make a let's build something which is nanoscale. Okay, now when we talk about the nanoscale, right, all the materials nanoscale properties are not out. Okay, it's not available. Okay, so when you are trying to go down to a nanometer length scale for a specific material, right, people has to understand, okay, the behavior of the material at a nanoscale length scale. Okay, so the properties of nanoscale material influences the performance, lifetime, durability of a commercial system. This is another statement. When I say this, right, manufacturer will jump and start doing something in that direction. Okay, but then the manufacturers or researchers doesn't have a very standardized processes to basically building this material, which is at nanometer length scale. Okay, so everybody will go and identify one particular processes and wants to build some material at nanometer land scale. Okay, one uses the different process, another use another process, third one uses the third process, and all these three people, right, are working on the same material. Okay, now the processes are different, material is same, the outcome which is there is also a nanometer land scale structure out of that particular same material. Now, when people will try to apply into an application or the environment, right, this material will behave differently. Though the material is same, size and structure is same, okay, but the behavior is different. Okay, why it is so? It also depends on the processes then. Okay, so people has to really understand that aspect of nano structures. Okay, that the processes which you are following to build a nanostructures, right, is also a process dependent. Okay, manufacturing process dependency is also there. Now, when I say process dependence, right, then the process parameter also comes in picture. If your process parameters are not same, then also your behavior will be different. So when we talk about nanometer or nanostructures, right, they are really fascinating structures, but then they are also very, very sensitive towards the processes and process parameters. So one has to understand that particular thing before they really get into this manufacturing nanostructures. People can build nanostructures, but the properties that they are expecting from that will be process dependent. So we have to make sure that the processes are selected in a right manner. How will you come to know that the properties are as per the expectations or not? So you are having a tools, okay, which you will characterize the properties of these nanostructures, right? You will try to see whether these properties are matching with your requirement or not. If not, right, you again optimize your processes, okay, and come back with another round of the nanostructures, again characterize it, okay, match it with your standards, like, or match it with your applications. If not, then again you have to go with a process parameter optimization. So it's basically a cycle. Okay, manufacture, okay, characterize, okay, compare, and then again you do a processing. Once it matches, your process parameters are optimized, okay, and then you move on and start production of that particular material straight away. For that, you need some kind of a characterization tools, right? And when we talk about the nanometer length scale, there are specific characterization tools which are important. Now, when we will actually characterize the nanometer length scale properties, right, it will also helps you to basically connect with your bulk properties. So when you use these characterization tools to study nanometer length scale properties, right, but there are also conventional technology available in the market, right, which studies the bulk properties of the same material, right? So now you will have a scale connectivity, okay, between the nanometer length scale and the bulk. So that is also a very interesting outcome of this kind of characterization. It will also help us to identify the failure, okay, and the quality of your material which has been manufactured. Let's talk about the mechanical properties. As I mentioned previously, that we will more focus on the mechanical property characterization, right? So when we talk about mechanical properties, right, we should know what is the mechanical behavior of the material, right? So I'm sure a lot of people in the audience may be having a similar background, right? Mechanical or material science background, right? They must be having this information for sure, right? The material exhibits three different types of behavior under stresses, all right? One is elastic, plastic, and the failure, okay? So now the behavior of the material will be in between this particular stress strain curve, okay? So the behavior, whether the material is elastic, plastic, or it will fail, right, depends on this particular curve. Everybody knows about it. Now we are also interested. So who will tell whether the material will be the elastic, plastic, or there will be a fracture? Okay, so we should know which are the properties of importance to determine this behavior, right? So the mechanical properties are usually divided into like conventionally hardness and the elastic modulus of the material are important properties, which basically helps us to understand this behavior of stress strain curve. Okay, so the hardness is basically a measure of resistance of a metal or a material to a plastic deformation. So the hardness is basically an indication to a plastic deformation. So it will give the information about the plasticity of the material. Elastic modulus, right, is a property which determines the recovery from a permanent deformation. Okay, so when you deform a material, right, you apply some stress, right, so material will deform, and when you release the stresses, right, material will try to recover some of its properties. So that recovery information will be provided by the elastic modulus, and that is nothing but the information about the elasticity of the material. So hardness gives the information about plasticity, and elastic modulus gives the information about the elasticity of the material. So now, if we talk about the conventional property, this property measurement instruments, right? We know that there are Brinell test, Rockwell test, Duiker test, and so on. So there are different techniques which are existing for measuring the hardness of the material. Now, if you look at these techniques, right, these techniques depends on the load that you have applied during the puncturing the sample surface, right? And then once the experiment is over, you take the sample under the optical microscope, right? Just like you are seeing on the right hand side bottom, right? You are seeing some indentation imprint, okay, residual imprint of the indent which has been made through some indenter, right? You use an optical microscope, you find out the geometrical parameters, right, and use these geometrical parameters from this optical image and put it in a standard equations which are determined for various tests, okay, with reference to the maximum load. You will be able to find out the hardness value. So we have a HV, we call it weaker hardness, Brinell hardness, and stuff like that. Okay, so these are all basically the numbers. Okay, there are no as such very specific unit. People talks about numbers, right? So HV is this, HV is this, something like that. Okay, but there are some restrictions with this conventional hardness testing. These techniques are mainly used for the bulk material properties of the bulk material. So it's very, very difficult to characterize nanometer length scale objects. Okay, so it will be very difficult for the regular people or the conventional hardness testers to study the properties at nanometer length scale or a nanometer length scale structures. So in that reference, one more important thing is that the hardness testers, right, measures the hardness value, and the elastic modulus, you have a tensile testers. So the one single instrument is not going to give you an information about the both the behavior, elastic behavior or a plastic behavior. Okay, so you have to have another instrument called tensile testers, which will give you an information about the elastic properties. The hardness tester gives you about information about the plastic information about the sample. So you have to have two separate instruments to study two different properties. So it's very important. Okay, so as I mentioned, there are some limitations of the conventional measurement techniques, particularly when we talk about the nanostructure material properties. Okay, we are unable to measure what are the limitations? That the large uncertainty due to the limitations of the optical resolution of optical microscope. Okay, when we talk about the nanometer length scale imprints, right, the resolution of the optical microscope will not be sufficient to see that particular imprint, okay, to identify their dimensional information. So it is a biggest limitation for the conventional measurement technique, which is not sufficient. Second thing, which is that you have to have a two separate instrument for identifying the two separate parametric properties from the surfaces. And the third one, which is again very, very important, is that you are not recording the data during the experiment. Okay, so when you are loading the indenter on the sample, right, and you are unloading the sample, unloading the indenter, right, so the loading and unloading cycle, you are not continuously monitoring any parameter during this experiment. And as you are not monitoring anything, you will not be able to identify some of the events that is going to take place during this experiment. Okay, so these are a couple of things which is very, very important when we talk about the nanometer length scale characterization. So the conventional techniques will not be able to use full for this kind of technique. So in that reference, people had to come up with a new technique, okay, which is nothing but instrumented indentation technique, which has been introduced like almost 2 decades before. People are utilizing this very efficiently now. So it is referred as two to three different names are there. People talks about the depth sensing indentation. People talks about instrumented indentation, nano indentation. So if you are hearing any of these words, right, it is nothing but the same technique which I am talking about today. So what we are exactly doing in this technique is that we are actually doing the similar experiment which the actual hardness tester is doing. But here, what we are doing is that we are actually monitoring or recording the data during the cycle of the experiment, means loading cycle and unloading cycle. Whatever the force that we are applying on the sample, we are continuously monitoring that force, okay, and the associated displacement that is happening on the sample surface. So I would say we are monitoring and recording the force and displacement data during the indentation cycle. I will store this data, and then at the end of the experiment, I will plot this data against each other, as you are seeing on the right hand side graph. This is a force and displacement data, loading and unloading. Now this particular graph that you are having is one of the is the most powerful graph, I would say, because this graph is going to give you a hell lot of information about the sample behavior, okay, about the elasticity, plasticity, failure, and stuff like that. Many more. I will just come to that particular point soon. So the hardness and elastic modulus will be, so whatever the properties that we are talking about in my previous slide, right, a hardness and elastic modulus, we will be able to calculate directly from this resultant curve, okay, force displacement curve. I will explain how we are going to calculate this, or how we are going to get these numbers, okay. So this is the technique which will help you to characterize the hardness and modulus value straight away from the experiment. So this is a nano indentation technique. Now, if we talk about the instrumentation part, right, as I mentioned, what exactly we are doing in this experiment, that we are applying a load, right, and we are measuring the displacement, okay, during the complete indentation experiment. So what we are doing is that the instrumentation, right, depends on what kind of functionality that you are looking for from the experiments, right? So if you see here, the instrumented indentation instrument will be generally looks like this, okay. So it is a block diagram, right, where I can show you that what, so there will be a force actuation mechanism, displacement measurement mechanism. So the force actuation mechanism will apply the force, okay. The displacement measurement mechanism will measure the displacement during the indentation experiment. You need an indenter shaft, okay, and then the shaft is holding an indenter tip. Okay? And this tip will be in contact with the sample under the investigation. Now you want to you don't want to do the indentation experiment every time at one specific location. You have to move across the sample, right? You want to move to a different locations and to see whether your data is repeatable or not, right? So you have to move your sample across the lateral direction, means X and Y direction, right? So you have to have an XY platform for holding the sample. This XY platform will move the sample in X and Y direction, right, to a different locations, and you want to conduct experiment at different locations. And the whole platform has to be supported by a very stiff frame. Okay, so you need a supportive frame for that. Okay, and that supportive frame has to be very, very stiff as compared to the whole mechanism. If it is not too stiff, you will have a compliance. Okay, it will be too much scientific. I'm going, so please bear with me, but yeah, it is important that your frame has to be very, very stiff. And now, as we are talking about the nanometer length scale displacement, right, we have to be very, very careful about the building vibrations, noise, which is mechanical noise, basically, which is reaching out to the interface. Okay, so you have to have a vibration isolation platform, whether it is a passive isolation or an active isolation platform would be sufficient, depending on where exactly you are installing your instrument. So either you can select a passive isolation or an active isolation platform. So this is how the whole instrument looks like. So you will have a force mechanism, okay, actuation mechanism, displacement measurement mechanism, indenter, the frame, and isolation platform. Once you have all this, right, your system this is a very generalized block diagram of indentation test. There are various indenters geometries available in the market. People can select any of these geometries depending on what kind of applications or what kind of characterizations that you are looking for. The most popular indentation geometry is a Berkovich geometry. If you can see on the left and top right side, left side, Berkovich geometry is the most popular geometry for the instrumented indentation experiments. Because there, okay, cube corner, flat punch. So if somebody wants to do only compression test, people will go with the flat punch one. People wants to have what do you say, unified areas across, or you want to create a stress distribution has to be uniform, right? Then people go with the spheroconical or a conical geometry. People, if wants to study the fracture toughness, people will go with the cube corner, okay, because it's the sharpest geometry of all. So that will create a lot of stresses on the surfaces. So will create cracks during the experiment, and which will help us to find out the fracture toughness of the sample. So as I mentioned, various geometries are available, and that depends on what kind of test or characterization that you are looking for. So how basically instrumented indentation technique works. So here is a small animation here. You can see that there are 3 different experiments we are conducting. The first graph that you are seeing shows the perfect elastic recovery. Okay, means the loading and unloading cycle curve, right, follows each other. So there is no hysteresis in that. It means that the behavior of the material is purely elastic. If you see the second one, where there's hardly any recovery after the loading cycle, right, there's hardly any recovery happening on the surfaces. It means that this material will be a highly plastic material. Okay, so the deformation is maximum, so the plastic material. If you see the third graph, where you will see some percentage of recovery, okay, but then it is not exactly coming back to the 0 position. It means that there is a deformation and there is a recovery both. So it means that the material behaves as an elastoplastic material. So these are the straightaway observations that you can make with the curve, which you have got from the experiment, whether the material is elastic, plastic, or elastoplastic. So that is the first information that you can get out of these experiments. So these are the typical material responses. Okay, the first three I have already discussed. Okay, in the previous slide, we know elastic, elastoplastic, and plastic behavior. But if you see at the bottom three, right, which has a very unique thing in their loading and unloading cycles. So if you see the D curve, right, where you can see some kind of a pop-out event during the unloading phase, right, which is basically people refer it as a phase change behavior. So if you are seeing this kind of behavior in your load displacement curve, right, which has something to do with the phase change in the material. Okay, so if you really compare the conventional testing where you are unable to record this loading unloading data, right? But there may be a possibility that in that particular experiment also this kind of events were happening, right? But we cannot monitor that in the conventional techniques, right? So you will not be able to see this kind of things with the conventional technique. So this is another benefit that you have it with this kind of technique. Okay, so I don't want to get into too much detail about this graph, but we have an example of the silicon. Okay, if somebody is interested to understand this, I can discuss later, or they can approach me later as well, where we have conducted some experiment with the silicon where we have seen this kind of phase change behavior. Okay, interesting thing is that silicon, we all know that silicon is a semiconducting material, right? But we never knew that the silicon can also become a metal. Okay, so this kind of experiment helped us to understand that behavior of the silicon. That silicon has been transformed from a semiconducting material to a metallic material. Okay, so the D response, right, is mainly I'm referring in terms of the silicon material. So there is a E shape, right, where you are seeing the pop-in events, right? This pop-in events is mainly the cracks that is forming during the, so that refers to a fracture toughness behavior of the material when you are using a tube corner tip and you conduct an experiment on a glass or something, right? You will be able to see this kind of behavior. Okay, so these pop-in events are mainly due to the cracks or a failure mechanism. And the last one, F graph, is nothing but a creep behavior. Okay, so the creeps are the responses of very, very soft materials. Okay, I don't say that it is not existing with the metallic material. It also exists present. The creep is also present with the metallic samples. Okay, we have observed in the aluminum with my experience with a similar technique. We have observed the creep in aluminum as well. Okay, so creep is not only specifically for the very, very soft material, but it also present in a metallic phase, metallic material as well. So these are the typical responses that people come across during the indentation experiment. So let us talk about that, how we will extract the information of elastic modulus and hardness from the indentation experiment. Okay. So there are people, Oliver and Farr, who has actually identified the model for how to extract the information about the modulus and hardness from the indentation experiment. And they have come up with these two equations, which you are seeing in the right hand side. So if you see the elastic modulus, right, elastic modulus is a function of S and AC. Okay, S and AC. AC is nothing but a projected contact area of the imprint. Okay, what we know about the imprints, right? When we indent, right, there will be an impression on the sample surface, and that area of that impression, right, we refer it as a projected contact area. Okay, so then S. S is what here? Okay, S is nothing but the stiffness. Okay, so how I will be going to get this projected contact area and the stiffness? Okay, then if I know S and AC, I will be able to calculate the elastic modulus. The another equation is the hardness. Hardness is a function of maximum force. Okay, P max is nothing but a maximum force divided by projected contact area. So how I will get these numbers, okay, from the experiment, and how I will be able to calculate. Okay, so I've shown this graph before. So I have a load displacement data. I plot it against each other. Okay, and then I'm getting this particular curve. So what I will be doing is I will be linear fitting the unloading curve. Okay, I will linear fit the unloading curve, and that linear fit will give me a slope value. Okay, will give me some number of the slope. Right, slope is what? Is a dp by dh. Dp by dh is nothing but a stiffness, right? Load divided by displacement. A difference in force against the difference in displacement is nothing but stiffness, right? So I'm getting the S from this particular slope curve. Linear fitting of the unloading curve gives me the stiffness value. Okay, this I'll talk a little later. Okay, now the projected contact area, which I'm talking about, right, is basically you cannot, you don't have any facility of microscope here, right? So that you can see the impression, calculate the dimensional information from there, and you find out what is the contact area, which is impossible in this case, right? So now how we will be able to calculate this projected contact area then, right? Only thing I can tell you at present with this slide is that this projected contact area is a function of contact depth. The contact depth that you are getting is basically from your indentation graph. I will tell you in the next slide, next slide, right, how you are calculating the contact depth. Okay, and then what is the relationship between the contact depth and the contact area? How will you calculate that? I will talk about that. So how we are doing this extraction of the property from the experiment, right? So I did the indentation experiment. I got the load displacement curve, and when I linear fit the unloading curve, I got the stiffness. Okay, now I got the stiffness. How I will calculate the contact depth? Okay, so the contact depth, right, has a relationship with the maximum depth, okay, maximum force, and the stiffness. So this is a equation defined by the Oliver and Farr. So I know what is the maximum contact depth from the experiment. Okay, HM you are getting from here. Okay, what is the maximum FM that you are getting from the curve? Okay, so now you have HM, you have FM, and you have a stiffness. This epsilon, which is in front of the FM by S, right, is a function of the geometry of your indenter, and that number is fixed. Okay, which is a constant number. If you have a Berkovich, it will be around 0.75. Okay, so similar way, if you have a different geometry, you will have a different number of epsilon there. Okay, I'll try to see if I have that particular chart with me where I can show you these numbers. But yeah, so now you have HM, FM, S, and epsilon. You put these numbers into this equation, you will get the contact depth. Once you get the contact depth, the relationship between the contact area and contact depth is straight away like this. AP is equal to C0 into HC square. Okay, this equation, again, I would say that this equation is for the Berkovich geometry. This relationship will change with the different geometry of indenter. This relationship is for the Berkovich geometry. So AP is equal to C0 HC square. For the Berkovich, C0 value is nothing but is a constant 24.5. So now I have HC value, which I calculated from here. I know what is C0, which is 24.5. So I will multiply 24.5 into HC square, will give me a projected contact area value. So I am not actually monitoring the imprint of the indentation imprint from any other other instrument like microscope and all, but I'm straight away calculating this contacted area from this particular experiment data. Now I have AP, projected contact area, right? Steepness also I know. Now I have everything with me to get a value of reduced modulus and the hardness of the material. Okay. So this is how basically we will be able to extract the mechanical properties from this indentation experiment. Okay. So with this, I would like to straight away go to some particular practical considerations. Okay. Now, when I have shown this particular exercise, right, how to extract the properties, people would be very happy. Oh wow, this is pretty simple, as simple as that. Okay, let's do the indentation experiment. We'll do the we will unload with the unloading curve, get stiffness, got maximum depth and everything. We put this value, we'll get the modulus hardness value. Now I will just ask the question: whatever the value that you have got for the from the experiment, right, hardness or reduced modulus, is it valid? Is it a true value for your sample? Because, right, your material is new, okay, in nature. New in nature means that people have not done the have not characterized such material before in terms of mechanical properties, right? So the properties are unknown, right? So for the new materials, right, properties are unknown. Okay, so whatever the value that you are getting, how will you validate that? How will you validate whether the modulus and hardness value you got is true, right? Yes, it's a very big question actually, particularly when you are working with an unknown sample, right? So I have some couple of tips, I would say practical considerations that somebody has to taken care of during the experiment, which will help them to make sure that your data is valid. Whatever the values that you have calculated is a correct value. Okay, there is no as such any problem with that. Okay, so which are the factors? So first of all, I should know which are the factors which will basically affect, okay, the real values. So these factors are listed on the left hand side. Okay, thermal drift. One very important thing is the thermal drift, initial penetration depth, instrument compliance, indenter geometry, pile up and sinking in, indentation size effect, and the surface roughness. These are the various factors which somebody has to understand when they are actually doing this kind of experiments. Okay. So what I will be doing is that I will be taking up some of these things, and then let us move forward with this understanding that how we will really minimize or try to see that we can get rid of these factors so that there won't be any effect on the actual measurements. So first parameters one should handle in this reference should be the indentation penetration depth. Okay, and indentation penetration depth. When I say indentation penetration depth is an HM. I'll just go back to my previous slide, right? And if you see, right, the first equation that I have, HC is a function of HM, FM, and S. So HC is highly influenced by the HM. HM has to be accurately measured. Okay. How will you do that? HM is the maximum penetration depth. We have to calculate this, or we have to monitor that we are not having any influence of anything in this HM. Okay. So what are the factors that influence this HM? Are the thermal drift and initial penetration depth. Second parameter one should handle should be the stiffness. Okay. One is HM and another is the stiffness. If we have not corrected this HM and stiffness in this measurement or in this calculation, you are going to end up calculating a different HC, means different contact depth. Different contact depth will give you a different contact area. And if you have a different contact area, both of this hardness and elastic modulus will be different. Okay, so you have to make sure that your HM and stiffness has to be accurately measured. Okay, so now as I mentioned, the contact depth is a function of this. It is a repeatable repeat of my previous slide, so I will not go into that. Okay, so first parameter that is influencing the HM is the thermal drift. Thermal drift means every system flows. Okay, every system may have a thermal gradient. Okay, and as with respect to the temperature, right, the system will displace. Okay, whether it is an electronics or a mechanical system, electronic system or a mechanical system will have a drift associated with any of this mechanism. So even if in a stationary position, right, some kind of a displacement will be happening on the mechanical system, and that displacement, right, as we already know that on our instrumented indentation tester instrument, right, we have a displacement measurement mechanism. So now if the system is displacing, this displacement measurement mechanism will measure that displacement as well, which is due to the drift. Though the system is not moving, so my indentation experiment is not happening, my tip is in contact with the sample surface, right, but I'm not performing any indentation experiment, but there will be a displacement due to the drift, and that displacement will be monitored by my measurement mechanism, right? Now when I'm actually performing the indentation experiment, the displacement that has happened due to the drift will also get added to your actual displacement measurement, right? So you have to be very, very careful. So if my the drift, right, is something around 20 nanometer, right, and my indentation displacement is 100 nanometer, then the actual system is monitoring 120 nanometer displacement. The 100 nanometer is due to the indentation experiment and 20 nanometer is due to the thermal drift. So you are adding these two, which makes it to 120 nanometer. 120 nanometer is the maximum displacement. So as I mentioned, if you put this number into the HC, right, it will be a different number. So you will be actually ending up with a wrong calculation of modulus and hardness. Okay, so there are two ways of doing it. One, that people do the correction in the data after the indentation experiment has been performed. Okay, so what they are doing is people do the drift monitoring before they start the experiment. Okay, so people brings the tip in contact with the sample surface, keeps it there for some few seconds. Few seconds means it varies from 40 to 90 seconds. People keep it in contact with the sample, and then during that 40 to 90 seconds, people will monitor the displacement as a function of time. Okay, as you are seeing on the left hand side, right, there is a displacement and there is a time. So this displacement is increasing with respect to time, which is nothing but a drift. So if you take a slope value of this, right, which will tell you the drift rate, that this number x nanometer per second is my drift rate. Now, after that particular 90 seconds, my indentation experiment starts. And I will complete the experiment. After completing the experiment, I will collect all the data. And what I will be doing is, I will correct all the points. Okay, I will subtract all these points with this drift rate number. Okay, so that I will be correcting the drift into the data. So I will see that there is no drift in the data. So I'm eliminating the drift from the actual data. Now my question is that, is it the right way or right approach to correct the drift, or there is another approach where people should monitor the drift during the experiment? Okay, when you are actually doing the experiment, you should monitor the drift, okay, and correct it in a real time. Okay, because see, in this traditional approach where people are monitoring the drift rate before the experiment and correcting after the experiment, right? I'm not sure whether the trend, okay, the slope that I'm talking about, which they have monitored, right, is going to be the same when it is actually in contact with the sample. Okay, during the experiment, whether this drift will remain, the slope will remain same or not, I'm not sure about it. Okay, so in that reference, to make sure that you are correcting the drift in a real time is the most important consideration. Okay, people should do a real time drift correction during the experiment, not before before they measure and correct it after the experiment. The measurement and correction has to happen during the experiment. Okay, so there can be another mechanism, right, which you can actually see. So there is a conventional indentation tester. If you see on the left hand side, right, is a very conventional technique where people do the monitoring of drift before the experiment and correct it after the experiment. There is another approach on the right hand side where people can have some kind of a referencing mechanism. Okay, so there is I would say another indenter which is also sitting on the same sample. Okay, but that indenter will not be actually performing the indentation experiment. It will just stay there on the sample during the indentation experiment and monitors the drift during the indentation experiment. Okay, as the indenter and this referencing indenter both will be experiencing the same drift, right? Because both of these are placed on the same platform, right, on the same sample surface. Both of them will be experiencing the same type of thermal drift. One is not moving, another will be moving. So indenter will be definitely moving in the sample during the experiment. Okay, but the displacement which is happening due to the thermal drift will be monitored by the referencing mechanism which is on the side blocks. Okay, this will monitor that displacement during the indentation experiment, and I am taking the differential signal across the main indenter and the referencing indenter. So if I take a differential signal between these two, right, what I will be having is the actual displacement that is happening due to the indentation experiment. So whatever the 20 nanometer which I was referring in my last example, right, both of these indenter is experiencing 20 nanometer displacement. But what I'm doing in a real time is that this 20 nanometer, right, with the referencing mechanism, I'm subtracting from the actual indentation displacement. So the actual indentation displacement is happening 120, okay, but then referencing also is happening 20. So what I'll be doing is 120 minus 20. So effectively, I will be monitoring only 100 nanometer, which is an actual displacement that has happened during the experiment. And that is happening during the real-time scenario. So this is a very interesting technique which people have come up with, and will be very, very useful, particularly when people talks about the creep study. Okay, because creep is another behavior where the material flows under the constant load. Okay, and when material flows, there will be an associated displacement or deformation. Okay, under the constant load, and that displacement has to be monitored over a period of time. Creep is basically a time-dependent property of a material. So now we have to monitor this creep as a function of time, right? And if there is a thermal drift, right, which is also basically introduce a displacement under the constant load, right? So people has to really figure out whether the displacement is due to the creep or due to the thermal drift, right? So if you have a mechanism, something like this on your platform, right, which is actually correcting the displacement, correcting the thermal drift displacement in a real time, right, would be a very good solution to make sure that the user is actually monitoring the creep behavior only and not the thermal drift. Okay, so it's very, very important. Then second parameter which is important to make sure that your maximum penetration depth is correct is the initial penetration depth. What is this initial penetration depth all about? The people who have worked with indentation technique, what we are doing is that we are bringing the tip on the surface, okay, keep the and maintain some contact between the tip and the sample surface, okay. And for to maintaining this contact form, right, you have to apply a small force on the samples, okay, to make sure that your tip is in contact with the surface. So when you apply a small force, there will be a associated displacement in the sample. Okay, so that minimum force, right, will make the indenter displace into the sample, a small displacement. Okay, that displacement, right, is referred as the initial penetration depth. This initial penetration depth will be always constant. This is not going to deviate during the experiment. It will be as it is. I would say it is an offset. Okay, and that depends on the initial load that you are applying to the surface. Okay, so we should know what is this initial penetration depth. If I know initial penetration depth, I will be again correct that particular number from the maximum penetration depth, and then I'm making sure that my maximum penetration depth is accurate. So I have no thermal drift involved in my sample. Okay, in my system, thermal drift is corrected using a referencing mechanism. I have also calculate. I know what is the initial penetration depth. Okay, so I will subtract it from the maximum penetration depth, and I will be making sure that my HM is accurate. Now we have corrected the effect of thermal drift and initial penetration depth, and now we are sure that HM is true penetration depth. Sorry. Now, second parameter which one should handle is stiffness. Okay, the stiffness, what I'm talking about, right, is important part, because that is involved with both contact area as well as the modulus value. So it is important we should know what is the stiffness, and we have to correct the stiffness after the experiment. So if when we say stiffness, right, the sample also has a stiffness, the indenter mechanism also has a stiffness, then you have the system stiffness as well. Okay, so there are many other parts of the whole instrument, right, which contributes to the overall stiffness of the which we are calculating. Okay, so it is very, very important that we have to make sure that all other stiffnesses, right, has been corrected. So how basically we will be able to correct the stiffness? We know what is the stiffness is a compliance. Okay, so we have to identify what is a frame compliance. Frame compliance will determine, will help us to basically figure out this. So the total frame compliance is a function of two different things. One is the stiffness, 1 by S, where 1 by S is the stiffness calculated from the unloading curve, and plus CF. CF is nothing but a frame compliance. Frame is nothing but the whole the system which is sitting on some frame, right? Granite frame also has some kind of a compliance. So this, if your CF is has to be as low as possible. Okay, so C total is nothing but the inverse of the stiffness we get from the load displacement data, as is stiffness from combined effect of the sample indenter interface. CF is the inverse of the stiffness introduced by the instrument frame. Okay, so now if you see here, S is equal to if you take the previous equations, right, is a square root of 24.5 divided by pi into bracket modulus into 2 into beta plus HC. Okay, and if you really calculate the stiffness, right, the other way around, right, you can write dH by dP, and if you replace the S into the top equation, which is nothing but a C total, right, you are getting dH by dP is equal to inverse of 1 by S. Okay, sorry, yeah. And now I will be actually doing this one experiment, okay, where I will take one sample and I will do multiple indentation experiments, different loads, okay, and for the different loads I will be getting different load displacement data, okay, and for different indentation experiment I will get dH by dP, different dH by dP, okay, and I will be able to what do you say the plot, okay, dH by dP versus 1 by HC, which you are seeing on the equation at the extreme bottom, right? So I have these two equations with me, right? Which is nothing but a linear equation, okay? Y is equal to mx plus c. That is the basic equation, okay, linear equation that we know. And I'm trying to plot that equation, plot this data, right? And I'll try to linear fit that to get this particular thing, okay? And where this graph is touching on dH by dP, right, is my offset. And that offset is nothing but my CF. This is how I will be calculating the CF value for any given system. Okay, so people, the manufacturers will give the stiffness value. Okay, for their frame compliance, people refer it as a frame compliance. Okay, manufacturers. So when people say frame compliance, right, it is been calculated in a specific location. Okay, and so whenever the instrument is moving from one location to another location, right, it is very important for the user to recalibrate or recalculate this frame compliance, okay, because there is a possibility that it may deviate depending on the location. Okay, so make sure that you do this before you go and really start your actual experimentations. So you have to correct the frame compliance. Once you have a frame compliance corrected, you will have everything corrected. Okay, so now as I mentioned, we have corrected the thermal drift, initial penetration depth, stiffness, means the frame compliance we have corrected. Now once we have corrected everything, right, I will be having the correct contact depth. And I know what is the relationship between the contact area and contact depth. Using this equation, I will be able to get the correct contact area. right? Using this equation. So I have corrected contact area. Now the C0, okay, which I have referred as 24.5 for Vickers or modified Berkovich, right? Now how whether it is reliable, that numbers, okay? Because practically when you will be buying the indenter, right, the geometry, the sharpness at the tip or apex, right, the tip will not be perfectly. It will be it will not be exactly what is defined in the diagram. Geometrically, whatever is defined, right, will not be exact radius that you are getting at the tip. Okay, so this tip radius, okay, or a tip area calculation has to be carried out to make sure that whatever the relationship between the contact area and contact depth, which has been determined for a specific geometry, will not be actually ideal. Okay, definitely this will be a part of the relationship, but this is not the only coefficient which is present there. Okay, so people has to make sure that you have a corrected contact area tip contact area equation. Okay, and for that people also conduct the tip area calibration experiment, and this tip area calibration has been conducted with a known value sample. I would say standard sample whose modulus and the hardness value is known to us. Okay, so we will perform the experiments calculating the contact area from this particular equation. Okay, so now if you see the modulus equation, right, I'm doing the replacing like in terms of AP. Okay, so this if I rearrange this equation, making the AP as a main parameter, I will get this particular equation. Okay, now the stiffness, right? I know the stiffness. From each of this curve, I have a stiffness value. I know what is the ER. Okay, ER is nothing but a modulus of a fused silica, which is already known number there, right? So I will give this number. I will measure the S. Okay, I know what is the stiffness, right? And this one, so I will be calculating AP for each indentation experiment. S1, S2, S3, S4, and as I made 110 indents, I will have 110 S value. ER is fixed, beta is fixed, pi is fixed. So I will be able to have 110 AP values. Okay. Same way, I will have 110 contact depth values because I know what is HM, epsilon. I know what is maximum force. I know what is the S. S also will be 110 numbers. For 110 number of days, I will have 110 HC values. So I will plot this 110 AP value against the HC value, right? I will be actually getting the plot something like this. I will use some B-spline fit, okay, some model, right? B-spline fit curve, right? I will be able to establish a new relationship between the contact area and the contact depth for this particular geometry. Okay, so you are correcting the area function as well. Okay, so your previous area function was very simple. AP is equal to C0 HC square, but now after because the geometry is not ideal, right? Is really in a real scenario it is not a sharp tip. It will be different. So you are actually re-establishing this relationship between the contact area and contact depth. Once you have done this, established this new relationship, you are making sure that the contact area which you are calculating is also a true contact area. Okay. So everything, whatever the previously which we have discussed, right, is basically the we have corrected everything against the system response. Okay, there was something which is related to system which we had to take care of it and make sure that your whatever data that you are measuring is a true number. Now there is another aspect from the sample side. Okay, people think that should not think that only instrument contributes to the errors. People also should realize that they have something from the sample side as well. Okay, so what kind of samples that people should work with, what kind of samples you can characterize with this technique, I'll be discussing now. Just a minute. So the first most important thing that is somebody has to take care of is the sample roughness. So if you see the diagram here, right, you can see that there is a Hmax. Now Hmax is what? Is that basically the maximum displacement from the surface. From the surface. Assuming that my surface is really flat. Okay, so my displacement, okay, will be happening from a specific reference, right? So referencing is very important when we are calculating the numbers. If this surface is having too much of roughness, means there will be a lot of peaks and valleys, right? So my referencing will be changing, because if I'm landing into a valley, right, my referencing will be at a lower height. Okay, and if I'm making an indent near the peaks, okay, where the referencing will be a peak which is not the flat average number there. Okay, so if it is a peak, then the Hmax will be higher. If I'm talking about the valley, my Hmax will be lower. Okay, so my Hmax will not be consistent if my roughness of the sample is too much. Okay, so Hmax is deviating, and as Hmax is deviating, most of the time my contact area also will deviate. Though my testing condition, experimental conditions, right, is same, as my Hmax is different, I am getting different numbers of Hmax. The hardness and modulus value, because contact area is wrongly calculated. So it's very important for one to make sure that when you are doing nano indentation experiment, your surface has to be as flat as possible, has to be a mirror polished. I'm showing you one example here. So the material which I'm talking about on the left hand side, two images are there. Okay, the material is same, okay, but the roughness of this material is different. First roughness is 5 nanometer and another is 167. If you see the right hand side indentation curves, which is load displacement data, right, you can see there is a drastic difference, right, between the two repeatable data. What we have done is we have conducted 10 experiments at different locations across the sample, right, and we have plotted it together. If you see the gray diagram, gray graphs, right, they are quite scattered, okay, but the black one is pretty consistent, repeatable, right? And if we convert it into a histogram, or in terms of the hardness values, right, across this these 10 indents, right, I can see that this roughness having a smaller, the sample having a smaller roughness has minimum standard deviation. Okay, the hardness value is almost falling in the same regime. Okay, but the standard deviation is almost nil with a less roughness. Okay, but in the rough sample, your standard deviation is pretty high. Okay, so it is very, very important that your roughness has to be as minimum as possible. But then it is not always possible. Okay, there are samples where people says that I cannot modify my surfaces. It has to be as it is. I cannot polish my surface, but still I'm interested to understand the mechanical properties. Okay, so if that is the case, then we have some thumb rules. Okay, these are all the experienced the figures that your maximum penetration depth has to be 20 times of your roughness number. Okay, so if you say here, if you see somewhere in the first image where my roughness is around 5 nanometer, right? So my thumb rule will be that my maximum penetration depth should be greater than 20 times 5 nanometer, means 100 nanometer. Okay, so if I go beyond 100 nanometer displacement into the sample, right, I will not have any influence of this roughness of 5 nanometer. Okay, and the scattering which we are referring here around 167 nanometer roughness, right? In that case, what is happening, that if that is the case, and if you want to have a repeatable data with a lower standard deviation, my maximum penetration depth should be 20 times 167 nanometer, which is not true in this diagram, right? So that's why I will be able to see the scattering. If I go beyond 20 into 167 nanometer displacement inside the sample, my standard deviation will come low. So this is what how you should be able to handle the roughness of the sample. The another important thing that is people has to take care of it is the pile-up and changing. Okay, so there are some samples, mainly the hardening processes which people follow, right, will basically contribute to this particular behavior of the surfaces. When I'm pushing the indenter in the sample, right, the material will start flowing towards from the bottom of this indenter towards the surface. Okay, and then eventually there is a pile up which is happening at the surface. So if you see the diagram here, right, where on the left hand side material is going in, okay, on the right hand side material is actually being pushed upward side. Okay, left hand side material is pushed downward side, right hand side material is pushed upward side. Now in this upward side direction, when the material starts flowing from the side to upward side, right, my H max, okay, H max will remain same. Okay, H max will remain same. Okay, but my HC will basically, because actually during the unloading my pile up is higher than the H max, right, my HC will be higher than H max. This is very, very critical situation. Okay, people has to really understand this. Okay, see, my H max is this, but my HC, which has been calculated from the experiment, is this much, right? So HC is higher than H max. HC contact depth is higher than the maximum penetration depth. If you look at the previous equation which I was referring previously, right, where HC is equal to H max, HC is equal to H max minus epsilon maximum force divided by stiffness. It means that HC will be never greater than H max as per that particular equation, right? Which is not true in this scenario. If this is the case, that equation will not survive. Okay, that equation will not help us to really get to some conclusion. Okay, so this is very, very important event that is happening due to the material. It's not a problem of the system, okay, instrument. Okay, people sometimes blames the instrument that my instrument is not giving a good result. Okay, I'm not satisfied with that. But have you ever studied, try to see whether there is a pileup happening on your sample? If pileup is happening, you are actually ending up with calculating a very wrong number of your hardness modulus values. Okay, so it is from user side also should know this kind of things which are happening with the system. Okay, so make sure that you, and how will you make sure? Okay, I will tell you how to figure out whether there is a pileup in your data. Okay, you will not see this in this diagram, right? It's just for the explanation, right? How pileup will contribute and lead you to a wrong calculation. But you will not be seeing this, right? But how will you figure out whether your sample may have a pileup, right? So you see the right hand side graph here. I've shown a graph on the right hand side. So if you see a diagram or a load displacement curve, something like this, okay, where HP, okay, so there's a limit, okay, there's a border line, okay, where HP is equal to 0.7 H max. So I will call this depth as an HP, okay, penetration depth, right? When the relationship between the HP is less than 0.7 H max, right? Then there is no pileup. If HP is smaller than 0.7 H max, means there is no pileup. And if HP is greater than 0.7 H max, then you will see so there are two possibilities. One is that your material response is like that, or there will be a pileup. Okay, so there is a possibility that there is a pileup. When you can conclude with this particular scenario, when your HP is greater than 0.7 H max, possibility is that there is a pileup. Okay, so if you have a pileup, you have to really get it to understand that. You take the sample under the AFM and see how much pileup that you have. And once you know what is the height of the pileup, you will be able to correct the things. Okay. So I think I'm taking too much of time. I will just briefly go through some case studies here where people have studied the biological samples, which will be very interesting because this is another interesting area where the indentation technique has become very, very popular in recent years, like into 3 to 4 years back. People have started exploring this technology for the biological samples as well. Okay, so the various areas, application areas in life sciences like cartilage, the cornea studies, okay, hydrogels, and many other things, okay, drug delivery systems and all. There is another non-biological samples areas where the materials are really soft, are the contact lens and stuff like that, membranes, inks and all. So let's talk about some soft materials. Okay, the soft material where the material property will be something around 2 kilopascals. Okay, modulus is around 2 kilopascals, and if you see some adhesive films, we have done some couple of testing. Most important difficulty for the biological sample is that the displacement. Okay, so the displacement has to be like too much of. Okay, so it's so soft that at very, very small forces, your displacement will be too much. Okay, and they are more on the elastic side rather than the plastic deformations. Right, elastic deformation will be more in this kind of experiment, right, where you have to have the samples also has to be in a hydrated conditions when there is a buffer solutions and the sample is dipped into that. Okay, so and the displacement has to be big enough, right? So there are a couple of other hydrogel sample studies have been conducted. okay, where you can use the titrate dish and stuff like that. Okay, I would like to show you some couple of comparison. Okay, there are varieties of samples. Hydrogels have been taken up, okay, and the experiment was conducted on this hydrogels, and these are the couple of results that we have got. And if you see here, it's pretty nice repeatable data on those samples, having a nice modulus values, which varies from 25 kilopascal to 2 kilopascal. So, which is very, very tough in terms of handling such very soft hydrogels. If you people, the 2 kilopascal, right, is a sample like a soft gel. Soft gel means jellies, right? We eat jellies, right? And that jelly will have this kind of modulus, okay? And then this has been characterized in terms of the brain tissues. Okay, so the brain tissues are also very, very soft, maybe in terms of around 1.5 kilopascals. We have recently done some couple of testing for such very soft tissue. If people are interested to know about this brain tissue characterization, please let us know. We will provide the data about that, and the videos also we have. We will share it based on if somebody is interested in. Okay, as I talked about the creep, right, poroelasticity, right, that is also a very interesting part of the biological samples, because as the samples are immersed in the water, right, when we are actually doing the indentation experiment, the water will start flowing from the body, okay, and then there will be a creep associated with that, which has to be characterized on such biological samples, right? And as I mentioned, that there should be a thermal drift, which is again, people has to take care of it during this kind of creep studies, right? So if you have a mechanism which will take care of this kind of thermal drift, would be a very good option to study this kind of samples. Okay? So here also we have done some studies where we have studied the creep over a period of time on cornea, right? Which has helped the customer to optimize the properties and to mainly the recovery stuff, a comparison of creep with the different soft tissues. Then we have also done some couple of studies on cartilage, where the recovery is also very important part of it on the goat's human cartilage. Then we also conducted on rat's human cartilage. Okay, and observe the recovery and the recovery mechanical property as well. After the recovery, we have to identify what is the modulus and hardness values of that particular zone, right? Also been studied. Also, the transference of cornea is crucial for the good vision, right? And this happens due to some kind of accidents and like diseases, right, which will progressively leads to a opacity of cornea, right? But we can do the recovery also of the cornea, right? And so how this recovery can take place, right? Cornea can be regenerated from the limbus area, okay? And the artificial growth, which has to be studied, right, which under the suitable mechanical environment, right, it will basically recover it. Okay, so how people can do that, right? A study has been conducted. Okay, so the self renewal of the limbal stem cells depends on the biomechanical property of the environment, right? So it is very important for somebody to really study these mechanical properties of the environment, so it will help to recover fast. Okay, so the growth rate, okay, of cornea depends on what kind of environment that you have to the limbal and its mechanical properties. So this helps in that characterization as well, and we have publications for this particular studies. Yeah, so these are all things The last, I would say there are many application areas. I have just discussed about the biological samples, but there are many different areas where the instrumented indentation techniques can be very, very useful, which has been listed out here. Okay, and at the end of my presentation summarizes that in the indentation used for the local hardness and elastic measurements can also be used by very low indentation depth and loads, particularly for the soft samples, right? It's also standard now has been defined for this particular characterization. We can also get the stress strain data out of this indentation experiment, and the possibility to perform large matrix of indentations for the statistical analysis, which is nothing but a mapping of mechanical properties of the surfaces. With this, I would like to end up my presentation. I've taken, I think, quite a long time, but yes, I thought
Yes,
I
thank you so much, Dr. Chintan. Thank you so much. You have really put a significant effort, and I appreciate it. And I hope that students will get benefit out of it. You have really explained from the scratch to the end. It is really appreciated. I thank you for your effort, and you have spent a sufficient time with us. Thank you so much. Now I request my students and participants from the audience, if they have any specific question about the indentation techniques and about his talk, please feel free to ask directly, because it is one of the important mechanical testing tool which all mechanical engineers as well as material engineers use everywhere. Any specific question? Any specific question?
Yeah, Chintan, this is Professor Shankar.
Yes, hi.
Yeah, so I see, basically we work into rheology. So rheology of hydrogels and other things, whenever you whenever we try to do in temperature ramping, for example, what we are doing is a hydrogels that will be sol-gel transition in at around 35 to 38 degrees normally. Okay. Whenever we do temperature ramping and other things, we are finding it is transforming from semi-solid state to a porous solid state. Okay.
I see. Okay.
So, do you have any such literature? Because triboroeological, we are working on triboroeology actually. So rheology followed by tribology, because whenever we do a rheometer MCR 50302, when we use it actually. So whenever we try to do the temperature ramp, so temperature ramp when we are doing from 20 degrees to 40 degrees or 45 degrees. So there is we want to measure rheology, but problem that is taking is a tribological aspect also coming, because there is a sol-gel transition. You are getting a problem. Okay?
Yes.
Because it is becoming a porous solid at 35 degrees. Because body temperature is 37 degrees. We have made a hydrogen that will become a porous solid at 37 degrees. So, do you have any can you throw some light on that direction? Because you people might have done something. Because
actually, rheology is not my background. Okay, but I would say, see, we have as far as the indentation experiment is concerned, right? We have a setup. Okay, we call it ultra nano indentation setup, right? Which has a similar kind of studies. Okay, we called it viscoelastic property study. Okay, where we can do a thermal ramping and we can find out the storage and loss modulus, even the tan delta, right? Energy related information we can extract out of that particular experiment, whether it is in the liquid or as a like straight away as an hydrogel, right? We can conduct that particular kind of experiment. We can go up to 50 degree actually. We can ramp up to 50 degree in that setup. Okay, in hydrated or non-hydrated conditions. Okay, and we can try to figure out. Okay, but I have to work out. I have to work with rheology team. Okay, there's a one of my colleague, Dr. Karthik Podicherry, right? He's an expert of Geotribo. Okay, so I can probably discuss with Karthik. Okay, and then get back to you, or we can have a separate discussion sometime next week. Okay, we can definitely provide you a right solution for that.
Yeah,
I'm 100% sure about that.
People are working on Geotribo, combination of Geotribo.
Yes,
Yeah.
yes.
Because
Yes.
those are interlinked actually. So that is what we are facing some
Exactly.
issue. Because whenever we want to write
No. So that's what I mean. Yes. If you just pass on the information, right? Or you can, if you have noted down my, or Ajay must be having my contact details, right?
I know many from Dharmesh Gala to the people I know. So okay. That's
Okay.
yeah.
Okay. So you know Karthik.
I don't know Karthik. I know this guy, Partha Sarthi. What is his name? Sarthi, Hyderabad. Vijay Sarthi.
Okay. Vijay Sarthi. Those are sales team. Yeah. But I think probably what we can do is we can sit with Karthik as well. Okay. So we guys are more on a scientific side. Okay. Scientifically, we can give the solution. Okay. Rather than just talk about the instruments and stuff like that. Okay. It will be a more understanding and the solutions. Okay. I see. We are all scientists actually, basically at the end. Okay, so we talk about the techniques. Okay, so let's do this way. If we can spend 15-20 minutes time together with Karthik, right, and discuss, we can definitely give you some idea how you can utilize your system or your instrument for this particular characterization. Okay, is it okay?
Yeah, I have another query. For example, I have a lapping fluid. For example, I have a, you know, any polishing fluids, no? Polishing fluids means when assume that I have a grinding wheel, simple grinding wheel. Yeah, I think.
Right.
Okay.
Yeah, lapping machine, I know. Yeah.
Lapping or anything where abrasives are embedded on a. So now I want to check one abrasive particle pulling out. So I want to pull out one abrasive particle from a bonding material. So, so how much energy is required for dislodging and other things? So which division of Anton Par works in that area? So what I mean to say is that I have a fluid which is a semi-solid. For example, I have a butter. I have a butter.
Grease kind of stuff.
Grease is there, wherein I blended my MOS2 particles or diamond particles or any particles. But now
is embedded in the grease. Okay.
Embedded in the grease. Now I want to know how firmly my grease is holding my diamond particle. So you understand. For example, atomic force microscopy is there. So I put a diamond indenter and try to pull it so that I can measure what is the force required to dislodge from that location. So,
so you want to see what force the nanoparticles can be removed from the matrix.
My question is that which division of Anton Par normally are you handle this? I want to know how much force is required to dislodge the particle from the matrix. You understand ना? मुझे ये पता करना है कि उसको कितना एनर्जी चाहिए उसको डिसलॉज करने के लिए उस मैट्रिक्स से। मतलब ग्रीस के अंदर मेरा पार्टिकल छुपा हुआ है या थोड़ा ऊपर थोड़ा दिख रहा है, तो मुझे पकड़ के खींचना है, कितना फोर्स मुझे चाहिए उसको खींचने के लिए, मतलब उस लोकेशन से।
I got it. Understood. I understood that. Yeah. Okay. Yeah, I will try to figure out somebody who can do that. Yeah, it's interesting actually, either way. Sure, I will check that. Yeah.
Why I am asking is in the artificial cartilage and other things, Nowadays, people are coming with some biocomposites and other things. So there the particles are there. Whenever there is a wear and tear, कितना force में और कितना ये सब में वो जो input conditions में the reinforcements are coming out. This is vaguely I'm telling, but our application is different because I cannot tell directly my application.
I understand. That's okay. That's okay. Yeah.
So I want to know, apart from atomic force microscopy, any type of characterization technique in Anton Park can do this type of.
I will figure out. I will figure out that. Sure. Yep. Yeah.
Thank you. But however, it was a fantastic presentation.
Yeah.
Thank
Very
you.
nice. Yeah.
Yeah. Thank you. Thank you.
Yeah. Thank you so much. Thank you once again, Dr. Chintan. It was really a wonderful talk, and you have really put a sufficient time and effort.
Yeah.
So we will.
It's my pleasure.
We will keep our. We will continue our interaction. Okay.
Absolutely.
Yeah. Thank you so much. Thank you so much.
Thank you. Thank you. Thank you, Ajay. Thanks a lot. Bye.
Thank you.
Take care.
Bye.
Thank you.
So now I request all the participants, we will have a small break. And next talk will be by Professor Nikhil Gupta from Newark University. So he will be joining with us by 6 p.m. So we will take a small break, maybe for 5 minutes or 10 minutes. And by 5:15, we will be ready for joining with him. Okay. So we will wait, we will take break for maybe 10 minutes and we will rejoin again at 5:15, 5:45.
Hello?
Yes, Professor.
Yeah, I'm online now.
Yeah. Thank you. Dr. Ajay? Please give me 2 minutes, sir. I will contact Dr. Ajay and I will get back to you.
Sure, I sent a message to him already.
Yeah, thanks. I'm just, give me 2 minutes. I'm just contacting him through phone.
Hello, Professor Nikhil Gupta.
Hello, good morning.
Hi, good morning. This is Dr. Kiran. I'm assistant professor in the Department of Mechanical Engineering. So I welcome you wholeheartedly to this session on the topic, the reduction in the material characterization effort, a transformation to extract elastic properties from viscoelastic measurements. So I welcome you, sir.
Thank you.
So, dear participants, let me introduce Professor Nikhil Gupta. He is a professor at Department of Mechanical Engineering and Aerospace Engineering, New York University Tandem School of Engineering, New York. He is one of the leading researchers on lightweight foams and has extensively worked on hollow particle-filled composite materials called syntactic foams. He developed a new functionally graded syntactic foam material and a method to create multifunctional syntactic foams. His team has also created ultralight magnesium alloy syntactic foam that is able to float on water. He has appeared on Discovery Channel and in National Geographic as a material science expert, particularly for lightweight materials. In 2012, he explained the science behind athletic helmet construction as part of a National Science Foundation sponsored video featured on NBC Learn during the 2012 Summer Olympics, which was a series of 10 videos that has more than 125 million views and won a Telly Award. So I welcome you, sir, for this webinar, and I request you to start your talk. Thank you.
Thank you very much. I hope you can see the screen.
Yes, sir, we can see.
Okay, thank you very much. I see Dr. Ajay is also there. Thank you for your kind invitation. I'm really excited to be here.
Yeah, thank you so much. It is really a wonderful opportunity for us. You have joined with us today, and I hope that it will be a nice opportunity for students to interact with you, and you can also share your thoughts. You can also interact with the students and some of the other. Thank you.
Yeah, so the last slide I have is about a USA India program that we are starting. It's a summer program. So I'll give some information about that. Yeah, at the very end. So I think the talks yesterday were excellent. Actually, I got to listen to a few of them. And what Professor Surya Kalidindi from Georgia Tech and Professor Satish Bukkapatnam said from Texas A&M. So that gives a very good introduction to the kind of work that I'm going to show today. So my website is here, wp.nyu.edu/cmml. So you can see the publications and all the projects that are going on right now on our website. And the talk today is about reduction in materials characterization effort, because we have to characterize materials continuously. No matter what kind of material we are developing, the material development cycle actually depends upon developing something and testing and then iteratively improving. So that effort actually goes on and on. The work that I'm going to show here, I would like to thank National Science Foundation and USAID, which is a program administered by national academies. And also we partner with a company, Anton Par, which is manufacturer of thermal analysis equipment. So we design all kinds of products, and when you are a student, your aspiration is always to design aircraft and fast cars. But you know, a lot of people make good careers designing shoes and toys and all kinds of other things that are industrial products. And they require different kinds of conditions. Like we are always testing materials at high strain rate and high and low temperature for aircraft or automobile applications. But then I was really surprised to look at the data sheet of some of the very common products. And this one was a very surprising example, that when I saw the data sheets used to design a toothbrush, they are actually making use of the elastic modulus versus temperature data, because you might have experienced that when you dip a toothbrush in hot water, the bristles become very soft for some time. So their softness is coming from the material selection, because they selected a material that becomes softer when you heat it up just a little bit. Also, the materials that go in making containers that go inside refrigerator, now they are extensively tested for low temperature properties, and they make sure that the glass transition temperature is according to the freezer temperature, so that the brittleness does not take place in these materials. So this effort actually goes on, and it's not just that different products require different properties, but take an example of TPU foam. The same material is used in a number of applications. So each application has their different different conditions for which material needs to be tested. So for example, that this is a simple case which protects a sensitive equipment from damage. So it needs to be tested for minus 10 degrees C to plus 40 C at every 5 minutes at 1 minute ramp rate. We want to test impact and compression properties here. And then the underwater application require testing mechanical properties at moisture conditions. And then we have thermal expansion and conductivity, and the shoes have other applications where you require different strain rates, like 10 to the power minus 2 to 1 per second. Cars are tested for impact. So all these different properties, different conditions for the same material. So this effort actually becomes overwhelming. And now the question here is that how do we cut down this effort? Because if you think very carefully, you know, TPU is the same material. Interatomic forces are same for the TPU material. It does not change based on the conditions that you are testing at. So we need to we need to understand those governing relations inside the material that can provide us some information where we can cut down this repeated testing effort by as much as possible. So I'm going to ask a couple of questions, and maybe you can reply in chat if you have an answer within a minute. So here is a graph, and on the y-axis we have elastic modulus here, and the graph is with respect to temperature and strain rate. And this is for HDPE, high density polyethylene. So how many tests are required to create a chart like this, where you have elastic modulus with respect to temperature and strain rate? The temperature is varying from 40 degree, consider like room temperature, to 120 degrees. And the strain rate is from 10 to the power minus 5 to 100 per second. Any ideas that how many tests are required to create a graph like this? What kind of test would you conduct to measure the elastic modulus?
Rheometer.
A rheometer? The elastic modulus. Most people would probably think of tensile testing to find out the elastic modulus, but I'm glad that you gave the answer rheometer, because that's exactly where we are going. So elastic modulus comes from tensile test. Everybody is familiar with that, and feel free to write your answers in chat. I'll have a couple more questions coming up later. So let's keep everybody engaged a little bit. And tensile testing also requires 5 replicates under every condition, minimum 5 replicates under every condition. So you can imagine that a graph like this would require testing at every maybe 10 degrees or 15 degrees and different strain rates. So you can use Instron or MTS machines at low strain rate, but 100 per second is probably more than what you can do with an Instron or MTS machines, universal test machines. So we would need some different equipment for those kinds of testing. So now we are talking about these viscoelastic materials, and viscoelastic materials are the ones that have strain rate sensitivity. That means their properties depend upon the rate at which you do the tensile testing or at rate at which you deform this material. Temperature is one factor that changes the properties, loading frequency, strain rate, and also in nano indentation, people make sure that they test material at different indentation depths. I think that was one of the presentation yesterday from Professor Bill Klein. Also, we want to test with respect to different compositions. So summing up all these things together, there are a lot of parameters. And if you have to test with respect to each one of these parameters, it's going to be a lot of material characterization effort. And this is exactly the situation that we deal with right now. Every single test, every single material, every single test condition needs to be treated separately. So we would like to apply machine learning like a lot of other people have successfully applied. But the basic questions that come up is that when materials are governed by laws of physics, Professor Kalidindi was emphasizing that yesterday, that their models are actually building the new physics for materials. So why do we need these data-driven models when laws of physics are actually defining how materials behave? And the other problem is that I'm already complaining about the amount of testing we are doing, but the machine learning actually requires you to have a very large data set. So if you don't have that large data set, how do you train the models? And if you already have tested everything, then what's the value of predictions? So where exactly these predictions can be useful? So all of that needs to be taken into account here. And finally, can machine learning methods derive the material development? So here you can look at HDP, and this one is a magnesium alloy on the right-hand side. So high density polyethylene is tested at 10 to the power minus 5, and this one is 10 to the power minus 2 per second. All of them are within the quasi-static range permissible by ASTM standards. But here all these lines are well resolved from each other, which means that within the quasi-static regime, HDP has a lot of strain rate sensitivity. So imagine the tensile testing that we are conducting, it's not at zero strain rate. It has some strain rate, even at quasi-static, which is right here. But within this range now, there is a problem here. Viscoelasticity plays a big role, even at room temperature at low strain rates. Magnesium alloys, on the other hand, they don't show viscoelasticity. Metals generally don't. But there is a strain rate sensitivity here. And this sensitivity is at much higher strain rate, from 800 to about 1200 per second. So we would have to treat them a little bit differently because of this strain rate difference. So here comes the next question, that we got all these machines in our lab, Instron machines. So these can go UTM machines. These are mechanical systems. They go from 10 to the power minus 5 to about 1 per second. Then these are the servo hydraulic systems that can go up to about 100 per second. We have a split Hopkinson pressure bar that goes to about 1,000 or a few thousands of strain rates. And finally, we got the DMA. This is a machine DMA, and we have a vibration test bed, which provides the properties. Each of these methods can measure elastic modulus. So now here is the question. Suppose I had some magic that I do on these machines, and these machines are all able to calculate modulus from 10 to the power minus 5 to 10 to the power 4. That means they are all working across the entire strain rate range. But their measurement principle is different. So the elastic modulus will I measure from each of these machines? Will it be the same or different for a given material? Any ideas? No? Are people able to chat here? So I'll repeat the question that if these machines were able to measure the modulus of a material in the entire range of strain rates, will they measure the same modulus or a different modulus value for a given material? So somebody is saying different, and that probably stems from the reason that they have different measurement principles, especially the vibration method versus Hopkinson bar or other method. I think somebody is saying that it would be the same. So we have two opinions and they are not the same opinions. But let me give you a third opinion. And the third opinion is that we don't know because nobody has done it. And we've tried to extrapolate the results, but there is no way of saying that they actually are the same values obtained from different methods. And the bigger problem here is now with these methods like DMA and vibration method, because they are providing frequency domain properties. They are not providing the time domain properties. So what they provide really is not the elastic modulus. Now this second problem here is displayed. These are literature review graphs. A lot of different studies were taken. And from there, we took the data out just to see where the data lies on these charts. Aluminum foams and PVC foams. So I showed you 5-6 methods of testing modulus, but still what comes out here is that these regions, which are pretty big here, there is no data here from 0.1 to about 500 per second. And then you see the same trend in aluminum foams, that there is no data between about 0.1 and a few hundred per second strain rates. Why is it like that for every single material that we try to see? Even if you find data for some material, there'll be like 1 or 2 studies that show data within this range. So we have a bunch of techniques, 5-6 different techniques that can measure modulus, and there are more methods that you can apply. But still, they are not covering the entire range. We're not talking about one machine covering the entire range, but collectively together, they are not covering the range at all. So this data is from Hopkinson bar, and this data here is from servo hydraulic machines or electromechanical test machines. So looking at this DMA, dynamic mechanical analyzer, we thought that let's start looking into this problem and see what's really going on in these test methods. And DMA is a very versatile method. It provides you with the mechanical data with respect to frequency and temperature. And you can do that in the same experiment. So testing just one sample can provide you with a lot of data. It works in a number of different loading manners, but this is the one that we have been using. So a sample is clamped on both sides. These are the 2 sides of sample clamped. And then you have this loading head, which is applying a frequency at a certain amplitude. And then you get the load and displacement or stress and strain graphs out from this machine. Here what happens is that in viscoelastic material, the load and the displacement curves, they will start to lag from each other because of viscoelasticity. So material does not have enough time to recover after the first deformation cycle. And the second deformation cycle will catch the material in a deformed state already. So that's why the load and displacement or stress and strain cycles, they show some lag in between. And this lag is called phase lag, or also called damping parameter. The graphs are very standard how they come out from DMA. So this one is the solid line is called G prime or E prime, depending upon how you are testing them. So E prime is storage modulus and E double prime is loss modulus. So storage modulus is the measure of energy stored in one cycle of deformation. Loss modulus is energy dissipated in one cycle. and E prime is called complex modulus. Okay, so why we call this complex modulus, not elastic modulus, is because this is a property in frequency domain, not in time domain. That's why it is called E star, which is a complex modulus. So when we conduct this testing at different frequencies and temperatures, you can ramp up temperature and frequency both in these experiments. And now this smaller data set is at 1 Hertz frequency on the left. The larger data set here has frequency varied from 1 to 100, and the temperature is varied from 40 to 125. So the bigger graph that I showed in the beginning for HDPE, this is the original data set that comes from the machine to create that three-dimensional plot. So it's easy to understand that as we increase the temperature, the modulus is going to go down, material becomes softer. So the storage modulus goes down here in this case, which shows that it's fine. And also with frequency, it shows that as you increase the frequency, the modulus or the storage modulus is increasing here in this case, which is also something that we have previously seen from tensile tests, that as you stretch something faster or increase the strain rate, the material behaves like a stronger material. So now the question here is this, that this E star is a complex modulus where E is the Young's modulus, a frequency domain property E star and the time domain property E. How do we convert the E star into E? Is there a method to do that? Also look at these definitions very carefully. We said storage modulus and loss modulus. So if you're working with metals where loss modulus value is negligible compared to storage modulus, we can simply neglect this quantity and E star becomes E prime, or complex modulus is equal to storage modulus. And we also call that this is equal to elastic modulus or Young's modulus. And this is something that we have been doing for a long time. Then the other method is what everybody would say when you're talking about these properties, is that you can extrapolate these curves to zero frequency. If I extend this axis and say this is zero frequency, it's log, so that will not happen, but somewhere the extrapolation will give you zero frequency. And then you can say that, okay, so at zero frequency, this is my storage modulus, and that would be the measure of elastic modulus. And people have done it for a long time. But what really is the validity of this for a viscoelastic material? That's really a big question in front of us. Because in viscoelastic materials, E double prime is not zero, it's not negligible. You got to deal with this complex equation and end up with E star. And there's no way currently to find out the value of elastic modulus from this chart. We looked at the literature and just couldn't find any of these methods to convert them into Young's modulus, where the entire data set can be used. So that was a good starting point. Now this DMA is a general method. What it's doing is that it's creating a cyclic load. It's applying a cyclic load on the specimen. And it's looking at the deformation cycle versus load cycle to calculate the values here. Now, you can try to find these equations in undergraduate textbook. I don't think you'll find them. You won't even find them in a beginner's master's level textbook. So that's a big problem with the definition of E star and E prime, E double prime. Understanding of these frequency domain properties is actually pushed to advanced domains. So that's why I think this introduction is very important here. So you can broaden the horizon by saying that this DMA, let's consider this as a method, not as an equipment, and see where else people are applying similar kind of loading situation. So where we found out is that nano indentation is also a method where people are using the same kind of test principle that's applying cycling load. So nano indentation has two methods. One is called Oliver-Farr method, where you simply do the indent and you get the values out. So you must have seen graphs like this, and then people take the slope of this part, and that's the elastic modulus. But then nano indentation has a second method called CSM, it's continuous stiffness method. So in this method, the tip is continuously vibrated at different frequencies. And the output from that method looks a little bit more like a jagged pattern here, something like this. And each of these serrations here are at different frequency. So you can go inside and you can actually find properties at different loading frequencies in nano indentation. And again, it gives you the storage modulus and loss modulus out from here. In nano indentation, this is an example from our medical school. So they tested the larynx tissue, and soft tissue is a hierarchical biomaterial where properties vary in any direction. So it's a very common practice to do 1,000 to 10,000 indents and create a property map like this. The first one is storage modulus on top and the loss modulus here. These maps are always qualitative. There is no equation where you can actually go and put storage modulus and loss modulus and do some calculation for materials design until you reach your PhD level actually. So what is really the value of getting these properties was quite unclear. And in biological fields and in polymer fields, people have been reporting the storage modulus and they have a good understanding, just like we do for elastic modulus. But for soft materials, this storage modulus is not an elastic modulus. That's the bottom line. So what are we missing here was really the challenge. And the idea here was that these properties are not what you would use in any of the material design. So suppose if I had to create a surrogate biomaterial, so a lot of people require repair of vocal folds, and it requires you to use a polymer material to fill the gap in the natural tissue. And this polymer is tested for at certain frequency to match it with the larynx tissue property. But then you can imagine that when we are talking, this tissue is vibrating at many different frequencies, not at a single frequency. And matching the properties of these tissue at all the possible frequencies that a larynx actually goes. So that's just not possible to develop a material like that currently. So those are some of the future directions that we would be looking once this project is successful. So going back here to the basics, we said that let's start looking at this equation more carefully and see how we convert this E star into elastic modulus. So this is written as the elastic modulus, but you can also write the same kind of equation as loss compliance. So E star multiplied with the C star is equal to 1. It's not the multiplication, but I'm just calling it a multiplication right now. So this is an inverse basically. So we started with this storage modulus graph, and people have used time temperature superposition. And the basis for time temperature superposition is that if you increase the temperature, that is like decreasing the strain rate. So there is a correspondence between the strain rate and the test temperature which is used. And now we are going to use the same relationship here. So the method I'm going to show you, they apply for what is called rheologically simple materials. That's a definition for that. And the basic characteristic of these materials is that they follow the time temperature superposition. And that's the starting point for our work here. A lot of materials come in this definition, quite a few polymers, composites, and many different materials come under this category. So this method is very useful for a wide range of materials. And we got a patent issued on this quite recently. So in time temperature superposition, what we do is we select one of these curves as the pivot curve. So for example, I took this curve, it's at 70 degrees as the pivot curve. Now all the curves on the top, they will be shifted to the right, and all the curves below that will be shifted to the left. And these are shifted until we create one single curve, which is called a master curve. just by shifting this. There are procedures in place. I'm sure you can read books to figure that out. But we could write a simple program to shift them and finally create the shift factor and use those for some validation studies here. But once this master curve is created, the black line in this graph here, then we fit a function on top of it, which is the red line in this graph here on the right hand side. This fitting of this curve is very important because now we are going to start dealing with this fitted curve, the equation for that. It changes slope here and then it changes slope here. It becomes asymptotic on top. It becomes asymptotic on the bottom. So all these properties need to be captured. And that's why finding this was a little bit of a challenge in the beginning. But once you find this, then you can deal with this mathematically to convert to time domain. We'll take the fast Fourier transform, convert it into time domain, and then deal with those properties. So, so based on that, we find this relaxation function from the master curve. And this relaxation function is plotted with respect to time. Now you can use any other pivot. Let me go back to the previous one. So you can, the way we select the pivot is a little bit random. Actually, the temperature that you are interested in, you can take that and you can shift all the graphs with respect to that temperature. So one important thing I just wanted to highlight that suppose I select this red line here, which is I think 80 degrees C. And if I shift this curve here, so this curve will go here and then the next curve will go on top, then the next curve will go in front of it. Similarly, the curve at the bottom, they will be shifted this way. So effectively, what I'm trying to do is I'm extending this frequency axis. This will be like 1,000, this will be 10,000, and this will be 0.1. So the frequency axis is getting shifted on both sides by doing this kind of transformation. So if you look at the right-hand side, what we see here is 10 to the power minus 8, and this one is 10 to the power 4. Actually, they are cut here. The graph goes much farther compared to what you see on this case. But 10 to the power minus 8 and 10 to the power minus 10, how different are they from practical purposes? So there's not much of a difference when you go that slow. That's why we just cut the graphs here. So the frequency axis is enhanced. And from that frequency axis at different temperatures, then we can create these ET or the relaxation function. Now, once this relaxation function is transformed to time domain, we can use the integral relation of elasticity and try to get the elastic modulus out. So this is the equation that we end up with. And you can use any strain level in this equation, like we took the 0.25% strain level, calculated the secant modulus because the curve is not straight line, so you have to calculate the secant modulus instead of elastic modulus, but they are equivalent quantities here. And now we ended up with the frequency that was converted into strain rate, and this is what you see here, 10 to the power minus 5 to 10 to the power 2 per second. And the temperature is on the x-axis of this graph, while secant modulus is on the y-axis of this graph. So that one master curve that we had, we created multiple master curves at different temperatures as pivots, and then we converted that into the time domain, which gives us this secant modulus. And now we replot that graph, the previous graph here. This is temperature and strain rate and elastic modulus. So this is what you get here, temperature and strain rate and elastic modulus. So I think the answer was correct that we took only a single specimen to create this whole graph from DMA. And this time domain conversion actually gave us the elastic modulus. So I'll go back a little bit to that master curve because the relation that we found, there are lots of different properties that needs to satisfy. So initially we ended up with a convolution, and converting that convolution to time domain or transforming them to time domain was a big challenge. So originally the work was done partially computationally or numerically, but now we have different functions and we can just take the FFT satisfying all the conditions and still get the results out from there. So this was verified on a number of different polymers. For example, HDPE was a starting point, but PVC and PMMA. Now here the results are for a composite, which is CNF and HDPE, the carbon nanofibers in high density polyethylene. We also tested for graphene, HDPE, and syntactic foams, fiber reinforced composites. And these are all the materials that fit within the rheologically simple material category. And we find that there is pretty good correspondence between the converted modulus, which is this elastic modulus coming from storage modulus, and the modulus measured from tensile test. So there are a number of papers we published on different materials and different mechanisms. So I'll summarize what we have done so far before we go forward. So we started with the storage modulus, but now you can also go to loss modulus because they are complementary properties, or you can go to loss compliance, which is the inverse. And from there, you can build the same kind of relationship. So you can take the Kramers-Kronig relationship, which defines the storage modulus and loss modulus relationship. And from both of these paths, you can go to relaxation function using the integral relation of viscoelasticity. And finally, use the strain history, get the stress strain relation, and then we get the time domain elastic properties. So depending upon the viscoelasticity, the contribution that comes from the loss modulus component, which we completely neglect in metals, in polymers, that component can be 20 to 40% in elastic modulus. So that's really what we figured out for HDPE and some other materials. So it gives a big advantage to us that this whole chart came out from a single specimen. We didn't do any tensile testing for measurement of modulus. You may still have to do tensile testing for strength or failure mode and other things. But a lot of this polymer materials design is revolving around measurement of modulus. So that effort can be substantially reduced. So imagine that originally, if you had to do all the tension tests, it would take months of effort. But one DMA test took us about 8 hours to conduct that time and temperature variations or sweeps. And then we convert that all into the elastic modulus. But there are limitations to what I showed. One limitation is that we only deal with just one thermal transition. If you have more than one transition, then the function that we select becomes more complicated. And then you have to build a function that can capture all those thermal transitions at different temperatures. Or you can do a piecewise conversion and then you can assemble the solution together, but it just becomes more and more cumbersome at that point. At least we have a method that's validated now. So this is the chart that gives you the overview of all the equations that we have used. The Kramer-Kronig relationship goes between storage and loss modulus, and eventually you can convert everything to time domain properties. So this part shows how to convert the loss modulus, because loss modulus profile is different. The storage modulus profile is always like this. The loss modulus profile is always like this. And the peak comes at a temperature which is called glass transition temperature. So DMA is the best method to measure glass transition temperature. It gives you measurements better than DSC because this peak is very sharp. And even if you don't catch the peak, you can still get the temperature at which this peak appears. And using the same kind of methodology, now we can convert both these charts into elastic modulus curves at the end of this procedure. So here, the validation is shown with respect to a number of different material systems. The carbon fiber reinforced composites here, CNF HDPE is here, then HDPE is here, and this is with rabbit vocal fold. The data I showed you for nano indentation, we even fit the nano indentation data here, and we find that it's pretty close to the prediction that we obtain on these material systems. So now the question comes that we use the standard protocol, which protocol requires us to test these materials at 20 different frequency values between 1 and 100. You divide it on the log scale. Also, you can see that the temperature-based testing is conducted at every 5 degrees C here. There is a soaking time involved after you ramp up the temperature. And then you really have to do the testing for a certain amount of time until the behavior becomes stable and then note the data. So it takes about 560 combination of temperatures and frequencies over 8 hours to create a graph like this. Can we reduce this effort further? And if we can reduce it further, what is the way to deal with that? So one thing that I said really casually was that the storage modulus, no matter what material you have, will be like this. Loss modulus, no matter what material you have, will be like this. And this is within certain temperature range. If you go outside of this temperature range, there can be multiple slopes. Like for this one, you can have waterfall slopes like this. For loss modulus, you can have slopes like this. But the basic nature of each slope does not change. So within that range, within one thermal transition range, what you're always going to get is this waterfall plot. When we know that this is the nature, the only question here is that what are the slopes in each of these three regions? Or what are the two changes of slopes that we are looking at? So with all this background, it's simpler to think of a method where we can capture this entire three-dimensional surface rather than catching each of the point on this three-dimensional surface. So this was the exercise that we conducted next. We said, let's look at this whole surface as a surface and find out if we can use sampling methods and capture this surface with good accuracy by testing only a few test conditions. So suppose if I fit one experiment here, I'd select some combination of temperature and frequency randomly here. Then I select a second one randomly here, and then third one here. Similarly, I select first 5, just generate the data. Then I select next 5 and generate the data. And based on that, I create a curve. And then after that, all the tests I'm doing are only for the validation and adjusting this initial data set. So this is how the sampling method works. And here you can see that these are the different sampling schemes here. You can create the grids of different sizes and try to capture the accuracy within these grids by conducting certain set of experiments. So using these optimization method and particle swarm optimization method is used very commonly. What it shows is that the average error here is plotted on the y-axis with respect to the swarm size. So we started with 560 points, which would be somewhere here, I would guess. And at about 100 points, we start to converge. That means the error is about the same in our original measurements and these reduced measurements. So consider that I was taking 8 hours to do 560 points. If I have to do 100 points, it's going to be only a couple of hours of effort, not more than that. But we can reduce it further. So we started looking into other methods for optimization. We selected 4 of them just to get a good start. So Monte Carlo, Latin Hypercube, quasi Monte Carlo designs, there are 2 different types. And then we did these testings to see where do they converge, where is the error converging. And here you can see the Sobol is actually converging at only about 10 points. Most others would converge for less than 20 points here. So that means instead of 560 points, we are testing only 14 or 16 points, and we are getting a pretty good prediction here from our testing. So this 8 hour can go down to about half an hour and still give you the same level of prediction. So we tested them for Gaussian noise levels of 5% and 10%, and we found that 14 gives you a baseline for 3 of these methods are converging. But to be on the safe side, you can conduct a few more experiments, use them for validation, So maybe a set of 20-25 combination of frequency and temperature would be enough to give you a pretty good handle on how this graph is going to come out. So now you can imagine that we are coming down to hundreds of tensile tests in first case. Then we replaced it with a single DMA test. And that single DMA test had 560 data points here, which is now reduced to only 14 data points and still get the profile with high accuracy. So this is how we can cut down a lot of this materials characterization effort that is going on in these materials. So this accuracy of transform depends a lot on the master relation, and that's why we struggled in the beginning quite a bit to find the right relations that capture the behavior, they capture the physics, and they capture the trends that you observe. And finally, we try to get the time domain properties. So now the question here is that when we have this framework, and this framework I tried to explain that we go from storage modulus all the way to time domain, then you can go to storage compliance and you can go all the way to time domain. And you can have different materials. So if you want to add different materials, we would add those materials here as bubbles, and one composition, the second composition, and things like that. So looking at it gave us a visual picture that, this is how the neural network looks like. But does it behave like neural network? Can we use the neural networks here? And those were really the questions in our case. So we looked at neural networks in detail, different factors that you can use. And then there are these layers. You can have hidden layers, the number of layers that are needed. And finally, you can get the predictions out. So in our case, because we're trying to do the testing right now, eventually we have the system in place where you have the input properties of just the time, temperature, material compositions, and other factors. Then you do the predictions here for the final properties like elastic modulus. But for demonstration purpose, I'll go through the steps and try to predict the storage modulus and loss modulus out from here and see if we capture the trends. The benefit here is that we have a lot of data coming out from DMA. So if I was complaining earlier that we have 560 conditions and all this data to deal with, now that becomes a powerful tool for us that we can use all that data, train the neural network, and finally get the predictions out from there. So the standard formulation, I don't think I'll have to go through all of it, but just to make sure that all this is here. So this graph actually defines how we are building this neural network. The temperature and frequency are the two parameters. Eventually, we are getting the storage and loss modulus out, but we are then using our relations to convert it to time domain elastic properties. And then the standard test that we have to conduct on these neural networks to find out the number of neurons, the penalty factor at different Gaussian noise levels of 5% and 10%. This one is 2.5% here. So it depends upon the type of material you are testing and what is your accuracy level you're looking at. And once you conduct all of it, we can do the experimental and predicted storage modulus, and they fit pretty nicely on this 45-degree profile. So that gives us confidence that this method, the neural networks are able to predict the storage and loss modulus profiles. So again, these predictions were compared for EVA, graphene epoxy composites, and a whole bunch of other polymers. And they found to fit pretty well, whether you're coming from storage modulus or loss modulus. The neural networks were effective in this case to capture these trends and provide us with the predictions. We extended this work to composite materials. In composite materials, we have directional properties for different directions of fiber orientation, and the neural networks are able to predict that too. And eventually we do the material design where the problem is essentially this, that suppose you have an application that requires 3 gigapascals of modulus. Now you're trying to find which material will give you 3 gigapascals of modulus. And usually the answers are not unique. You would have to add more constraints in order to get a unique answer. But here these neural networks can give you a whole bunch of compositions at the end where you can do the material selection based on the other criteria that you have. And this neural network could be applied in these inverse problems to find the material compositions. And now finally in this material design, we are extending these to different kinds of composite materials. Here is the example for syntactic foams, which are hollow particle filled composites. The predictions are not as close in this case as for graphene epoxy or graphene HDPE composites. But in this case, the problem that really happens is that the damage starts very early in the deformation process. So the curves start shifting even in the DMA testing. And that's a little bit of a challenge to capture the trend. But I think this can be corrected with the right physics embedded into the models. So these were the predictions for syntactic foams for different compositions of microballoons. And the accuracy of these graphs is I think most of the data actually fits within 10% of the experimental observations. So 3 things I showed. I just wanted to conclude pretty quickly that the theory of viscoelasticity, for a long time, we were neglecting this storage modulus, loss modulus correlation with elastic modulus. We were happy with complex modulus. Dealing with metals, it had never been a problem. But now with softer materials, especially in soft robotics and biomaterials and surrogate biomaterials, there are a lot of these test conditions going in. And we have to revisit this viscoelasticity in order to find better correspondence with the elastic properties. And then the testing effort increases a lot due to the strain rate effects in viscoelasticity. You need vibration methods or Hopkinson bar or other parameters or other equipment to test material properly. Also think about a test which is at 10 to the power minus 5 per second strain rate. Just one test, tensile test would take forever. It's a lot of time of a person and the equipment for just a single test. So that reduction comes from converting one type of properties to the other type of properties and finding exact values that you are looking for from there. The neural network approach worked out pretty well. It was able to capture the trend and reduce the effort further. So these are some of the publications that we have within last 2-3 years on this topic. The schemes were expanded for composite materials, for nanomaterials, for different types of polymers and different properties that we can capture from there. So that's all for the technical part. There's just one last slide I want to mention. So this year we are starting a undergraduate research program, USA-India program. It is funded by National Science Foundation. And our partner on this program was NIT Surathkal. I've been collaborating with them for quite a few years now. So we are going to take 6 students from the US and they will go to NIT Surathkal. They will spend 8 weeks in the Surathkal lab working under the guidance of their faculty. And we want actually 6 Indian students to be paired with these US students. So we opened up this program to Indian students and now we have a call out. So if anybody is interested to apply, they can apply. Out of these, there are certain slots we are reserving for master's level students, especially on Indian side. So if you are interested, this would be a program to apply. But the only problem here is that given the travel ban, we're not able to bring this year physically the students to India. So we'll have to run this program in virtual mode for this year. And hopefully from next year onwards, we will be able to travel to India and give these students a flavor of the Indian labs and how the research culture is, and also the whole cultural aspect of these trips, because a lot of these students would be traveling for the first time. So thank you very much. I think it was a great opportunity. I wanted to thank Dr. Ajay Kumar for the invitation. And if there are any questions, I would be happy to answer them.
Yeah, thank you so much. Thank you, Professor Nikhil. It was really a very insightful talk. And now I request all the participants, students, if they have any queries, they can directly ask Professor Nikhil Gupta.
I think one of the messages was about the other sampling method. So I think it's an example that you can find the sampling methods or you can develop more efficient sampling methods. In this work, I didn't claim to invent any new sampling method or new neural network method. We are applying many of these existing methods. But the focus here is to really twofolds. First, the reduction in the total experimental effort that we have. And the second one was here is to find out a meaningful interpretation of storage modulus, which we were successful in doing here.
Okay, thank you. Any other question? Yeah. So if there is no question, yeah, okay. Yeah. So I think one more question from Dr. Ravi Shankar.
Professor Gupta, could you tell us about some LVE? What is the importance of LVE in linear viscoelastic region? So normally.
So, linear viscoelasticity, okay, so linear viscoelasticity is a little bit easier to deal with. I think the latest paper that we have published is in the nonlinear viscoelasticity. It came out in Journal of Composite Materials, if I remember correctly. The problem here is not related to simply the viscoelasticity. The problem here is that the frequency domain properties that we are measuring, and you can expand the horizon a little bit more, saying that the data coming from your ultrasonic imaging, where you can measure the elastic modulus, and we always see that there is a difference between elastic modulus measured from tensile test and the one measured from ultrasonic measurements. Why are they a little bit different? You can also consider acoustic methods where there is always a little bit of a difference. And then there are other frequency domain methods, which are simply the vibration method. So nature of the material does not change based on the type of test method that you are applying. And linear viscoelasticity, most of these equations that I showed are built for linear viscoelasticity in this presentation. This new paper that we have are extending these equations to nonlinear viscoelasticity. But my focus here was really to make you aware of this problem of time domain properties versus frequency domain properties.
Okay. Thank you so much. Any other question from the audience? So I think if there is no question from the audience, let us thank Professor Nikhil Gupta for the wonderful talk. And today he has explained about reduction in the materials characterization efforts. And I hope that all of you have understood his talk, and it will be beneficial for your academic career. So thank you so much, Professor Nikhil. I look forward to see you. May not be this year due to this pandemic. I was really waiting for you to, when you are visiting India, we would like to host you at IIT Tirupati, and we will have more interaction and how we can collaborate and work together.
Sure.
Yeah, for this Indo-US program, some of our students will be applying. So I will be informing you about that, and so that will
Sounds
be
good.
that is a wonderful opportunity for our students. Yeah, thank you so much. Thank you so much. Yeah,
thank you.
Yeah. So with this, we will have our closing ceremony. Now I request Professor Ravi Shankar to deliver the concluding remarks for our international webinar. Professor Ravi Shankar.
Yeah, thank you, Dr. Achai, for organizing all these things by taking much efforts. Even though it's a group event of Department of Mechanical Engineering, but most of the responsibilities that are taken care by Ajay. So I wish to thank on behalf of Department of Mechanical Engineering and in particular from the manufacturing fraternity. So coming to the concluding remarks, thank you for all the people who are there, from the speakers to the participants to the mechanical fraternity who has taken in and out of their time to spend most of in the international webinar. So the most of the things, no, whenever you want to take this type of webinars and other things, you need a proper permissions and other things. First and foremost, thanks goes to the Professor K.N. Satyanarayan sir for his approval and kind and continuous support, and followed by Department of Mechanical Engineering HOD, Dr. Madan. So for his timely support and other things. So we are all thankful for the speakers ranging of from across the globe. So first day we have Professor Pedro from Aalto University, friction-based welding, and we have Professor Gaurav Mohanty on Institute of Mechanical Testing. Then after the break, we have combination of industry and academia from Professor Klein and Professor Campbell from UK on obtaining metal plasticity and failure characteristics. At the end, we have Professor Surya Kalidindi from Georgia Tech on AI-based knowledge systems for accelerated metal innovations. So this is the first day we have. And the following to second day in the early sessions, we have Professor Satish Bukkapattam and Dr. Bhaskar on AI-driven characterization and process monitoring from Texas A&M. Then followed by Professor Pradeep Menges, who talked about tribology in advanced manufacturing from University of Reno, Nevada. Then in the afternoon, we have David Cleel from Washington State University on microstructural evaluation during deformation, and Bilash from Instron. So we have a blend of people from academia as well as from the industry, so that our participants will get a good flavor of the knowledge. It's not only about the bookish or the practical oriented, but also many people have demonstrated some of the case studies in between this, what are the laboratory scale as well as from the practical application also. In the after the lunch, that is what I would like to emphasize, that Devdutt Patro from Ducom Institutions, Ducom Instruments on Tribology 4.0, Chintan Bhatt from Anton Par on surface characterization, and at last we have a good on viscoelastic materials. In particular, I work into the area of micro nano manufacturing, and especially most of my research work, in particularly in my PhD, if I see, I work into rheology of complex fluids and finishing fluids. Basically, I work into viscoelastic finishing fluids and other things. So I'm more than happy to listen to Professor Nikhil Gupta from New York University on reduction in material characterization and effort. So when I saw the curve, automatically being a rheology guy, I can say that this might be done by the rheometer and other things. This is what I was very fascinated about. All the speakers across the globe, they have put their efforts to make this particular webinar a great success, and hope all the participants might have gained a lot of knowledge. And if always IIT Tirupati is open to you, and we are also thankful for all the faculty who are the resource persons. We wish to have you at IIT Tirupati if there is a chance of international conference once the pandemic is completed. And at last, no, all the good things comes to an end at certain point of time. So it is the right time to end with a successful note that hope you gained a lot of knowledge from this one, and your gaining knowledge will enhance your skills in terms of academia. I'm telling about the participants and academia, and into your practical oriented in universities and institutions. Thank you one and all for your kind support, and we expect your support in upcoming webinars or international conferences, which we are going to conduct in upcoming time. Thank you.
Yeah. So thank you so much, Professor Ravi Shankar. Now I request Dr. D.V. Kiran for vote of thanks. Dr. D.V. Kiran.
Good evening and good morning. So we are concluding our 2-day session on the advances in materials processing and mechanical testing with a vote of thanks. So I feel honored and privileged to get the opportunity to propose a vote of thanks on this special day. On behalf of the organizing committee and Department of Mechanical Engineering, IIT Tirupati, I convey my regards and hearty thanks to all eminent speakers and participants. I'm very much thankful to all the sponsors of the webinar for their generous financial support. I would also like to thank the organizing team, staff members, and student volunteers who put a lot of effort into organizing this webinar. We thank once again all the speakers for accepting our invitation and sharing their inspirational research experiences. All of us who participated in this webinar have learned a lot from the speaker's content, and thank you very much. This webinar also allowed us to interact with the speakers and look for the collaboration in the near future. I conclude my vote of thanks by thanking Professor Satyanarayana, Director, IIT Tirupati, for his continuous encouragement in organizing this webinar. Thank you. Good night and good day.